Okay, yeah. Okay, so let me begin by really thanking Emergence for this opportunity, not just for the hackathon. I mean, so we have a situation which is unusual where two technologies have both matured. Maybe not unusual, but we have a situation where two technologies have matured at the same time. So on the one hand, you have generative AI, which everybody knows about. On the other hand, formal methods have been around for quite a long time, what would be broadly considered formal methods. But they have also grown a lot. And these two complement each other extremely well. So the idea of the hackathon, it's quite an ambitious goal. And this workshop is to make it maybe a little more reachable, is to try to work on small cases of what is using Lean and using formal verification to make AI reliable. We'll later on discuss, so these tutorial sessions are simply an introduction to Lean, but later we'll discuss the hackathon portion, what is the idea, and there are basically two ways in which you can make things reliable. One is make the agent's own behavior reliable. They don't do things that are dangerous. And the other is to verify the output of agents. And so there will be different projects which will be of both kinds. But right now I'll simply start by introducing Lean. Lean is a programming language. It is, so far as I know, one of only two languages, the other being Idris, but which is not taken off as far as I can tell, which has the feature of being at the same time a self-hosting programming language. It's a programming language which runs fast enough that Lean is written itself in Lean. The program that's running here is in Lean. Yeah, so it is, and at the same time, it's a system where you can integrate proofs into theorems. It also lets you integrate what is called metaprogramming, which we'll see today because that's essential for the projects, together with programs and proofs. So what do I mean by this? Let me get started. Sorry, should I make the size one bigger or is that font size fine? I think this is fine. One bigger would be nice. Fine, no problem. And I think there is this thing called Zen mode, which might be also. Okay, let's get things going here. So let's start with something very simple. We'll define a function that finds the smallest element in a list. You can do this in any programming language, but just to show how Lean works, let's start off with it. Okay, I'm going to rename this. Okay, there is Copilot acting up. Okay, so let's call it smallest. Okay, and I'm given a list of natural numbers. Okay, okay, let me just do it. Smallest x and y's. Okay, so is this correct? I'm sorry, it's not, it's just smallest of y's. Okay, I have very quickly ended up in the situation where Copilot feeds me wrong stuff. So let me correct it and then turn to the examples. Okay, so let's start. How would I try to define the smallest element in a list? If you have a list with one element, so we use pattern matching. Now pattern matching is even in Python. Many languages have it. And it's completely intuitive what is happening when you see this, even if you're seeing it for the first time. If I have a list with one element, then that element is the smallest. No problem. What if I have a list with at least two elements? Then I can write it as x, which is the first element, y, which is the second element, and z's, which is the rest of the elements. Okay, so colon is add in the beginning an element to a list. So then you look at the smallest element of y followed by z's and take the minimum of that in x. This becomes the smallest element. Okay, so far so good. You already see one feature of Lean here, which is an error here. It's telling you there's a missing case. So this is the first instance where you see that Lean checks things for you. Okay, if you did this in a language which was more liberal, you would just do this, you would run, and somebody would give an empty list, and then you would have an error. Okay, but Lean notices there's a missing case. It's saying, what should I do in this missing case? Okay, and we'll solve this in various ways. One is that I'm going to call this 0. If the list is empty, I'm just going to return 0. This is not great. I mean, this is an invalid value, but in this case, it's okay. Okay, and so this is the first option we can do. We'll see there are better options. That is the point of Lean. But to do this, I'm going to just change my program here. I'm going to call this smallest I. In a little while, you'll know what that I stands for. Okay, those who know some Lean can try to, or some functional language might try to guess what that I stands for. For whatever reason, I'm calling it smallest I. We'll return to that. But that's not an important point. So the first thing is we can just write a program, and then one of the very great conveniences of Lean is that it has a notebook-like interface. That is to say, we are working in, so this is Visual Studio Code. We are working in that. I can simply calculate straight away. Okay, so I can evaluate a list of natural numbers. Hash eval is evaluate, and then it evaluates C by compiling and running. It runs it on the spot, and we can evaluate it. So Lean can be used as a functional, as just a programming language, and it's a very pleasant one to work in. So ergonomic, and it has this nice feature that you run it in an interpreter mode. It compiles and runs, and you can immediately see the value. It's like a console or the notebook. It's convenient to have it, one feature. Okay, but I don't like this for the present, even though this kind of thing is done quite a lot in this context, because, well, what if you're writing a stack machine, which we will see later and so on, and when you do something invalid, you could write in a part of memory which is not allocated to you, you'll get a buffer overflow or underflow and have a vulnerability. So we don't want to have an invalid case, and this is the first case where Lean offers something that very few other languages do. So here's my second definition of smallest. Okay, this time I'm going to take a list of natural numbers. Okay, and I'll remove this. Since Copilot did the hard work for me, I'll accept what it did after checking that it's correct. Okay. So now you see the difference in how I have defined this list. I have taken a list, and what is H? The term H is used, H is for hypothesis. I throw in the hypothesis that the list is not empty. Okay, and I'm giving it a natural number. Now, the cases, the first two cases are, the first case is just the same. If it's a singleton list, it's a singleton list. What if it has at least two elements? They're X, they're Y, and then something that follows. Well, then what we get is the minimum of X and the smallest of Y's colon Z's. But note, we had to do something else here. If I wrote smallest Y's colon Z's, that's not enough, because smallest is defined only if the list is not empty. Okay, so if we go here, we'll get the information here. On the right hand side, you see what is the info view. It's telling that I have to show that the list which is Y and Z's is not empty, because I can only call the smallest function if the list is not empty. Okay, so this is the first special feature we are seeing. I want to show a few other things. I want to emphasize a couple of natures of these. So I'll take relatively simple examples, but emphasize certain key points about it. So what I should emphasize, if you look at the syntax, this and this look almost the same, L and H. But L is data, while H is a property, what in logic would be called a proposition. Okay, so there is a deep notion called propositions as types. But for this hackathon, we'll take a very pragmatic view. What you notice is they look almost the same. So it's not just that you have something deep underlying it, but when you're thinking about it, where everybody deals with data when they're writing programs, you can deal with properties just as if they were data, no difference. Okay, you will even output properties here. So notice that formal similarity. So this smallest has two arguments. One of them is the list, and the second is the property of the list. Now, to prove a property, there is what is called tactic mode. We'll see that again in a moment. We'll see a little more in a moment. Okay, so when you say by, it means I'm going to use tactics, which is some automation to prove things. And once you enter tactics, you will see on the right this thing called the info view. It will show you the goals. I mean, it will tell you what all you have. I have a list, L of list of natural numbers. I have X and Y, I have Z's, and I have this hypothesis, all of which is actually ignored. All I have to prove is the list which consists of y followed by something is non-empty. But of course it's non-empty, it has at least one element. And there's a tactic called simp, which is simplify, and just simplification will tell you how to do it. Okay? So these are just to get familiar. Yeah, so please feel free to interrupt if you have questions. So now you notice there is no error on that match, because Lean was smart enough to know that if I assume the list is non-empty, the empty list case doesn't come. So I could just drop it. Okay? I could also include it and say by simp or something like that. There are various ways of doing it. But just notice that as soon as that case was not needed, it's not needed. So this is nice. Fine. So this has actually already, yeah. So Zs is how it is read. This is in functional languages. So the so colon means prepend. Add it to the beginning. Zs is just the name. Okay. So this is naming convention in Haskell and so on, which is I'm following here. Which X is a natural number, Y is a natural number, Zs is a list of natural numbers. So this is saying list is of the form a single element X, which I could also, by the way, write as X : an empty list. So X followed by an empty list, or X and Y followed by anything at all, which is Zs. So if I say Y : Zs, that's a list which contains the second element onwards. So you take the smallest of the second element onwards, minimum of that with the first element. But you can only take the smallest if you know a list is not empty. So you have to prove that second element's onwards is non-empty. So you use by simp, and that does it for you. Okay. So again, to emphasize, it caught an error very early, and it proofs and arguments just look like each other, no difference. Let's go on. So fine, but you could make all sorts of logical errors. What do we know about the smallest element of the list? Fundamentally, we know two things. First, it has to be an element in the list. Okay? So let's prove that. Okay. So I'm not going to do this here. So I'll, okay. We'll get Copilot to shut up for a bit and say sorry. Okay. So let me check that the statement is correct. So we are showing smallest. Suppose I take a list which is not empty. Then the claim is that smallest LH is an element in list. This belongs to a list. Okay. Smallest has to be an element of the list. This is one of the logical properties here. Well, how do we prove it? Fortunately, proofs in Lean have become easier and easier with various sophisticated automation. So here we can, so sorry, by the way, is a proof placeholder. It says, it gives technically a proof, but the yellow says that we use sorry. It uses sorry. So you can use it temporarily as a halt. Yeah. If you do this thing in the presence of kids, they find it very funny saying sorries in your code, as I know. But so what we can do is smallest is defined by induction, and there is this fancy tactic called fun induction, smallest. Okay. What this does is it breaks up into cases, two cases, the empty one and the other case. And because it's an induction, it also picks up the correct induction hypothesis. So this is a really smart tactic. Okay. And then there is another tactic called grind, which does all kinds of automation, and it just proves it for you. So every time I do these kinds of examples, a few months later, my proofs get shorter and shorter because Lean is getting better and better. So here we are. So what we have done is we have proved it's the smallest is a member of the list. What is the other property of the smallest of the list? It is that any element in the list is greater than or equal to the smallest element. So let's prove that as well. And then I'll make a couple of comments. Okay. Okay, fine. So Copilot completed. By the way, don't overestimate Copilot. I have a drafts. Copilot is smart, but I have a drafts folder where many of these proofs are there. So sometimes it's actually copying and you think it has very smartly figured out a proof. But sometimes it really is smart. So yeah. So smallest less than all is that if I take a non-empty list and I take any element, the smallest element is less than or equal to this. The proof actually looks the same. If you go here, you'll see it's quite different. The goals are different, but both of them are proved by induction and you take care of it, automation. Yeah, so they're at some mathematical level, they're all just proofs by induction. Okay, but an induction tailored not just to natural numbers, to the specific definition of the smallest. Yeah, so at this point, yeah, I should say all this code is going to, okay, so we'll move on to the other things after, okay, a couple of comments to make again. So that I am emphasizing this, I'll reduce the emphasizing, I'll say this time to time later. Notice the extreme parallel between this and this. So this used the word def, this used the word theorem. I could actually even use the word def here. It's perfectly legal. There's a name, there are arguments, and there is something on the right hand side which is the type. So in this case it's natural numbers, in this case it's a property. Okay, so the magic of propositions of types is that a theorem and definition look almost the same. You have a name, you have some arguments, some of the arguments may be data, some of the arguments may be properties. And what you return may be data like a natural numbers, or it may be properties, or it can be a mix of the two. Okay, if you put them together in a structure. So that seamlessly you can go between data and properties. They just look the same. Yeah. The big difference is that we use the automation when we prove things, which you don't have to, but it is convenient. And given the shortage of time today, I will not show proofs without automation. In a full course or even a full workshop, one should see them to understand what is going on. But yeah, sorry, you had a question? I can't hear again. Yes. Huh? Yes. That's right. To do what? To prove what? Oh, because you're proving a lot about the list. You're talking about here, right?
No. In the smallest function.
Smallest function, yeah.
Here, that is.
There is no tactic. Oh, this tactic.
Yeah.
Very good point. It's because smallest function, let's look at its signature. It says given a list and a proof that it's non-empty, it gives you a natural number. Now here, what is the list? It's y : z's. Thanks for the question. Our original list was x, y, and z's.
Yes.
Okay? So we have the hypothesis that that is not empty. But here we are calling the function with a different list. So we have to show that this different list is not empty.
Okay.
Yeah?
So the original L is not empty checks for the entire list.
Exactly.
Yeah.
So H is x : y : z's. Yeah. So if we go here, in fact, you'll see by the hypothesis, H is saying x, y, and z is non-empty. And this is saying y is z is not empty. Which is actually not a consequence of H, because we have shortened the list, but a list with at least one element is not empty. It's a separate proof by simplification. Yeah, thanks. Yeah. Yeah.
That should work, right? Because
if you write smallest,
if we instead of y : z's, we just replace it with y's or some x's or something like that.
yes.
Instead of using the cons.
Okay. So instead of having x : y : z's, I just wrote x : y's.
Yeah.
You're correct, but that will depend on the priority of matching. I'd rather make my cases disjoint.
Okay.
Because
So
yes,
yeah.
I mean, you could as a programming, in fact, programming you would do it, and in Lean it happens in order. But I want to think more mathematically. You're correct, but I'll tell you the motivation why I wrote it this way. If I just wrote x : y's instead of writing this, then what happens is that the case where y's is empty is the first case.
Yeah.
But that first case comes earlier, so it matches.
Okay.
I'd rather make the cases disjoint rather than depending on order of cases.
Okay.
Yeah, I don't know whether Lean's automation will also work based on order of cases or not. I haven't tested it. But my motivation was from my clear thinking point of view. You're correct that because first case is missed when we reach the second case, there was no need for having... No, but then I would have to... Oh no, the second point is that if the y's was empty, I could not say smallest y's and by simple.
No, but we have the case that L is not empty, and then we have eliminated single element case, so it must.
Yeah,
be
so
more
you
than
would have
two.
to prove with a little more work that y's are not empty because the single element case is eliminated
Yeah, okay.
in a match.
Yeah, yeah.
I think one could maybe do that, but it's harder.
Yeah.
But anyway, this is cleaner. I just wanted to make the cases disjoint. But you're correct that the order of cases would mean you would get the same definition as a program. But sometimes the same definition of program may be harder to prove, like in this case. Yeah. Yeah. But the other point here is, by the way, I don't actually need a hypothesis that it's non-empty. What happens in an empty list? Smallest is still less than or equal to everything. I'm sorry.
Excuse me, sir.
No, huh? Sorry? I need to use the other smallest, which I'll get to later. Yeah, thanks. Thanks, Amrit.
Sir?
Yeah, I remembered planning some things like that. Yeah. Okay.
How would I go about running smallest? Like,
Huh? Thank you. I almost forgot. How would we go about running smallest? And that will bring another feature of Lean. Thank you. So let's evaluate smallest. And it will not work. Yeah. Okay, Copilot answered this question, but I'll just first do it without it. So if I just wrote this, there's a problem. It will give you an error because smallest is a function which will take a list and something else. And if you don't give it something else, it's still a function. Okay? But I can use by simp. That means that I got this list and a proof that it's not empty. Okay? And the proof here is the proof that this list is not empty. And simplification showed this list. Okay? So now I can run it. But this seems like a pain. Why do I want to keep having to type by simp, right? Can I get rid of by simp? So let's see another feature of Lean. Another feature of Lean is that it's amazingly easy to extend its syntax. Okay? So I don't want to keep saying, why I keep saying by simp, why repeat myself. So we're going to see a lot about extending syntax, but this is bad. Code, it's better to call it smallest percent. Conventionally, things like this we use smallest. Okay, so smallest percent is a macro, as it is called. It is some new notation. It expands to this, and let's eval. So now suddenly, if I just say smallest percent, it automatically plugs in by simp. Again, you can see what we have. In the afternoon, you'll see a lot about extending the syntax of Lean. But this was a demo, so it's really easy to extend the syntax of Lean. In fact, when Lean kept coming, there used to be complaints. I mean, I like this syntax, and then Leo de Mora would always say, then extend it. I mean, you add that, and they would demonstrate it. Like this by mode used to be begin and end in Lean 3, and people would say, I like begin and end. He said, okay, sure, make begin and end. Here's how you do it. Okay, so it's very extensible. We'll see. This is the less simpler form of extending, but I wanted to show that it's really simple. Okay, so now, yeah. Are all tactics proof by induction? Not at all. Tactics is a very powerful form of automation which generates a proof in the foundations of Lean. There is a whole range of tactics. For example, grind is not proof by induction. Grind involves what's called an SMT solver. So it can solve using linear programming. It does simplification. It does searching. All sorts of other things. Yeah. So there are tactics. Simp itself is a fairly complex tactic. It uses simplifications in all sorts of ways. But simp is a sort of monotonic tactic. It doesn't backtrack. Grind does backtracking, etc. So no, tactics are a whole range of automation. Writing tactics itself is a very interesting topic, one which I will not have time for today. Yeah, so, right. Yeah, so I'll move to the next file. Thanks. Any other questions? Yeah. You use theorem, meaning you don't evaluate them. These theorems, the presence of these theorems tells you that your implementation of smallest is correct. Right? You see these two properties, you know immediately. So they guard you against logical errors. So if you're going to write a program, as we'll see quicksort as another example, you prove properties of the program to see that it is logically correct. So that is the value of a theorem as far as programming is concerned. Yeah, so, but you can use theorems to prove other theorems. So that is another sense in which you use it. And you can use theorems where function like you wanted to say HL is not 0. Here we use simp, but you could use a theorem which told you that list was not 0 also. Yeah. Yeah. Yes. Uh-huh. Okay, sorry. Due to shortage of time, this is an important question. How would we generally prove theorems in Lean? Due to shortage of time, I am not going to answer that. I want to move to other things. Yeah, this is a good point. How would, by the way, but with natural numbers, subtraction behaves in a very weird way. That's another important point, and another important point which I'm not going to get to for shortage of time. Yeah. Yeah. Exactly. So that's, thanks Ashish. So that's the point. So where we use the hypothesis here, we just use syntactic, but we may use theorems, but also to grind and simp, you can tell them use this theorem. So grind with, we'll see more complex examples later. So after a while, I'll switch away from live coding for time. At that time, we'll see more complex examples. So you can use theorems either directly for filling in the hypothesis, and you can use them indirectly by passing them to tactics. If they tell you correctness, they can use for other theorems as well. Okay. So now, any other questions? I'll move to second item on the agenda, and then I'll come back to smallest. Yeah. So I had a list of plan. Yeah. Yeah. Ah, there's also adder. Yeah. So as I move to LeanLang, as you see, just all this thing is going to go to a repository called LeanLang. I'll share it on the Zulip where that is. Its name, as you would see, is I had a geographical series, so it's continued the series. This is a repository where I'll put all my expository works. I had a previous one where I used it as well. So I actually in Singapore I had a thing called LeanLang. So then in China I had Lean Panda. So continuing the animal series, I wanted to actually have Lean Loris and IISc, but that was I had already used for something else. LeanLang has an accidental pun though, besides being alliterative, right? Like Mysore or Bengaluru or something, it's the land of LeanLang. I mean, it's the town or city of LeanLang, so it's accidental pun. So LeanLang is where this code will go. So we'll turn to, okay, the code itself. So first thing we have seen, I think we have seen already very attractive features of Lean, the seamless integration of theorems and proofs, and that you can prove you're logically correct. Okay, not merely that you don't crash or something. Okay, so now let's define some more functions because I want to see you define functions, an important point which is implicit and explicit parameters in a list. So let me quickly define some functions. I'll take double of a list, but I'm not just going to look at lists of natural numbers. I'll take any type, and I take a list of type. No, so I just mean this Copilot completely misunderstood. In fairness, my name is not good. L plus plus L. Okay. So now this is looking at not just a list of natural numbers. You can look at a list of strings, list of anything you want. So alpha is a type, which is going to be list, which could be string, natural number, everything. By the way, basic question, you type \A or \alpha, you get Greek letters. It's conventional in Lean to use Greek letters for types. So list of alpha. As an example, if I want to evaluate list of nat and 1, 3, 4, 5. What am I saying? Sorry. Double list. If I evaluate 1, 3, 5, it's just giving me 1, 3, 5 and 1, 3, 5. Okay. So similarly, I can evaluate a list of strings. Yeah. Hello world, yes, hello world. So plus plus is the concatenation operator or append operator. It takes this and does this this way. Now when you look at this, you realize that why am I supposed to type nat? Why am I supposed to type string? It already knows these are strings. Isn't that kind of redundant? Okay, so this is what brings us to the concept of implicit parameters. But first, no, I don't please want, okay, it's Copilot wants to keep giving examples here. Okay. So I have a list of strings. again, ABC. So I'm going to change this. I'll tell it, you know these are strings. Why do you want me to tell you this? So I can just put an underscore there. Okay. And when I put an underscore there, it tells me figure out what that is. But how do you figure out? By matching types. So these are called, so this is what would be implicitly given. It's implicitly given by matching types. Now I want to emphasize this is only by matching types because we'll soon see something more sophisticated called type class inference. Okay, so, but, so you say underscore you do it, but if you do it the other way, it's of course rubbish. So if I say eval, double list, nat, and underscore, it tells me don't know how to synthesize placeholder, meaning I'm telling I'm given a list of natural numbers, double it. It says how do I know what list it is? The fact that it's a list of natural numbers doesn't tell you what the list is. Okay, so let me use a cool feature of Lean which is for learning and teaching guard and messages. So I can type this and then update. So instead of an error, it says it doesn't know how to have type placeholders. Okay. But now the first parameter can always be deduced. So why bother to specify the first parameter? So we can make it implicit. I'll call it double list. I'll give it a shorter name. And I put braces. Okay. So this time Copilot did it here. And when I put a parameter in braces, it says this is an implicit parameter. You figure it out. Okay. So now if I eval double list of 135, it filled in alpha as a natural element. So this is our second topic. So we had functions. Now we are looking at implicit parameters. Emphasize that just from matching types, it can figure out. And you all can figure out what this is. Okay, so this is another concept. Now, sometimes I want to be explicit. Maybe I really wanted this to be integers rather than natural numbers, in which case, maybe we'll get Copilot to shut up. I can use at double list and then nat 135. So when I use an at before it, it makes all parameters explicit. Okay, so this is one way. This is a point, reason I want to make this eval. So I can also do a slightly perverse thing. I made it explicit and then said figure it out. So that's also fine. Okay, so there are parameters that are implicit and explicit. And this is the one thing that we wanted to do. Okay, so now I hope this is a minor point. But the reason I emphasize this so much is because we are now going to come to a more sophisticated minutes. Okay. So now let's take something a little more complicated. Okay. Let me just say what it is. So list of pairs using do notation. Okay. So far we did simple things to this. Now suppose I have two different lists. They may be of two different types. And I want to have pairs of elements in that list. This is a little bit complicated. And so this will be where we'll see one more feature of Lean, which is what I call Monads. Yeah, so monad is, I'll make a comment on that. But let's just see how this works in an example. Okay, so suppose we have list of pairs. But I don't want it to be natural numbers. I'll take any two types, alpha, beta, type, L1 is list. Is list not a monad? I have to import MATLAB. Thank you. Okay, this is going to take a little time, but while it compiles, yeah, compile it. So here is something, let me just eval and then explain. It's going to take a minute to import MATLAB, and we'll get to rapid introduction here. So I'll come back to smallest in a few minutes. Let's look at this code anyway. We got it. Okay. So first of all, let's see what this code did. What this code did was looked at all pairs, where the first element is in the first list and second element is in the second list. Now, how did it do this? Programming-wise, this is slightly complicated. If you think what you do in Python, you'd probably take an empty list, you will nest two for loops, and then keep adding it to the list and output it. Okay? But list in Lean and in other functional languages, you have a concept called a monad. Okay? What is the concept called a monad? Everybody has their own views of monad. It's somebody actually joked that there are so many tutorials on monads because every time somebody understands monads, they're so happy they write a tutorial on it. Okay. So what I'll do is I'll just say that it's a common structure that you see in many connections. It's like groups or whatever, like you see in an algebraic structure. And we'll learn how to work with this common structure. Okay. We'll see a little more. Prathamesh might explain a little more. I don't know. I will of what this common structure is. We'll see lots of examples, but the list is the simplest of these. I imported Lean's mathematics library. Is that in red? Is that in red? I'm going to exit there now. Everything is in red. That's red usually. Oh, okay. Card message has changed. That's okay. So if you import the Lean's math library, and natural numbers can be written nicely with the blackboard monad. Okay. So what happened here? Let's read this list. It says I have to return a list. List is a collection. Collections are examples of monads. There are other things which are examples of monads, as we'll see with states. Okay. And so when I say do, it means I'm looking at a monad, and X, this arrow says extract something from list 1. Okay. And Y, arrow L2 says extract Y from list 2, and return is return the pair. So you can think of this like Python's for comprehension, for X in L1, for Y in L2. The arrow extracts things from monads. But this monad is a common structure which applies not only for collections but for things that depend on side effects or things that depend on state and many other things. We'll see that through the day. Okay. So this is the one feature of lists I wanted to show. Okay. Now let's try to do something else. I'm going to change this definition a little bit. And let's try to return sums of lists. Okay. So sums return, and now we'll get an error. Yeah. So it's yeah. I'll find up in. I'll take another 3 minutes or so. I'll shorten the next one. I just wanted to. Okay. Maybe I'll end in about 2 or 3 minutes. It's 10, 14. Yeah. So. I'll just shift topics to the next one. There's no problem with that. Okay, so here I wanted to actually point out one thing. So now what I want to do is I want to add elements. Now let's take only one type. Let's take a list of type alpha and let both lists be of type. Sorry, I let Copilot listen to try too much. Just one. Okay. So what is the problem here? What I want is if I have a list of natural numbers and list of natural numbers, I can look at sums of pairs of natural numbers. But given the type alpha, I do not know how to add things of type alpha. Okay. I don't know how to add things of type alpha. So here, let me add a parameter, which is the type class parameter. I think the sensible thing will be for me to just stop with that and explain with examples in the second session instead of running over time. So I want to add x plus y but we don't know how to add things. For example, we cannot add strings or functions. So what we need to do is provide another kind of parameter, which is called a type class parameter. This has square brackets. Add alpha is capability of adding alpha. Okay. So what does this mean? We have to see examples to understand this. We have to get familiar with this. But since it's just past 10:15, I'll stop, and in the last session of this morning, I'll return. So as everything takes longer than expected, I'll return to this, and we'll see how we can tell Lean how to add things, and then we'll return to how we can define types and so on. Okay. So right now I'll stop, and Pratimeshwar can set up his laptop and take over. Thank you, Professor. So now we have our next speaker, Professor Prathamesh. He is Assistant Professor of Computer Science at Kriya University. And he works at the intersection of logic, application of formal methods in computer science and mathematics. So he will be covering more about LeanLang and covering different aspects from what we have covered yet. So, yeah. Thanks a lot, Aileen. So, briefly, I have 45 minutes, and I think, so I just kind of tried what I'm going to do is I'm going to basically introduce a few concepts. I try to understand, like, as much as possible for those of you who haven't seen Lean. The point is, even if you don't quite understand everything, it's fine. I mean, you have time left for the next few days to kind of do it, but then as long as you get familiar with the language for it. Okay. So, I basically started off by saying, okay, what we're going to do is we're going to really look at how types are constructed. So that's going to be one of the primary things, and how do we really work with types that we construct on our own. And that often, especially in verification, you will have to sometimes build your own custom types, and that's kind of where we're coming with. So what we're going to start off is basically constructing our own type. Okay, so this is a type of bool, and we're in Bengaluru, so I kind of wrote the Kannada words for true and false, Nija and Sulu, if I'm not wrong. I mean, I asked Google Translate, I hope it's fine. Okay, so, Sulu is not false. Okay, I couldn't think of a better one. So, Tapu would be okay, fine. So I could just, okay. So, yeah. So, I mean, this is just telling that these are two elements. This my bool is inhabited, these are the two elements that inhabit this type, and that's all there is to it. Okay, so now, let's, for instance, if I wanted to say build Telugu types, I mean, it's a language that I know better. So I would say, okay, Nijam, which is my bool, Telugu bool, and Abhaddam, which is Telugu in some sense. Okay, it's basically going to look like this. And let's say if you want to kind of create something like a traffic light, you want to create a type of like basically traffic light symbols, you can basically write it as, let's say, red, traffic light, and then you can just basically make it as yellow, and okay, so this is just the simplest example. Remember, these are just finite types that we constructed. These are like just
types of 3 objects. So in addition, we see something else here called rep and decidable equality. Okay. Now the idea here is that rep. Oops. Info you was missing. Sorry. What rep does is it kind of creates objects of this type for display. It basically produces a string equivalent that you can actually see on your info view. And decidable equality ensures it basically derives a decision procedure for equality for this particular type, essentially. Because not every type has an equality that is decidable. I mean, usually, something that mathematicians often quite know that there are definitely many sets that we don't have a decidable equality for. But this basically ensures that the types that we have essentially something that it kind of derives a decision procedure for equality, so that you can actually equate 2 elements and it kind of can return true or false. Okay, so so this is what the rep is doing and this is what decidable equality is doing, and these are 2 things I usually try to keep it on most types that we create. Okay, now we're going to try and now write a small function here. Okay, so this is a negate, and again it's just going to be doing with like what Siddharth is doing. So I'm going to match P with 2 kinds of things. This is now I'm just going with the third boolean, so which is Nija. So Nija is basically I'm going to negate it with Sulu, and dot Sulu is going to negate with Nija. Okay, right? So where it is Nija, so where the is it kind of negates it with this. Okay, so now we can of course just evaluate like as it was said. So you can see that right there on this side, we can see that this is being negated with Sulu, and Sulu gets negated with Nija, and we can also negate and kind of gets back to Nija. Of course, you see something very peculiar here. I have to do something very cumbersome, which is basically put a dot at each point to kind of say that it's identified with the types. So now I just kind of include it in the namespace, and what's the difference we notice here between this and the earlier? Anyone in the audience wants to just take a guess? What's the difference between the evaluate and sorry? So the dot is basically to say that it actually belongs to the type that we are talking about. We have to refer to the type that essentially it's kind of. Okay, so it's a invisible reference to the element that it's a member of that type, which is what we're taking away when we're saying in the namespace. Okay, so it's basically essentially this dot is again, it's basically saying that it's actually my bool.nija. Okay. Okay, so it's basically like a bit of syntactic sugar to say that it's my bool.nija. And here it basically, I don't need to really specify that. Okay. So if I actually just take this away, it does not evaluate because it does not know how to infer the type for this. Okay. So in the namespace, the type inference is unambiguous. So that kind of essentially makes it fairly clear that this is what we are doing here. Okay. And so now we're going to write a simple function which is AND of 2 things, a Boolean operator. So of course negate is a function that has 1 input and 1 output. So this is the simplest way of the naivest way of I can write it. There are 2 elements, P and Q. Okay. And I want to basically kind of write a AND. Hi. Sorry?
Is it possible to go all the way up? Just want to see how my bool is defined. Okay. Okay, it's an inductive. Okay.
It's an inductive type. Okay, so just it's finite inductive type. Okay, so so there are 2 elements, Nija and Sulu, and I'm basically this is a simple pattern matching. I'm kind of trying to say, okay, Nija is Nija, Nija Sulu is. So I'm basically considering all the 4 combinations. But do we really need to do that? We can actually see a lot of redundancies here, right? What would be the redundancies that you really see here? So yeah. Sorry? Can anyone see redundancies here in the patterns? Just a quick question from the audience. Sorry? Yeah. The return value is same for the last 3, right? So basically I can say that for the first one it is, and for everything else, so this is basically underscore, which kind of literally is like placeholder for everything else. And for everything else, you just give me Sulu. Okay. But even here, there is something more interesting. Is there a redundancy we spot here as well? Sorry? Nija is obviously, so very first one, you just map it to the second parameter, right? Like if the first one is Nija, you just map it to the second parameter. Okay, right? So we, instead of actually kind of matching it with two parameters, we just match it with one parameter. And if the first one is Nija, we just map it to whatever is the value of the second parameter, right? So this is like a simple thing. So these are actually some pattern manufacturing optimizations we often do when we are actually writing lean code. And yeah, so this is basically one kind of elegant thing that essentially the kind of pattern matching in functional programming allows us to do. Okay. So similarly, now again, let's try and extend this for OR. And for OR, if you're basically matching, the first one is Nija, everything else is Nija. For whatever else, you get the value, right? You get the second value. No matter what else it is case, for an OR, you get the second value essentially. The first value is Nija. So that's essentially how you kind of do it for an OR. And there's an infix notation we can actually use. Okay, so here, writing my OR, my and all I can actually do. Okay, like for instance, just to tell you, I can do an eval with my and Nija Sulu. It tells me it is Sulu. I can also put a my OR here. My OR, my and Nija Sulu Sulu. It still gives me something, which is Sulu. Okay, but I don't want to kind of quite often, so I can just use an infix operator to just kind of make my syntax prettier. Okay, and we use this infix operator. We can actually, here we are defining it, and these are basically the infix ordering to in which order you want things to order. So, I mean, you can look this up, yeah. And now the question is, so I can just now write Nija plus Sulu for OR, essentially, and I can use for and, I can just use the product. Okay, right? So I don't need to really kind of write down the functions through the name all the time using these infix operators, and that basically means you can actually put them in between. Okay, so that kind of makes life fairly simple and quite elegant. Okay, sorry? So it's the infix ordering in some sense. Okay, so so it's the order of precedence essentially, okay, of application. I mean, I just looked up the table and then got the numbers. Okay, so I mean, yeah, you'll have to kind of figure out where exactly you want it to be. You just can look up the order of table if it conflicts with anything you want to know. Otherwise, you can just, okay, not do with that. Okay, so that's basically where it is. Yeah, yeah. So, okay, sorry. And now I think we'll just try and prove the first theorem. Essentially, okay, sorry, let me just actually just.
Sorry, quick question. Does the infix operator definition, does it interfere with the other plus being used for numerical values?
So in this namespace, it will not.
Okay.
In this namespace, as long as it allows type inference, it will not.
Sorry?
Okay. In this namespace, as long as we allow for type inference, it will not. Okay. But if when you actually take it on the standard, okay, the plus it assumes is naturally the natural number multiplication because of the way it kind of literally works, right? And yeah, yeah. But and outside of it, I mean, again, Nija will not make sense unless you actually invoke the type itself, right? So yeah, outside of the namespace. So yeah. But if you're actually creating another plus for natural numbers, then, which is using the same infix operator for some kind of a custom-made natural numbers, then again it can, yeah. Why not? Like in the sense, sorry? No.
So continue on that question, like plus, would it interfere with the addition?
No, if you're creating your own custom type, I mean, you have to kind of, I mean, so when you're trying to build it, I mean, you can basically express it as, let's say, my bool dot something, or just dot something, then it does the type inference, that part on their own. Okay. But if you, sorry? Yeah. So type class? Sorry. Yeah. Type classes, yeah, definitely, yeah. These are the type class inferences, so yeah. So let's kind of just look at how do we really prove it. So I think this is a simple thing. Actually, this is a type that just consists of two finite case thing. Okay, so for finite, we don't really need induction. So I'm going to just do something like cases P with. So what are the cases for P? Let's say is Nijam. So what do I really need to prove Nijam? Okay. And then let's say I'm going to do this as two sorries. Sulu is sorry. Nija, sorry, Nija. So I have these two objects, which is basically which it is, and I want to kind of so this is basically one of the simple De Morgan laws which you're trying to prove, and I'm saying negate of Nija is negate of this one, and so we are actually taking the very first case. So how do we really kind of do this? So I'm going to basically first simplify the my AND operation. Okay, then I would want to simplify negate. And actually I would rather want to simplify my OR, and then I might want to simplify negate, and then we are done. Okay, so simp is essentially a tactic that like primarily, I mean, it builds on other things that primarily on rewriting. You've declared certain rules as simplification rules, or when I basically explicitly call these rules, I can actually, inside a definition, I can actually put a simp qualifier to say that they actually are simplification rules. So what they do is they kind of rewrite from left to right. Essentially, that's basically, it's a rewriting strategy. Simp does, I mean, especially for those who know some computer science, this is basically a rewriting tactic in some sense. So, which is what it's going to do. And for Sulu, again, I'm just kind of going to repeat the same thing. It should not be very different. So it's going to rewrite these definitions, my AND, my OR, and negate, these definitions for these particular spaces from left to right. Okay, and that's basically going to solve the problem for us. Okay, all right, so, yeah, sorry, example? Oh, thanks. Oh, yes. Example is a theorem that we don't bother to name. I'm not bothering to name here the examples here because I don't want to kind of use these names anywhere. Okay, thanks so much. Yes. And so here I'm actually kind of going to see, again, the same tactic and the same definition both the times. So I can just put this, like what Siddharth has suggested, and just make life simpler. Okay, so I don't need to really kind of work with all of this. So I think I know that this is going to work. So I'm just going to use this and make life simpler by using it for both of them. Okay, so after that, I decided now we kind of will work with what are slightly now building types which are infinite. Okay, finite types, we've seen it. We've got some glimpse of it. Okay, so for this, I've used actually Arabic for this colon, right? You're talking about?
No, it's talking about bracket with semicolon. Apply to all this.
Oh, this is applied to all goals. Yeah. This one, right? You're talking about? Yeah. This is applied to all the goals, right? So basically, as I was saying, essentially all the goals we are going to have the same. Essentially, we remember we had the same tactic, so we're just going to apply it to that. So let me just show it to you. So if you noticed here, here we basically both of them essentially had the same tactic. Okay, right? So essentially I'm saying that whatever goals we get, let's just apply it to this and it'll just keep applying it, and whatever remains is sometimes it presents, but here nothing really remains. Okay, so that's where we are, and yeah. Okay. Is that good? Yeah, sorry. Yeah.
Can we, because we have the syntax plus and star for P and Q, the operations for my and
Yeah.
Can we try rewriting them in the proposition?
Sorry?
In the example, instead of using my and, can we use like the
You want to use a rewrite?
So it's saying you can write it, no, not that.
No, I'm just
Write a statement as negate P plus negate Q.
Negate P. Oh, plus negate Q. Oh, okay. My odd. Okay. Okay, you can do.
and in the simplify as well, we can, I think we can change the my and to plus.
Plus, yeah.
So plus is only
Not it.
not in simp, but yes. Then.
Can we try? I think we can do it in simp as well. Because it's just
Yeah. Okay, sure. But oh, inside the simp you can't. Inside the simp you can't.
You can try and see what happens.
Okay.
I don't think you can.
You can't. You can't use infix definitions within SIMP. I mean, in fact, infix definitions usually, like even on the right side, I mean, they kind of rarely unfold very well. So, so now I think let's kind of get to inductive types. Okay, again, infinite types. So I think, so we basically just borrowed the Arabic numerals, Arabic names. Sifr is, I mean, again, I'm made to believe by Google Translate is 0. I think there are good reasons I think I can trust that. Khalifa is what it says is a successor. I'm not sure about it, but let's just stick to that term. Okay, so now every natural number, remember, can be basically literally written as the following. Okay, I can just write every natural number to be Sifr. I can say every natural number is basically, I mean, so to be Khalifa of Sifr, and every natural number can be really thought of as Khalifa of Sifr. Okay, right? These are the ways we can literally write every natural number. Right? I mean, you can basically just add the number of Khalifas, that's basically the number of natural numbers you have. Okay, so how do we really kind of write it here? So one way is, I'm going to say Sifr is an example of a natural number, and Khalifa is basically a function that takes a natural number and returns a natural number. Now what this creates is basically now Khalifa becomes an injective function, and this is the smallest type which contains these two functions essentially. Okay, so yeah, so which is essentially what is kind of it's going to create, and so it's going to create a type of elements which contains Sifr, Khalifa of Sifr, Khalifa of Sifr, and on. Okay, so now again, just to create some definitions here, now the definitions become recursive again, just in the spirit of what Siddhartha had suggested. So we want to define addition here. Okay, so now the addition on Monad, so we can just define M with Sifr. So if I'm basically adding the first element M, if I'm matching it with Sifr, so then basically addition is just the second number. If you're matching it with successor of some number, Khalifa of K, it is Khalifa of my add Kn. Okay, right? It's basically successor of my add Kn. So this is basically nothing but adding M plus K plus 1 is equal to M plus K plus 1, right? It's just defining this phenomena, more or less. So essentially, right? Sorry, yeah. And which is what it's defining. And I can just kind of just to see here, we can just evaluate this. What do we see here on the right side? Can anyone just spot this part? Which is, so it's actually showing two Khalifas, that's basically it's adding just 1 plus 1, which is 2. Okay, so that's essentially what we are just showing. Okay, yeah. So now I just use some infix operator like this plus with like subscripted with a 1, and I'm just going to repeat the same thing with Khalifa Sifr plus Khalifa Sifr, which looks a little neater. That means I'm adding 1 plus 1 and we get 2, which is what Russell took a lot of time to prove at some point. And so now, just as an example, I'm going to use the reflection tactic here, which essentially just unfolds the definition here, and I'm just proving again 1 plus 1 is 2. I mean, which is the evaluation which I just kind of showed as an example. And again, another example where it just kind of just literally boils down to the working with the definition, which you can show by this reflection tactic. Okay, so let's try and prove something slightly, I mean, which we all know, is that when we actually define addition, we only define addition with 0 on the left. We want to show define with addition on the 0 on the right behaves exactly the same way. So which is basically n1 plus Sifr is equal to n1. Okay. So now, how do you suggest we do this? Sifr plus Sifr is Sifr. So what, sorry, yeah, before this, sorry, I completely forgot about this. So what I'm going to do is, we're going to basically work with the induction tactic. Okay, induction tactic. So it's essentially a tactic that we use to write induction proofs. And so when I write induction n with, I'm basically inducting on essentially natural number n, and I'm basically kind of writing all the cases that we have to consider. Okay, and I'm sorting all the cases just so that I don't have like any unnecessary like squiggly lines, which I hate when I'm actually writing code. So I'm just going to sorry all the cases, and I'm going to say that, okay, let's take the first case Sifr. So induction will have a base case, which is I want to show it for Sifr. That's basically the 0. Okay, and then I show it for the successive element. Okay, assuming that it holds true for n. And oops. Oops. Device power is fine. Yeah. This. Oh, sorry.
Oh yeah, it's my desktop, so I think I have to mirror, yeah. Yeah.
Okay. So it's an induction proof. So induction, basically we have the base case and then we have the inductive case. So the base case is if. So, and you can see on the right side, oops. I think this is loose or, sorry, one second. Let me just.
Is it on high resolution? It's 1920 should the resolution.
1920?
Yeah, that's perfect. Yeah. Loose color.
Oh, okay. It's a loose contact. Or maybe I'll just remove the power for now. We'll have enough. So, sorry. Right, so no, so it's not even like. Oh yeah. Oh. Yeah. Also, 1 second.
Okay, finally.
I hope it stays. Okay. So we see that on the right side, you see the case. And the case is actually telling us is that you want to show that 0 plus 0 is 0. This literally unfolds from the definition of addition. So I can just basically put an RFL here, and that should work. And that works. So now let's actually look at the more interesting case here. So what here is that you see actually some 3 things here. So what exactly is K and IH? Any guesses? I mean, what would you infer from what you see on the screen? Sorry? Sorry? What is inductive hypothesis here? So we need an element of which Khalifa is basically it's a successor, and K is basically the successor element, and IH is basically the name we are giving to the inductive hypothesis. So it requires basically 2 kind of parameters. One is basically the element on which you are inducting, and third is the name of the inductive hypothesis. Okay, so using these, we actually get this. Now IH is the inductive hypothesis. Now remember, these 2 are just variables. I can just call them like R, and I can just call it Timbuktu also. It does not really matter. But of course, the standard preferences, we want to keep in names at something like very well within the naming conventions. So I'm going to call it IH, which is pretty much a naming convention in Lean. So now we want to basically, now we have some result of this kind. And like, how do we really go about proving this? So of course, we want to basically, now the first thing, of course, riffle is not going to work. So what we have to do is we have to kind of decouple addition a bit. So so we've decoupled addition, and do you see something very similar here? Does it exactly match something that we know? Huh? The inductive hypothesis, right? It is exactly the inductive hypothesis. So I can just write it as exact IH. And of course, there are shorter ways to write this, but let's, okay. And as you can see, there's a linter because there's actually a nicer way to write it. So this is basically called lean linter. So, but I'll just kind of skip that for now. Okay, so this is essentially one part of what we're going to do. And so basically simp is a flexible tactic. Okay, yeah. Now, I'm just going to kind of just go back to and show binary trees. Okay, this is something Siddharth again was going to touch upon, but I think I'll just kind of quickly start. Go ahead. Okay. So here, again, we're going to define a new inductive type here. So here, now remember that how do we really think about trees? So the way I would think about a tree is the following. A tree is, I mean, everybody knows a binary tree here. That's something I'm assuming. Okay, so a tree has an object. It has a left side and a right side. so an object, it can be something like 5, then like it has something like 4, and then it will have some elements like this. It's a binary tree. Okay. So what I'm going to do is we're going to take a very specific binary tree which has leaves. Okay. So in the sense the leaves are not labeled, only the nodes are labeled. Okay. So I'm only going to label the leaves, and I'm not going to label the nodes. Sorry, I'm only going to label the nodes and not the leaves. Okay. And so we have these nice nodes here, and this is what a tree looks like. So essentially, if you really think about it, a tree has two kinds of object. A leaf by itself is a tree, or a tree is constructed by putting two trees together along with some value, which is the value of the node. Okay, right? So for the node, which basically is essentially can be just all the information is contained in a singular value, and you basically take two other trees and then you put them together. Right? So that's essentially what we really a tree is. So here this is exactly what it is defining. A leaf is a tree, and you can another is it requires a function that takes a tree, a value, and another tree, and it creates a tree. So tree is exactly one kind of these two kinds of objects. Okay. So now just some examples of how you can actually write a tree. It consists of two things: leaf and an injective function, which returns an objective of the type mtree. So mtree is the smallest object that can be built from either of the above. So how are we going to write an object of this kind here? So for instance, I can basically write, so check is just something that just tells you what the type of the object is. So yeah. This just tells me that this is a tree, and this is again another tree. So can we guess what exactly this tree looks like? So this is a tree that I'm actually taken a leaf on the left side, a 4 somewhere around, and then it has, it has basically 3 in the very center. It has 4 and 2 leaves here, and essentially a single leaf on the right side. Okay, so that's essentially this what we've actually kind of described. And the namespace of this we enter again, and I'm just going to write the same definition again. Okay. So let's try and prove some simple properties. So let's assume that someone's kind of created a mirror function. You may want to just mirror something. Okay. So how do you really mirror a tree? Now, for a leaf, you just pattern match and you just basically just send it back to the leaf itself and mirror a tree. Now, if I want to mirror a 2 branches and a value, so the value stays in the center. Nothing changes for that. Okay. But for the left and the right, we again mirror the right side and send it to the left. And we mirror the left side and send it to the right. Right? So that's exactly what we see here in this function. So which is actually a mirror of a lift, of a tree. Now, for instance, and you can see here, this is a tree which has 3 and a right side, it's a leaf. What do we really see is when we evaluate it, we actually get the tree where 3 is still in the center, but on the left side is a single leaf, and on the right side is the tree which was originally on the left side. So which is what we actually see when we kind of do the mirror. Okay. So now, what are the properties you would want to prove? Let's assume that you had a black box mirror function. So this is a simple toy case. So let's assume you want to prove some properties of the mirror function. What would be the properties that you would be invested in proving to say that the mirror function is correct? Or is the mirror function that you would really like? What would be some examples of properties that you would think of? Let's assume a mirror function is a black box with some by developer somewhere. You have no clue how it's working. Apply twice and we get back the same thing, right? So that's the first theorem that we're trying to prove here. Apply twice and we get back the same thing. What about the others? Any other theorems? What if someone then, sorry? They should not be new data. Fine, perfectly fine. Okay, now both of them can be contradicted by one particular example. What would that be? Can you just guess? I can fool you both by just giving you an identity function. Right? I can just fool an identity function, and if you mirror and mirror, you still get back the same thing. Right? So, so I want to just show that there is some tree for which the mirror does not give back itself. Okay. And then I also see that it preserves the size of the tree. That's a little weaker, but I think of the same kind of flavor that was suggested. And then if we actually kind of flatten a tree to a list, okay, right, so these are the 4 properties that you would want to prove. So I'm going to just start off by proving the first former. So let's kind of start off with this, with induction T. Okay, Now I think this is an interesting case because for a tree, for a natural number, we just saw that there was an induction case was basically just taking one smaller element. Okay, in tree we have two smaller elements. There's a left tree and a right tree. Okay, the tree is recursively defined in terms of to the left tree and the right tree as well. Okay, there are two trees that are actually contained inside. For a natural number, there was just one natural number that was basically it was succeeding. Okay, that's a fundamental difference. So we have to account for that when we're actually writing a induction. And so let's start with a very basic tree. So for a leaf would be the first case, and the second case of it would be a node of a tree which has the left, the value, the right, and it will require two induction hypotheses now. I'm going to call it IHL and IHR because I'm saying that the induction hypothesis has to hold true for the left side and the right side both. Okay, otherwise it's not a valid hypothesis. So now the first one is just telling me the mirror of the leaf is the mirror of leaf. So I'm just going to do a simp mirror here, which is going to simplify with using the mirror definition. And now again it asks us to do the mirror. Again we're asking us to check this, so I'm going to do a simp of the mirror. It's going to simplify with mirror, so it's going to kind of give me a few more very complex constructions. So I'm just going to use an ISOP, which is a relatively powerful tool. I mean, it's not as powerful as grind, but it consumes a little less memory. So I think you can just use grind, or in fact, if you want, and that literally takes care of the rest of the theorems here. It just requires like breaking it up into two parts and then kind of working that through. And oh yeah, even that would work, I think. That does it, yeah. Sorry. In fact, we can just kind of literally do this with grind mirror. So we can shorten this proofs, the induction proofs again, like as it was said. So again, like with the cases, you just take the induction proof and these colons essentially tell you that you apply the same tactic to both the goals. It's going to work. And since grind is more powerful than simp, literally it subsumes most of the proofs that simp can do. So yeah. Yeah. Sorry? No, so what happens is the induction hypothesis is already there. It's going to apply the grind to each of the individual subcases. Okay, just like the case. Sorry. Oh, yeah. So, yeah. So let's, one second, I'll just kind of completely answer her question here. So okay, what we are actually doing, I think, just to kind of clear this confusion, is that essentially if you see this proof can be literally solved by having a grind mirror on both the sides. If I just basically put it as grind mirror on both the sides, it can be done. So what we are actually saying is that if I do this grind mirror, I'm basically like for each of the goals just apply the grind mirror that is generated by the induction hypothesis. That's what we are really saying. Okay, so it's a short, elegant proof which writes this. Okay, is that clear? Sorry, huh? Yeah.
For grind, do you need to, when you define the tree data structure,
Yeah.
or tree type in this particular case, you also kind of have this decidable equality.
Yeah.
So is there some dependence over there that you can only apply grind on these kind of functions which are taking these? So you could just drop that deriving and still it works?
That's a good question. I've never tried it. Really. In this case, it doesn't. Yeah. Okay. So now I think the second question is we want to show that. Sorry. Yeah. Yeah.
If grind is not just an SMT solver like Professor Gadgil said, is there a way to like regenerate what steps it is doing in the back end to come to that proof or to come to that shape of the proof?
The proof objects.
Yeah.
So I don't think you can access lean objects in proof. I mean, no, I don't think you. And print. Hash print, huh?
Hash print, mirror of mirror. the one you just proved.
Yeah.
And it will show you in all gory details what
Oh,
the
yeah.
actual proof is. But then you'll have to click on that and then expand it. Or you can say set pp dot whatever, some
Yeah.
expansion thing. Yeah. You can
But
always expand using hash print.
Yeah.
There's a set pp dot all true in. Can you just go there?
Sorry, yeah.
Above that,
Hmm.
above before that, set
Hmm.
set option pp
Yeah.
set option pp dot all
pp dot all
true in
true
true TROS.
Oh, true, huh, yeah.
In
in.
and then look at that print. What is this? Curious.
Okay, I think is there a syntax error here?
Some set hash set option. No. Yeah, never mind. Sorry.
Oh. Oh, hash set option.
No. I got something wrong. Never mind that.
Okay, okay.
Set option. No, it's okay. Never mind. I'll answer it later.
Okay, so here we just want one element that does not do this. Okay, right? So essentially, so now important thing is our goal is of the form there exists. Okay, right? We've kind of come across this new kind of goal that so far we were always proving like, okay, some x is equal to y. We didn't have quantifiers in our goal. Now we are actually trying to prove a goal which has quantifiers in it. And so how do you really get rid of their exists? And usually the basic strategy is this anyway, actually the only way you can really solve any question of their exists kind usually is that you would generally produce an object of that kind. You generally produce an object which would generally satisfy this. So how would you really generate that object? Is that let's just look at this. This is not a tree because this is an unbalanced tree. We know that the mirror of this is not going to be that object. So I'm just going to add use this and so what it does is, if you can see that the goal is essentially this particular goal, which can be literally solved by sim mirror, right? So it can be literally solved by sim mirror, and of course you can also just kind of like just put make it slightly prettier by instead of actually writing something like this, I'm just going to use a shorthand by let st be equal to and the definition of st, and that takes care of this goal, right? So this is essentially a question of proving an object of this kind. And okay, so the last property, this is now the size of the tree. So size of the tree again can be recursively defined. So you have node LVR and 1 plus size of the left tree plus size of the right tree plus 1 gives me that. So is there anything that you can actually see on the board that's kind of slightly redundant again? So anything that be slightly redundant here? V is not something we're actually using on the right side, so we can just underscore this away. And so now the idea here is to prove that the size of the tree of the mirror is essentially the same as the original size of the tree. And again, we can try the induction tactic and induction T with a leaf is should give me sim size of tree mirror, and again we try this again with node L V R I H L I H R, and I'm going to simplify, but we're going to simplify just by adding IHL and IHR, and what we essentially get is just the same thing that's kind of rewritten in a certain slightly way, and I'm just going to use the linear arithmetic solver omega and just get done with this part. Okay. Oh shits. So while we do this in the afternoon, what we're going to actually try and do is actually try and look at a tree which is actually a max heap. So max heap is a tree in which like at the very center you have like higher value than basically the node has a higher value than all its children. The parent has a higher value than all its children. Okay, and try and see like if you actually build a visualizer, which is actually very good, especially if you're like trying to kind of train undergrads or even like for a formal methods expert to kind of actually see a max tree with full visualization to spot any errors. If you want to actually build a visualizer for something, now how do you really verify some correctness properties of that visualizer? Okay, so that's something that we're going to focus with your the undergrad. In the afternoon, and
Mirror.
yeah, okay, yeah. Oh, it's not mirroring. But I think right now the problem is more than the mirror itself. It's a loose contact because mirror should be fine. It's the loose contact right now. Something should be fine. Do you want to just change the port and see if it's the other port works better? Okay. So should I end it? Yeah.
Hello everyone. We'll just take a short break, say around 10 to 15 minutes. We'll have a refreshment and we can join back by 11:15 to 20. Thank you.
वो कर रहा था ऑलरेडी हाँ go for break I think so this should come from this side no this should come from this side. So resolution, can you just check?
Hello? Hello? Guys, there are tea, coffee upstairs. Yeah, please take a short break.
You can first line just give an intro.
Oh, sure, sure.
So, I hope you guys had a good snacks, and I think everybody please settle down so that we can continue with the talks. Yes. So moving on to the next talk. Now we have Professor Abhishek Kumar Singh. He is assistant professor at SERC in IIIT Hyderabad. He primarily works in formal methods, programming languages, software engineering, and trustworthy AI. So today he will be talking about an interesting topic, trustworthy parallel computing for AI at scale. So we welcome Professor.
Yeah, thank you organizers, and especially Professor Siddharth for inviting me for this talk. So this talk might look a little awkward in the setting of Lean, but I will try to justify why this is actually very much related to Lean and why this kind of work helps bring more people into the Lean or theorem proving community. Okay, so the topic for today's talk is trustworthy parallel computing for AI at scale. So parallel computing for AI is at a scale, almost all of us would agree that parallel computing and distributed computing are at the core of modern AI, right? Without parallel computing, you cannot have what you see right now. But the talk is not about writing efficient parallel program, but how to bring more and more trust into these parallel programs. Okay, so again, I mean, the focus of the talk is trust in parallel computing. So this I already talked that you cannot imagine modern AI without parallel and distributed computing, and all of this started somewhere around 2005-06. Before 2005-06, whenever we wanted to, let's say, improve our performance of computing devices, we primarily relied on improving our clock cycle. Okay, but then 2005-06, I mean, we realized that we cannot go beyond this 3 to 4 gigahertz clock cycles. Okay, so if you go beyond this, then your chips start burning. Okay, so then we realized that we need to adopt an alternate strategy where instead of having one super high speed processor, we go to multi-core. Okay, and I recall it very easily because I was doing my BTech, and then these processors were actually introduced in the market. So we came to know about core to duo and then core to quad kind of processor, and now you have on single chip 24 cores. Sorry, I mean something is going out of his screen here, but so what we have today is even more than this 24 cores. Okay, so how it helps now? All your individual this core are 3 to 4 gigahertz, but then combinedly, if you can use the compute power of all of them in some way, then you can achieve 24 times actually performance, almost 24 times performance of a single processor. So you don't need to keep pushing your clock cycle, increasing your clock cycles, and then increasing the temperature of your chips. So again, I mean, during the same time, I mean, when I was hearing about this kind of multi-core processor, this GPU processor also came into the light. And at that time, the primary purpose of this GPU was to somehow offload the main vision or image processing kind of tasks, which are which were assumed to be very monotonous kind of thing, but they required a lot of computational resource of your main CPU. So we were migrating to this GPU at that time, and now all of us know what is the importance of GPU in modern AI also. Okay, so but the primary the main reason this GPU became popular was doing this vision kind of task. And again, I mean, NVIDIA somehow ruled this space, not because they came up with this graphical processing unit. They were not first to come up with this graphical processing unit, but they came up with this language CUDA, which actually helped build this whole ecosystem. Alone hardware cannot help you solve this problem. So you need to have a complete ecosystem of hardware plus software where you can make it easy for programmers to write parallel codes. Okay, so the CUDA was actually the main purpose why these GPUs become so popular and why this NVIDIA actually still holds major market in the parallel computing world. So the current reality is that while you have Google tensor processing unit, AWS ASICs, and all of this, they only capture 30% of enterprise AI. And the primary reason of success of NVIDIA is not this GPU, but this CUDA software ecosystem that they have developed. They have unified platform for parallel computing with over so many 40,000 libraries and tools. And this tells us the story that going ahead even in the future, if you want to dominate this space and if you want to do computation in a verifiable way, then you need to have this verified or affordable software stack. If you don't build the software stack properly, then whatever hardware you build, no one is going to help use them. It's just like theorem provers. Before Lean, many other theorem provers came, right? But Lean is becoming more popular. Why? Because they are accommodating whatever you need as a prover. They're very approachable. They can actually accommodate whatever is your requirement, and then they're ready to adapt it to their language, let's say documentation or language implementation. So something similar happened with this NVIDIA and CUDA software ecosystem. And in future, when we talk about parallel computing, the reality is that the hardware infrastructure is going to be very heterogeneous. You will never know where your code is actually running. So your code may be running, some part of your code may be running on your CPU, but then some in GPU and some on cloud. So if you want to again build an ecosystem of software which can actually help you reason about your code properly, then you have to somehow abstract out this detail, because you cannot burden a programmer with all this detail of where there every piece of code is running. Then he will not be able to reason about the correctness of the code. Okay, so this is one thing that I want to highlight on this slide, that although the actual reality is that we have heterogeneous hardware, but we need to have a unified software or at least some abstraction where we can, on top of which we can think about the code that we have written and which will be finally relegated to different heterogeneous hardware. So the war is not over chips, it's over actually software. So the real in the real battleground, if you want to make most efficient and reliable computer solution for these high-end AI requirements, then you have to come up with some nice abstraction where you can actually abstract out the unnecessary detail of this heterogeneous hardware, and somehow those things can be unified using software. And this abstraction actually helps also as a contract, right? Because those who are building this hardware are not the same people who are writing code which will be finally running on this hardware. So you need a clear and concise contract between those who are developing this hardware, those who are, let's say, building compilers, and those who are writing actual programs on for these real machines. So it turns out that if we abstract out this detail in a mathematical form, and if we clearly specify what these hardwares are expected to do, then all of this gap becomes these are no more a gap. Okay, so there is a very clear contact between each layer of this developer. Okay, so whether it be between compiler designer or hardware manufacturer, or between a programmer and a programming language designer, everything becomes crystal clear. And without these contracts, you cannot work and write correct program which will execute as you want on the real architecture. Okay, so I will show that with 3 or 4 line of code, normally most of us will commit some mistake which is very unintuitive in nature. And if you do not rely on formal contracts or this kind of axioms, then reasoning about large programs is almost completely outside the scope of our imagination or our cognitive capabilities. So concurrency, the topic of today, actually provides you this abstraction. Okay, so why we talk about concurrency? Because concurrency abstract out this unnecessary detail of where your process is running. Okay, so the core principle is that when you have a hard problem, you split it into small pieces and run those pieces simultaneously. When I say simultaneously, it means it came back. So you can actually run it, you can relegate this task simultaneously to the hardware whichever is available. It may be on one chip or on 1,000 chips, and the developer should not have to know that this difference, right? Whether his code is running on one piece or one core, or multiple core, or he should not know the exact detail. So if you we talk about this concurrency or idea of concurrency because we want to elevate this thing to a higher level where one can write code without worrying about where it's going to execute. Okay, so this concurrency provides an abstraction for potential parallelism. And we completely try, so in any discussion about concurrent program, we would almost always want to ignore the notion of time, okay, in analysis. So we want to get rid of this time thing, okay. So you'll see that whatever model I discussed today, none of them actually assumes anything about when a particular event is happening on a particular thread or this thing. So this helps because if you, let's say, do analysis of your software without assuming this time constant or let's say CPU speed or this exact time analysis, then next time when you migrate your software to some other infrastructure, that works perfectly because you have proven every property without assuming anything about the time or exact time or relative time of when these events are happening with respect to each other. So the benefits are that you are building robust system which is safe under hardware or software modification, and that's why we always try to reason in this world of concurrency. So let me, talk about this idea of concurrency in one slide. So when we say we are talking about, so let's say, assume that we have already split our, hard task into some small subtasks. And now when we say that we want to run them concurrently, so what do we mean? So those concurrent execution does not mean that those things are actually running in parallel, okay? So this concurrency abstraction tells you that there may be potential parallelism, but it's not guaranteed, okay? So this is why we say a concurrency is an abstraction for potential parallelism, not the exact parallelism, okay? And in the most worst scenario, your different threads that you have divided your task into may be running into the, or maybe sharing the same CPU. They may be communicating with each other, or they may not. They may be, completely independent of each other. No, there are scenarios where when you write your program, you write only one, it as a sequential program, but then automatically compiler and other, intermediate translators can actually split them into multiple threads, and they may run it into, different cores. So you cannot even assume that. Okay, so when we talk about concurrency or this parallel threads or relegating, let's say, these subtasks to different compute resources where they are concurrent, we can't assume anything like this. Okay, so you should not put any of this assumption while reasoning about your program. Okay, so this is why I wanted to highlight it in the very beginning. So with concurrency, we get this abstraction, but the problem is, since the reality is not same, similar looking programs may behave completely different when you run them on different architecture, okay? So I'm saying, similar looking because they cannot be same, because, when you change your hardware architecture, let's say you go from one architecture like x86 to Power to ARM to RISC, the instruction set architecture changes, right? The exact instruction changes, but you can make, you can think some of these instructions to be mapping naturally to some other instruction in other architecture. So that's why we use similar looking program. But the similar looking program also does not actually behave exactly same on different architecture. And this happens not only at the architecture level, but also in the programming language level. So if you are, let's say, not bothered about the architecture and you are writing a program in C, C++, and you want to reason about all possible behavior of your program, then you have to be very careful. Where are you going to run? Are you writing this pseudocode in C, C++, or Java? Because all of them have specific memory model, and the behavior of the final program will be decided by the memory models of these languages. Okay, so these memory models are nothing but a way to clearly tell you what you can expect when you write this pseudocode in C, C++, or in Java, or in Python. Okay, so these models will be completely different. So you can again assume them as a contract. Like if I'm writing a C, let's say I'm designing a C programming language, I'm designer of the C programming language, I have to somehow give some guarantee to the user of the C programming language who writes programs. So these memory model that we will discuss, which is based on this idea of concurrency, they provide you this guarantee. So the guarantee that C language provides you for a pseudocode is not same as the guarantee that Java or other programming languages can provide you, okay? And it is the task of a compiler designer to somehow ensure that they map these guarantee properly to the hardware level, so that those guarantees can be provided to you as a end user. So in the most general setting, I mean, this is how the scenario, I mean, looks like. I mean, you're somewhere here, you're writing some code. Let's say you're trying to translate this kind of pseudocode into some language, which is, let's say, C language. So your C programming language manual will give you some guarantee about what will be the expected behavior of this program. But that is only possible if the compiler writer has properly translated those obligations into the obligation that will be required at this hardware level to, let's say, provide those kind of guarantee. Because again, these hardware, so C program can run on multiple different hardware, right? So you have to write your compiler properly so that it translates your pseudocode in C or your program in C to some program in these different hardware targeted for these different hardware that can finally give you that assurance, okay? So both, when we talk about this weak memory model or these contracts are not present only at the language level. So these contracts are present at each level, okay? So you can write down a assembly language program for x86 and directly reason about what will be the behavior if you know the exact memory model for x86 or whatever architecture you are targeting. But then you cannot use the same semantics or same memory model to think about a program if you have written that program in C++, okay? That memory model will be completely different. So although these memory models are available at each layer, they are different and they kind of provide you guidance how to translate program from one layer to another layer. So normally whenever we are talking about some contract or some simplified, let's say, framework where we can think about program, we normally want this framework to be very simple, right? And you don't want it to be very verbose or very exhaustive in nature in the sense, I mean, you don't want it to be big. So you want something minimal, and you also want this completeness guarantee that with this minimal set of axioms and reasoning rule, you can actually reason about any program that you can write in this programming language. Okay, so these are two properties that we almost always discuss, and we try to discover what is the minimal, let's say, subset that can help you do this translation from one layer to another layer. Okay, so that's why identifying the core programming construct is the very primary thing that we do when we come to do research in this area. You have to identify what are the core, let's say, element of your programming language, or even when you write this program for targeted for the hardware, what are the core construct that is available. Okay, and then we try to come up with reasoning rules. So more or less, I mean, we follow a convention where we only, whenever you want to, so parallel programs actually become interesting when they communicate with each other. Okay, so when different threads communicate with each other. When different threads do not communicate with each other via shared variable, then more or less reasoning about this program is not that non-trivial. You can actually reason about this isolated program and then prove property. But whenever they start communicating with each other, you will see this interference from the other thread causes a lot of change in behavior of this program. Now you cannot reason about these threads in an isolated manner. Okay, you have to take care of all the synchronization that might have happened till this point to accurately reason about what will happen in the future. Okay, so in this talk, whenever I show you some threads written in this way, this particular way, where you can see this is thread 1 and then thread 2. Whenever I use variables like X, Y, or Z, the last letters in the English alphabet, you assume that those are going to be shared variable. This is not a standard convention, but for our ease of let's say discussion, we assume always whenever you see some program on the slide, you assume that these X, Y, Z are going to be the shared variable, which will finally help this thread communicate with each other. And then A, B, C, these initial letters are nothing but local variable. Okay, so these A, B is not accessible by thread 2. Okay, so let's say if A is not accessible by thread 2, similarly B is not accessible by thread 1. But in this case, you can see X and Y, these two variables can be accessed by both of these threads. Okay, so this is the convention that I assume, I mean, this presentation. So the easiest mental model that we can imagine of, and which also gives rise to one memory model, which is the simplest memory model that we can think of, is called sequential consistency model, where whenever we are given a program written like this, where you can see there are two simple threads, right, which are doing some instructions on each thread. And if I want to reason about what can be all possible behavior, let's say, of this small program, what I have to do is only consider all possible interleaving of instructions from different thread, okay? So when I say interleaving, those interleaving has to somehow preserve the program order or the instruction order which appear inside the same thread. Any interleaving is allowed, but it should never disagree between order of two instructions appearing on the same thread, okay? So for example, I mean, in a given interleaving, you cannot assume that this particular instructions come before this instruction, okay? So this is what we mean by interleaving. So if I ask you for this small program, assuming this interleaving semantics, where any behavior can be outcome of only possible interleaving, so is it possible at this point, let's say for thread 1, when thread 1 is reading the value of this shared variable y into A, to read a value 0, and simultaneously the second thread B, which is reading the value of shared variable x, to read a value 0. So can you figure out any possible interleaving that can land you in this kind of situation where when this first thread is reading or executing this instruction, you get a 0, but the second thread, when it is reading or executing this instruction, you get finally a value 0 here. If you right, you can see that I mean, you can do all these enumeration and check. So that's one way to do. You can come up with some smart argument and tell me why this is not possible. Okay, so you will see that if you want to read, let's say, a 0 here, somehow this particular instruction, this instruction has to come in the interleaving before this instruction, right? Because this already updated the value to x. So if this instruction is coming in the interleaving or this total order after this instruction, then it cannot read a value 0. It has to read a value 1. Similarly, you can have a reason for this particular instruction also, right? We cannot, we have to somehow insert this instruction before this instruction, okay? So you can see that there is some dependency which is enforced if you want to see this behavior, okay? And under those dependencies, you will see you cannot have a total order which can order all the instructions available on these two different threads, okay? That's why we can rule out this, this you can consider as a proof by contradiction. You assume that there exists something like this, but then you show that there is a loop, and no loop can be linearized in the sense that you cannot form a total order if you have this kind of cycles in your graph, okay? So this is what we observe in this sequential consistency. This example is very well-known litmus test. This is called a store buffer example. It turns out that if you reason about program using your mental model, you will always say that this is not possible. But if I tell you the reality, I mean, all modern processor architecture allow this behavior, okay? So when you run it on power or x86, this behavior is actually accepted behavior. And the reason for that is that these architecture, for doing various sort of optimization, hardware as well as compiler optimization, they do not guarantee you this kind of interleaving semantics which we discussed just now, okay? So this will be something which will be allowed. So when you are reasoning about your program, you have to somehow keep in mind that if this is the bad state, let's say, of your program which you never want to reach, this will be reached, okay? And if your analysis says that this is not reachable, then that analysis is going to be wrong, okay? So that's why we say the sequential consistency guarantee is a very strong guarantee, and almost none of the programming language or hardware actually provides you this guarantee. Sorry. In fact, I mean, in most of these, real architecture, actually this is allowed behavior, okay? And reason for that, I mean, I will tell you just now. But no, here, I mean, in this slide, I wanted to just highlight, yeah, so this is important to understand why this is not allowed in any architecture, okay? So now, so the reason that we say that this is not possible is using this interleaving kind of reasoning, right? We say that, this has to, sorry, where is my pointer? Yeah, so this has to come before x is equal to 1, right? So that's why I keep it here. But if you see, if you try to enforce all these requirement, you will see again B will appear here, okay? So you get a cycle kind of thing, and you can never actually have this kind of behavior. So when we talk about interleaving semantic at any point of time, so when you start executing this program and you are looking at a partial, let's say, interleaving and or any initial segment of this total order. So what will happen after, let's say, executing these two instructions? At this point, if I ask you, what is the value stored in X and Y? So the value stored in X and Y is 0 and 0, right? So this is what both the thread need to know. But when you execute this instruction will not change the state of your shared memory, right? Because this is just reading. So reading does not change the state of your shared memory. But when we go to this instruction, we change the state of X, right? And at this point, if I have to again ask you what other threads can tell about X, then the value of X will be 1 and the value of Y is 0. So, but I mean, every thread will actually agree on this function. Okay, so you need not always remember what happened your exact past, okay, total past. You can actually forget about the past by just keeping track of what happened last, okay, what was the last write on every variable. And that can be compactly represented using a function, right? You can use a function to tell what is the last write, and you update that function every time your last write changes. So you can actually capture the state of shared variable or shared memory using one function. So that's why we say that sequential consistency assume that every thread have same global view of shared memory, okay? And that shared view can be captured using a simple function like this. But in actual hardware, I mean, not every processor has a unique global view of shared memory. Because if you have taken some computer organization course, you will know that in your multi-core environment, your processor has local cache, right? And they don't always, whenever they update, let's say, some variable, they immediately put that update into the local cache, but they do not push it to the main memory, okay? So they will do it in a lazy fashion. So let's say if code 1 has already updated some variable, it is not immediately visible to code 2. While code 2 might be executing some other instruction, I mean, still that last write has not appeared in the main memory, okay? So this is one small example to tell you one of the reason why this kind of example that we saw in the previous can be possible, right? Because you remember, I mean, the first thread was writing something to X, second thread was writing something to Y. Those were different variables, so they will have different store buffer, and they will push things from store buffer to the main memory only after some time, and those may not be immediately accessible. So in one word, what we can say is now those simple function is not helpful for you. You cannot have a unique global view of memory on which every thread will agree, okay? And that's the reason for this kind of weaker behavior. Now the question is, if we don't have those that kind of simple view or unique view of memory, then what can be the appropriate view of memory that can still help me predict the correct behavior accurately? And that view need not, and you have to come up with always a compact notation, okay? So this is also one requirement. We cannot talk about the whole program. We want to make our life simple. That's why we said in the initial case, I can only remember one function and then everything I can reason about the program. Here also we want something similar, but we somehow realize that one function is no more useful. So what we say is we have to come up with some other object which is like function but not exactly function, but that can help me guess all possible behavior of my program. So in case of most of the weaker or let's say weaker guarantee or most of the modern architecture, we identified that there is something called execution graph, which are nothing but partial order, that you can, if you can remember, then you can actually predict all possible program behavior. So I'm not going into the detail of how to properly define that partial order, but maybe with some example I will tell you how you can actually make out partial order for a given program, okay? Okay, so this is what we discussed, that in reality we don't have a unique global view, and our goal is to come up with an axiomatic understanding of this behavior. So we want something simple, but that simple thing cannot be as simple as function. So the next simple thing I can imagine is partial order, these kind of things, because you have to somehow retain some order. It may not be total order, but what about partial order? Can we remember this partial order and then reason about our program? So this is what we are going to see next. So we call it for execution graphs. So normally these partial orders are called execution graph when we want to talk about these concurrent programs. And it is very easy to draw partial order for this kind of simple program. So when drawing partial order for this kind of simple program, what we do is we don't want to think about anything that is happening locally, let's say only. So remember, all of these events are actually somehow engaging global variable, right? The first one also, somehow changes the. Sorry, where is my? Yeah. So you see, shared variable. So that's why in this case you don't want to get rid of any instruction. But your program may not always have this thing, right? Your program very seldom has this kind of shared variable communication, and most of the time you will have so many instructions which is only, let's say, changing your local variable. So when we want to think about the shared variable space, what we say is you simplify your program, you just completely throw out all the instructions which are only working on local variable, and you keep every other instruction which is working on a shared variable. And most okay, so the simplest way to get to this property of, let's say, or behavior of your parallel program by just keeping track of this thing, okay? So again, I mean, I'm not going to the detail, but these execution graphs has something like this. Again, when you have graph, you have events, you have nodes, and you also have some edges, right? So whenever some instructions comes in program order before some other instruction, I mean, in the thread order, then you put an edge between them, just hinting which one came before, which other event. Then the next thing we do is whenever you read from some value, because see, in this case, when I was saying that I want to read I want to observe a 0 here. So to observe a 0 here, this read must read from this right, okay? So if this is reading value from this right, then it cannot observe a value 0 here. So if your final outcome, or let's say the bad state that you are analyzing, is somehow enforcing some reads between, enforcing this read to read from this right, then you put an edge like this, okay? So this is what we call read from. So we are specifying in a way that this particular read is reading from which right, okay? So this information is essential for keeping track of this behavior. So once we specify this read from and program order, then immediately we have a causality relation, which actually we call happens before relation, which is nothing but transitive clausure of union of this PO union RF, okay? So what it says is that, for it to be meaningful, first thing that we have to ensure that these RF edges that you put, because you have choice of reading from any read while deciding whether this is a possible execution or not. But only those choices which do not, let's say, conflict with your program order will be considered, okay? So you cannot say that I want to read from a right which will happen later in the thread, okay? So those kind of things you don't want, okay? So that's why we say that this PO union RF should be acyclic, okay? So if you have those kind of things, then you start making cyclic, and then there is no notion of happens before, because again, with the cycle, you cannot say which event happens before another event. So this is an accepted axiom, or in another word, you can say a restriction imposed by any hardware on any hardware designer or any programming language developer, that they should never allow this kind of behavior, okay? So this is the minimal, very minimal that we expect for anything, for any notion of happens before, okay? So this is the very first thing. But then there are some more additional constraint that we put to finally make these things not arbitrary and give us some predictable behavior. So again, I mean, I'm skipping most of this just in the, yeah, please. Yes, right now only two colors, because I have talked about only two relations. So these are RF and PO, but most of the modern architecture actually also talk about another thing which we call modification order. So I will skip it for this talk. I mean, just to give you a flavor that these kind of simple graphs with these kind of relations, which are nothing but edges on this, in this graph, and you can specify what can be possible behavior by specifying these kind of constants. Like this is also one constant, right? PO union RF is acyclic. You are free to choose RF, but you have to only choose RF such a way so that you don't make a cycle. So this is also one constant. Similarly, there are more constant. And so in programming world, this array, release acquire fragment of C, C++ is very popular. Okay, so I have put this array in center because whosoever writes C, C++ concurrent program, they mostly rely on this release acquire fragment. Whenever they write program, by default, they are happy to write every write or store operation as a release operation and a read operation as a acquire operation. Okay, so again, we don't want to get into this, but this is the most useful fragment of C, C++. Those who write concurrent library, they mostly rely on this because somehow this provides some intuition to them, although this is not fully intuitive as sequential consistency. This gives them somehow some comfort that they finally use this fragment more. Okay, so since they are using this fragment more, we are also interested in figuring out, can we talk about this fragment in a more mathematical sense? Okay, that's why array stands in the center. But then researcher, I mean, simply because you use array will not restrict to array. I mean, they talk about some stronger version also, some weaker version also, and then they also propose in the next language revision whether the C, C++ language designers should stick to array or they should go to some other model. Okay, that provides maybe some stronger guarantee. So this is the area of research. I mean, where a programming language designer actually try to come up with modification and suggest it to the next programming iteration, language iteration. So in this case, so I want to just talk about one more behavior and then I will not go into the axiom. So the next behavior, which is again almost accepted by every causal consistency model, which will be assured to you by every hardware and every programming language, is this kind of behavior. That if using RF and PO edges, if you can draw something like this, where let's say this is a write happening on X, okay, and this is another write happening on X, and you could see a HB edge between this these two writes. HB edge means there is a happen before already established in your partial execution graph, okay? And you also have a HB to some other read. Now this read is trying to read from some write. So it can only read from those write which is available in your partial execution graph, okay? But it has multiple choices to read, where to read from. Now which of these choices are valid is what represented using this diagram. So this diagram says that if this read is already aware of a write which happened after this write, then this read should not read from this previous write. Right? Absolutely. This is very natural, right? Even in sequential consistency, we observe this, right? We always want to read from the last write that happened. But since here there is no notion of total order, we have to talk about this causality in terms of partial order instead of one total order, okay? But this partial order also provides you some causality, right? You can actually figure out that some of the events actually happened before this event, and I know already about these events. So if I know about two writes, and if those, among those two writes there is this happens before relation, then I should always try to read from the last write, okay? So this is what we assume in every memory model, okay? And this is very natural to expect also. So even though you don't have total order, you have some weaker notion of order, but using that weaker notion of order, if you can order two writes, then you should always read from the last write, okay? Now this thing has been talked about in literature, and many variation has come up, but I will not go through it. So let's skip all of this in the interest of time. So different like RA has some additional constraint which requires this modification order that I was about to talk, but let's skip it. So assume that MO is additional requirement which this RA memory model puts for predicting any program behavior, and then this SRA is even stronger, so it puts some more constraint to this RA. So this is not very important for our talk, so let's skip these details. So then once you have, let's say, this memory model, so when we say memory model, we have a bunch of these restrictions or axioms on these execution graphs, okay? So when I say sorry, WRA, I immediately know what are the restrictions or requirement for something being valid in this WRA world. Similarly, when I say RA, I know what is the requirement for this RA, okay? So your language will be following one of these memory models, so you can immediately then fix your memory model and know exactly which constant you need to satisfy. Now while satisfying those constants, if you can build an execution graph that shows that particular behavior that you want to avoid, then you are in a bad state, right? Then you have hit a bad state. Okay, so this is how we can actually determine a bad state, provided you have enough time and enough enthusiasm to sit down and learn all these requirements and then go through these graphs analysis by hand. Okay, so this is what. But at least, I mean, since you have these axioms, now you can reliably think about all possible behavior, and you have a formal proof why this should be correct. Okay, so that's why we say that this provides a formal guarantee, or this is like a formal contract. Without this, you cannot actually reason about these complex programs. So this is the general problem of state reachability that we want to put in this way. So given a memory model, or in another word, given the platform that you are working with, and let's say given this annotated behavior of program, which somehow tells you what is the bad state in your program, which you don't want to read, can I automatically now figure out using these axioms and let's say the given program and this bad state description, whether this bad state will be reachable or not? Okay, because since these analyses are very tedious and not so easy, unintuitive, so we want to somehow relegate it to computer. Okay, so for that you have to come up with some algorithm which can actually solve this problem automatically. But before you think about efficient algorithm or these kind of things, you have to know whether this problem is even solvable or not. Okay, whether this is decidable or not. It turns out that for okay, so I will just skip this thing. It turns out that for this array fragment, which is the most popular among programmers, this problem is undecidable. Okay, and so there was a paper in 2019 in PLDI which proved that even if you assume that your data domain is bounded, that whatever data domain you are working with, let's say natural number, you have an upper bound on those natural number, and so in the presence of loops, actually even with working with this bounded data domain, it turns out that figuring out whether a state is reachable or not becomes undecidable. So they map this to PCP, post correspondence problem, and then they show that this is not possible to decide. Okay, so now you know that there is no algorithm you can write to automatically check whether a state is reachable or not, assuming this array fragment. Okay, so this was a bad result, which we came to know in 2019. But soon after this, in 2020, my postdoc advisor Ori came up with two surprising results. That although this array was undecidable, so he came up with constructive proof of decidability for this SRA and WRA. So WRA is weaker condition than RA, most useful fragment for C++, and SRA put some stronger condition than that. Okay, so you have decidability on the both side, but then in the middle you have undecidability. Okay, so if you want to exactly tell or figure out whether this program will hit this bug, if I run it under C++ memory model, you don't have a choice. But then you can actually solve this problem for a weaker model and for a higher model. Okay, so what are the implications? So maybe the stronger model is not so useful, but the weaker model actually, I'm skipping the proof procedure how they proved it. So let's talk about the implication. Since you know that now you can solve this problem for WRA, and WRA puts less restriction. Putting less restriction means allowing more behavior, right? I mean, when you put less restriction, you are allowing more behavior. So if you can actually solve this for WRA, then it turns out it helps you for RA in some cases. For example, let's say if you know that the bad state is not reached in this WRA, which is weaker, which puts weaker restriction, then you know for sure that this is not reachable in RA as well, right? So remember, I mean, if I can show some execution graph while not violating these restrictions, then that bad state is reached, right? See, since my restrictions were strictly less in the sense that it was strictly less, and if I show that under these restriction also, less restriction also, I could not actually hit those bad state, then under heavy restrictions, you can never hit those bad state. Okay, so this kind of result actually helps you that if you figure out that this is not reachable under SRA, then you can be sure that this kind of bad state will not be reachable under RA. Okay, so for example, I mean, I am again skipping this example in the interest of time. This is one case where you know that this is not reachable under WRA, so you can immediately infer that this bad behavior will not occur when you run it on C++ RA fragment. Okay, but whenever, I mean, let's say, so when you get an answer, yes, that this bad state is now reachable in this WRA. So in this kind of scenario, you cannot be sure, right? Now you have both possibility. This may be, this bug may appear when you run the program under RA, or it may not appear under array. But you don't have this guarantee now, right? Because WRA allows it does not mean that array will also allow it. And we investigated multiple examples to see how often, I mean, this happens when, your WRA says that you will never, hit this, you will hit this bug, but your SRA says that RA says that you will not hit this bug. And we found that this gap was huge, actually. So there was many examples we could come up, which actually, just maybe 2 minutes and I will wind up, So, so what we try to do is we try to come up with these, counter example which actually made this WRA so weak and then categorize them. So the first task was, can we, again, I mean, since we are talking about formal things and contracts, we cannot say that this pattern, we want to get it. We have to somehow axiomatize this pattern or observe some behavior in this pattern and then mathematically try to classify those patterns. And once you classify those patterns, you give a new memory model and you say that, okay, this is the memory model which will be better than WRA whenever I am concerned about reasoning program in RA. Okay, so this was our work. I mean, one of the work where we try to identify. So we call it oscillation. This kind of oscillatory behavior which makes this gap look larger. So we try to identify this oscillatory behavior. We come up with a model, exact model which axiomatically characterize this behavior. And then we also prove that under this LRA now the state reachability problem is decidable. So now you see, I mean, you have a better model than WRA which is closer to RA and which is decidable. So once that is decidable, now we have a better model to check against, okay, whenever you want to check this. But still, I mean, that is strictly less than RA. This is also what we show in our paper, that there are some examples where, so this is exactly what we have finally. So this LRA is sitting somewhere between these two. Okay, but there are some examples which will tell you that it's allowed by LRA, but then it's not allowed by RA. Okay, so yeah, so I mean this is, and to do this we just added one extra axiom. So this is the extra axiom that we added, which does not require all those complicated MO kind of thing, which is very hard to figure out algorithmically. Okay, so one of the requirement that we had in mind when we were thinking about how to exclude this thing, to come up with some constant which does not require existential quantifier. So this HBR is not does not require finding out one such HB does not require you searching over this existential quantifier. But then MO, if you talk about RA, you will need some sort of existential quantifier, and searching in that domain is very hard. So this one extra axiom actually makes it happen, and under this constant we prove that this is decidable. So this is the theorem that we finally prove. So 1 minute, can I have 1 extra minute? Just then I will finish it. So another interesting problem in the same domain was this library abstraction. See, this is also motivated from real life example. Whenever you are writing concurrent program, you mostly rely on libraries written by others, right? You don't write all the library on your own. Now, if those libraries are not written by you, then what sort of guarantee you expect from, let's say, or what are the things that you expect in the specification so that you can ensure that whatever you have written as using those library work as intended. Okay, so this was again a theoretical work which I tried to identify what are those minimum requirements that you would put as an obligation to those library developer, so that later on whenever you build on top of those library, you can assure that your code behaves as it is. Okay, so this is what we call library abstraction theorem, and you can also again think of this theorem as a contract, right? That if this contract is made, then you can rely on this library and then you can build something on top of that. Okay, so yeah, so this is what the contract looks like finally. So this contract cannot have only, so see, final program is not only something written by those library designers, right? You have also written some component of those component of this final program. So what are the obligation that a library developer has to fulfill, and what are the obligation that you have to prove, so that finally the whole program actually works as intended, is what is given this library abstraction theorem. And we clearly identify those in separate terms. So this is another work which is very close to formal verification and library abstraction. Again, just in a summary, I am just concluding, this is the last slide. So weak memory models are like formal contracts, and studying these kind of models helps. Why? Because it can attract more and more formal method experts and bring them into the programming language and software engineering research, right? Because if you want to talk or you want to prove reliability or trustworthiness of your software, you need somehow this link to formal methods, okay? And formal method cannot be done on anything. You have to have clear mathematical structures to reason about property of your program, okay? So this is a very exciting, field, and getting into this field is easy for at least the formal method people, because my background is in formal method. I have mostly been, proving things in theorem prover, but it was not at all difficult for me to get into this area. Why? Because this weak memory model has already axiomatized the behavior of program using these graphs and this kind of constraints. So decidability result, proving them is important, but it's not enough, because with the decidability result you don't have guarantee of getting efficient algorithm. So it's also good to research towards figuring out these effective procedures. People have talked about this. They have used this bounded model checking kind of technique to come up with the effective procedure, but still they fail miserably when run on 8 to 10 line of code. So what our group is right now trying to do is use these axiomatic semantics as a guideline to come up with some effective procedures that does not do enumeration. Instead, it does some search in a guided way, so that you can, if there is a bug, you can hit the bug very quickly, okay? So this is the work that we are doing, and these are my collaborators, Hardik, Sri, Nitish, Ashish. So most of them are actually present here. So I will not talk about this, but this is roughly the area which we are currently working in. Yeah, thank you so much for your patience. Thank you. Yeah, if you have any question, I can take one question, maybe one or two questions, depending upon how much time we have.
I just had a general question. So in these verifiability constraints, if you are, let's say, writing a program for a machine, a robot, for example, and you need to finish executing a piece of code in a certain time-bound manner. So let's say 1 second. So then can the verification code, verification of those such kind of programs, is it possible?
So those things are also possible. I'm not saying, it's not that those things are not possible. In the work that we do, what I say is we don't assume that kind of time analysis. But it's not to say that, that's not possible. It's possible, perfectly possible. And people do that kind of analysis also. Yeah, they do some sort of temporal analysis. There are logic, well-established logic to do this kind of analysis.
But then wouldn't that also depend on the operating system which is running?
So that will depend, but then when you come to operating system, you don't know which event will happen first, right? So then any analysis that you do like that is not useful.
Yeah, so basically there was a requirement and we were thinking of implementing it.
No,
I was clueless how to go about doing such kind of verification.
Right, so if you can prove these things without assuming anything from operating system side, then only you can be sure. Otherwise, you can never be sure.
Hi, I quite enjoyed the talk. I just have one question. So when you said this problem of reachability, you said it's decidable for certain memory models like WRA. So this is specifically for assertion checking, right? This result.
So, so not only assertion checking, even data races can be actually modeled into this state reachability. Okay, so this state reachability turns out to be a more general kind of property testing than what you said assertion testing. Okay, yeah. So it can actually incorporate data races and other kind of things also.
Yeah, so anything that can be reduced to state reachability.
Exactly,
right?
exactly.
Are there any results for, say, something stronger, like any kind of temporal logic?
So temporal logic, so there are actually results. I mean, you can actually talk about times and the properties in time that you want to observe. But as I started with, I mean, in any real software analysis, when you want to do some, let's say, this bad state analysis, you don't have those guarantee of times. Okay, so that's why we said that we want to get rid of that. And when you come to concurrency, we do not talk about actually time, the exact time when it happens or what happens before, whatever. The only notion of ordering is what I told HB, and HB is not a complete ordering of events. Okay, so it may happen that now you can say something about what happened before what, but again, I mean, it's not necessary that that happens in the actual hardware. So don't take it like, I mean, this is the actual reality. But assuming this also, whenever you reason about the possible behavior, your result is correct.
Right. So you're just reasoning over all the potential paths that could be taken.
Right.
Thank you.
So this analysis is complete. It will not give you incorrect result. But when I say something is HB happens before some other thing, you cannot assume that when you are running those things, actually those things happen.
can I assume these are the kind of properties that we need to adhere so that when we, let's say, nowadays we are seeing this kind of trend where there are architectures being built and there are hardwares being specialized for those architectures.
Right.
So can I assume that, okay, these are some of the specifications that I should follow whenever I'm creating these hardwares or creating the compilers for these behaviors? Like, can I say, okay, these are the specs that I should follow so that I'm building some kind of a verifiable or verified compiler in some sort?
So the role will change based on, the answer will change based on your role. If you are like an application programmer, this comes as a guarantee to you. If you are a compiler writer, this comes as an obligation to you. Okay, so if you are a hardware designer, this comes as an obligation to you. So you have to, first think where are you lying in this whole layer. If you are going to write, let's say, assembly language program, then you are at a user end. So you will be provided this guarantee.
Thank you.
Yeah.
Excuse me, sir. You mentioned about LRA is stricter than WRA. So I was wondering how it compares to SRA.
So RA is strictly weaker than SRA.
Okay.
Yeah. So So there is this is strict implication kind of thing you can actually prove.
Okay. Thank you.
Okay. Yeah. Thank you very much. Thank you.
Thank you, Professor. So now we will have the next LeanLang talk by Professor Gadgil. So this will be a little shorter than expected. It will be till 1 o'clock, and then after that we will have lunch.
Can you move the laptop? Sorry, my hand is full.
I'll remove this also. Yeah.
Okay, so first of all, let me power cord. Plug it in. So what happened to that? Let me. Okay, so as a pleasant surprise, this thing started working straight away, so we can get going. So let me continue. I should thank Prathamesh. He had a slightly difficult task. I never told him where I was going to end, but because I didn't know, but he took off at a perfect point. So even though first one I skipped, I don't know, this thing is very fiddly. Yeah. So so what I was going to do this time he did, so I can save time on that. So let me first answer questions, then get back to where I was last time. Yeah. So people were asking what happened to the proof with grind. Okay. So what happened with the proof with grind? Now in Lean you can always see a proof. So let me go back here. We proved something called smallest mem using fun, induction, and grind. And if you print it, you see an expanded form of the proof. It is not fully expanded yet. You'll see some theorem called smallest induction unfolding. You'll see something called smallest mem proof 1.3, and you'll see something called smallest mem proof 1.2. But you can print those two. There should be some way to expand it fully. I don't know yet. One can always do metaprogramming to do it. And you see smallest mem proof 3 is something which is quite gothic here. It goes on for many lines. The induction involves this, and I have not expanded that. There's a match, congr equals, etc. But you can unfold all the way down. So technically by is simply syntax. A tactic sequence is simply syntax that produces a term which is a proof. So the right hand side of definitions are of course terms. These, when you get into by mode, it does fancy things, but it finally gives you a term. And that is, so there was a question about grind. The other philosophical point I want to make, and why is it that LeanFro is so keen on grind? And why is it I'm emphasizing this kind of thing here? So if you're looking at the theme of this hackathon, or more generally lean in software verification more than mathematics. In mathematics, people are happy using tactic proofs. They get a certain insight and so on using this. But with software verification, in fact, Ashish is going to talk about similar thing later. You want it to be an automated pipeline. You want programmatically to call something and it just does it. Okay, you can afford to call 3-4 different things. You can afford to be a little smart about configuration, but roughly speaking, you can't be interactive. You have to have a lot more automation. And so the lean creators, Leo de Mora and so on, are working so hard on grind because of exactly this, that you want the success rate of full automation to go up a lot. It becomes important when you go to these. Yeah. Good question. No, I mean grind will not produce counterexample. There is another tactic called plausible, which exactly is supposed to produce counterexamples. It's in the roadmap to work on plausible, but unfortunately plausible has not got as much attention as it should in lean. I myself keep hoping to work on plausible also, and there's discussion on the Zulip, and Eric Weiser has sketched out the better way to implement, etc. Yeah, but there's a complement of grind called plausible, which is supposed to do that. And while grind has got become really good, plausible is still quite inadequate in many ways. Yeah. 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 So grind is not all powerful. Very often you have to go and simp. Even grind is not even strictly stronger than simp. It's not even stronger. Sometimes you have to rewrite, and we'll see. Okay, we'll see where, when I talk about quicksort, we'll see a case where exactly what grind can do and what it can't do. And there is a good reason why it can and cannot do that. Yeah. So grind is not universal, and it's not even a full search tactic. It's not the only automation. There's ASOP, which Prathamesh used. There's lean hammer, as it is called, which does something a little different. And there's another thing called canonical. There is a bunch of other things. Yeah. Okay. So far so good. So I'm going to continue now with. So I'm going to switch mostly to non-live coding. That's the way to save time. Yeah. So I'll go until 1 and we'll continue. And afternoon I'll be talking more about syntax and so on. So as a clean break. So far what concepts we have seen is, as I said, we see definitions and types going nicely together. And then we saw the, I should have closed the other file. Let me just go to list tops. And I ended here, which is that I was looking at these list operations. And in the list operations, we saw implicit and explicit parameters. And right at the end, we saw this mysterious thing called add alpha. Okay, those who know functional programming would have seen this before. This is called type classes. Okay, but though many of you would not have seen this. And this add alpha is what allowed addition. Now there are sort of 2-3 different ways of allowing addition. In Prathamesh's thing, you saw ad hoc way of using infix. But type class inference is the much more powerful way of introducing notation of a general nature. See, addition can mean different things in different contexts, and you may want to create new contexts. So you want to do it in a way that combines things, and this is an important form of automation. And so this is the part I will do in a little detail now before moving on to a few other examples. So let's go to what I call adders. Adder.lean. Okay, so let's see how to add in the presence of the type class. First of all, we can evaluate 3 plus 4. Yes, of course, no surprise there, because we know how to add them. But we cannot evaluate, we can append hello and world, because string has an operation plus plus which calls append. However, if I eval, I don't want to do that. Suppose I want to eval hello plus world. I can't. And it gives some very funny error here. Okay. So I will not try to do it this way, but instead first I'll rewrite this term. Let me rewrite what the addition is. So I'm going to open add and I'll tell you what that means, and I'll evaluate add 1, 3. So the plus just gets rewritten as this function called add. Okay, but this function's full name is capital add dot add. When I open add, it just means change of names. You can use shorter names, that's all. And this is not opening as in importing or anything deeper. Okay, so far so good. Now we have been evaluating things. Let's see what happens. If I say check add, check tells you the type of add. Okay, so what is addition? It is given alpha and alpha, it gives you alpha, given 2 numbers, but you need something called a type class here. Okay, and the type class is what lets you use the add functions. A little later we'll see how to construct type classes, but first we'll learn how to construct instances of type classes. Okay, so now suppose I want to define addition of strings. I want to define addition of strings in such a way that when I want to add strings, I don't just concatenate them, I put a plus space in between. Okay, I want to add strings in a funny way. So let's make something which defines addition for strings. So if I try to add 2 strings, add, if I added hello and world, then it gives me an error which using this magic of guard messages I will save as a non-error. So it says it could not find a synthesize type class instance. That means it could not find a way of adding strings. So let's give it one. So I'm going to just define an instance. Okay, add is, I'm not going to use string.depend. I'm going to use add of s and t is going to be s plus plus space plus plus t. And now if I evaluate hello, add hello world, I get hello with space in between. And indeed, I can evaluate hello plus world. It also gives hello and world with space in between. So what did I do here? I created an instance of addition. And so when it tried to use add, you see the type of add told you it needs an instance of addition here. Okay. Now this is different from an implicit parameter. In an implicit parameter, as I emphasized, it tries to match types and infer what it should be. Here it does something more ambitious, it goes hunting for it. Okay. So I did something dull here, I just had strings. Let's show the power of type class inference by taking something a little more complicated. Okay. Now you would think logically that if I know how to add, let's try to add the following 1, 2 plus 3, 4. It did not manage to add this, but that's a completely logical way, right? If you have 2 pairs, why don't we add the first component and why don't we add the second component? Okay. So the thing about Lean is that it's extensible. Let's teach it to do that. So now I'm going to make a completely general rule. I'll say instance alpha, beta are types. And suppose I know how to add alpha, elements of alpha, and I know how to add elements of beta, then I can add elements of the pair alpha backslash times beta. Sorry, that was a capital B, where add is going to be function which will take A1, B1 and A2 to A1 plus B1 comma A1 plus A2 B1 plus B2. Okay, there's a lot to unpack in this, but it illustrates a lot of things here. If you understand this example, you understood pretty much all that's going on in type class synthesis. So what does this say? It says I'm going to create an instance, which means I'm going to tell you how to add pairs alpha and beta. Okay. but I need to know how to, you have to tell me how to add alpha, so that's taken as a type class parameter, and you need to know, tell me how to add beta, okay, and then I'll tell you how to add a pair. So then the addition is a function which takes a pair A1, fun means function, A1 B1 and A2 B2 and gives you A1 plus B1. And why is this plus defined? Because we know addition of alpha. And similarly we know addition of beta, so beta is defined. This is the key idea here, and now we can actually evaluate this sum. It became 4,6. Okay, and I can even evaluate, let's be a little more ambitious. I take hello and here I put world, and I got 4, 6 hello world. What this did is, now you see, step back, what did it do? Well, I have 3 terms, but 3 terms, triple is just a tuple of tuples. That is, it's a product of products in Lean. Okay. Now we know that we can add products if we can add each component. So it decomposed this into saying we want to add a pair and we want to add strings. I told it how to add strings. Okay, and then I want to add a pair of integers. It decomposes into adding integers, but adding integers is known to Lean. Okay, so what you do is you backward chain, saying that I'm looking for an instance of how to add a product of in nat, a nat, and a string. And it says if I know how to add a product of a nat and add nat cross nat and add string, I can add this pair. And then I know how to add string. I learnt it just now. I don't know how to add nat, but if I could add nat and nat, then I could add the product. That was the rule. It goes back and does it. Okay. So this is the power of this type class inference. And in mathematics, you can construct group structures, all sorts of structures like this. So it's a very powerful way of doing things. It's how inheritance works. It's how properties are captured. Okay, so this was our little digression. Now let me get back. Yeah. Plus is syntax. The type print, you mean show the type of add? Yeah, it's already here. Add has the following type. It takes an implicit parameter called alpha. It takes a type class parameter called self. And then it's a function given 2 alphas, it gives you another alpha. No, add is always this. Exactly. Type class synthesis is not modifying the definition of plus, it is filling in this parameter. So as I was saying, I did explicit implicit parameters to say there are 3 kinds of parameters in Lean. There are explicit ones, you give them. There are implicit ones which it figures out, but figures out from matching types. It deduces them by consistency. And there's type class parameters which it does a best effort to find using automation by backward following all the rules. Yeah, so it's not, so we have not changed that at all. What we have done is we have given it more ways of constructing elements of this guy. Okay, and I'll actually show you, we'll construct a type class. Yeah. It's an inductive type. Your mic is not on. Huh?
Then,
so an instance is simply a definition with an annotation which says it's an instance. Okay, we'll discuss this. But anyway, I'm going to give another example. I'll go non-live soon. I'll give an example where we'll actually construct an type class. Okay, our own. Yeah.
Sir, is there a type in the Lean language which is a super type of all types?
That's an entirely different question, but I will answer it. So no, you can't for consistency reasons. A type, if you look at, okay, let's do it. So if I look at check, check means tell the type. 1 is a natural number. Okay. Check. What about nat? Nat is a type. Okay. And what about type? Type is a type 1. And if I check type 1, it's a type 2. And so on, as you can guess. You have a hierarchy of types. Okay? But we also have a special kind of thing which is kind of like type 0, which is if I write type 0 equals 1, 0 equals 1 is a statement, it's what's called a prop. A prop is kind of a low level type. So proposition, there's a whole hierarchy of types. Technically there are sorts, there's prop, there's type, there's type 1, type 2, type 3 and so on. For Russell's paradox kind of reasons, you cannot have a type of all types. You have to have a hierarchy of them. So these are called universes. The point about universes is ideally you should try to ignore them as much as you can because they're a nuisance, but they're necessary for consistency. I mean, you should hope to, and Lean provides you with lots of helpers in metaprogramming to automatically take care of them. Programmatically, almost always they're automatically taken care of. Yeah, so there's a hierarchy of types instead of being a single one. I think in some,
these instances of add that we defined.
Yeah.
So,
right.
Do they require any properties such as associativity? For instance.
No.
Yeah.
No. If we, I'll come back to that in 2 minutes. So because I'll talk about linear order. So you'll have a further type class which will mean as a further property of, Okay. Now it's a good question, but I'm going to answer something. I'm going to better illustrated in an example in a minute. Yeah.
That fun part, it's is that like a lambda function?
Which, yes. Fun part is, I could even use lambda, and this maps2 could be replaced by, so I could also write it in, I could also use lambda here. I'm hitting the tab key instead of, left arrow, I see. So I could use lambda here instead of fun, and I could also use this instead of maps2. Okay, so so for those who know, of course, fun is, with Lean 4 they stopped using lambda notation, but they call it fun for function, which is anyway more fun. And built into maps2, you can use the double arrow and implies, which is used in many functional languages which we use, but you can also use the mathematicians maps2. In fact, early days of Lean 4, Patrick Massa would say the most important question in Lean 4 is how can we start using maps2 again, and indeed it has come in here. In logic, lambda so-and-so, comma so-and-so is used by tradition. The history of that is because Church wanted to use some symbol by hand, and he could not type it on a machine, so lambda is used. So lambda doesn't, but it's become historical. So those who know lambdas, yes, the fun is a lambda definition. But it's a function which given this gives you this. Those are, in mathematical terms, it's clear what it means. Yeah, so here we are. Okay, so let's go on. I'll come back to smallest now and do two things. Okay, why did I call this smallest I? Here I wrote 0. Let me call it instead default. I'm sorry. What is the default natural number? Okay, let's hover on default. If you hover, it says, so default is a value which makes sense depending on a type class called inhabited. And inhabited tells you it has at least one value. You see, if I took a list of type empty, there is a type called empty which has nothing, then you had an empty list, you actually have a serious problem if you give the smallest element or the head of that list or anything else. Okay, it becomes unsound because there's no such thing as an element of type empty. So in general, you could go to small, so smallest I is used as convention where you can do it for anything inhabited. I have done this for natural numbers, but I could do it for anything inhabited, and I could always return the default. Okay, I won't change that to this. So one thing here is that we want to have a default, but you need more than to have this. You need to have minimum. Okay. So minimum also depends on a type class called min. Okay. This is getting like Naveen's question. So min you can just ad hoc define what the minimum of two things is for any type. So the question we got a minute ago was, does addition have to have any property? No, you can just dump any old thing as addition. Like string with a space addition is quite a badly behaved addition. I mean, you could do anything. You could just take the first element, whatever you like. But what we will do is that I want to define generalized smallest. Okay. So I'm going to wrap this all up in what's called a namespace, which just means it will change the namespace. I'm going to call this nat. And so it's going to be end nat, because this is only natural numbers. Okay, and namespace not list. Copilot's guess is completely wrong in this case. Let me call it general. And I'm going to define smallest. This time I'm going to have a type called exactly. And the problem is I have to import MATLAB. It will take a minute. While it compiles, I will do it. STD is not enough, please. Okay. So when I wanted to define the smallest, okay, I need I wanted to define the smallest for non-empty lists. I wanted to have the minimum, but I also want my theorems about the smallest, and I want it to be well behaved. So what I want is a larger type class which is not just the linear order, which is not just that we have a minimum or even that we have an order, but we have a linear order. Linear order is the total order. Given any two elements, I mean, it is transitive, given A and B, either A is less than or equal to B or B is less than or equal to A, etc., etc. All the nice properties. Yeah. So the question is, you have a hierarchy of type classes, you can just take a simple one or not. Okay. So now sometimes it becomes a pain to keep having to type all these. So we can also simplify our task by calling these as variables. Variable def is nonsense. So this is a convenient thing we'll do here. So I'm just going to say I'm going to introduce these variables, which means every function will automatically pick them up if needed. Okay. And now this is not list of nat, sorry. Here I'm just having to make one change. I mean, that was actually true still. Okay. So the same proof worked in absolute generality. I mean, much greater generality. As soon as you have a linear order, I just copy pasted the proof just generalized using grind to a general linear order. Okay, so this is what were the type classes. Okay. So in 10 minutes, we'll go through a rapid tour of 2-3 things here. Yeah. So let me now stop live coding. So with Prathamesh, you saw how inductive types can be used to define data structures. But they can be used not only to define data structures, but also properties. And in some sense, that is just like axiomatizing. Okay. So I'm going to pick my draft version of this and take a case of even numbers. So when is a number even? So a natural number is either it's 0 or it's a successor of another number. Okay. So is even is given a natural number. There are two ways in which you can prove a number is even. There are two properties which characterize it. 0 is even, and if you take an even number and add 2 to it, then you still get an even number. Okay. So that's fine. Now it's kind of conventional in Lean, when you make this kind of definition, you extract the cases separately as theorems. Okay. The reason here is, this is actually good engineering design. The reason is you may change your definitions. So don't refer to definitions directly. Refer to their defining properties instead. So we just separate the defining properties. And when I annotate it by grind, I tell grind use this automatically whenever you need to. Okay, so then we can prove properties that if I take 2 times n, it's even. Well, what do? Induction n is even, and will give you 2 cases. It will give you 0, and successor is even. 2 is even 2 into n plus 1. Grind is powerful enough that we have told it to use the properties of n plus is even. It can just prove this. Okay, and so we have these properties here. Okay, so then the lesson 2 is we can sort of axiomatize properties. We can say something has these properties by inductive types, just as we had in these cases. Okay. So now given this, let me move to the next long example, and then we'll come back to type classes as the last thing I'll do. Okay, I'll take just 7-8 minutes more. Okay, so I hope these are sort of clear. We have understood type class and inference. This is an automatic way. It's a way which captures both properties like linear order and so on, as well as sometimes data like inhabited. It's telling you a number. Okay, so actually let me show non-atom. Let me just show you a type case where we construct a type class, because this is the smaller example, and then let me go to the biggest example of the morning. Okay, so non-atom, this is a very contrived thing as an example. So a non-atom is a type which has at least 2 elements. It's not empty and it doesn't have any element. It means it has a first atom, a second atom, and the first atom is not equal to the second atom. Okay, so this class is a special case of what are called structures. These are special inductive types. Okay, it's but they are commonly like this. It has these fields. You can think of these as fields. So it's quite obvious what this means here. Okay. Now one of the points is that if I know something is non-atom, I can define the functions called second atom, first atom and second atom. And I also have a theorem that tells you the first atom is not the second atom. Okay, and I can tell grind to use this. Okay, so what are examples of things which are not atoms? Natural numbers are not atoms because first atom I can take as 0, second atom I can take as 1, and this, and Boolean. Okay, but we now have the power of type class inference. Okay, if something is not an atom, then list of that is also not an atom. Why? Because I can take a single element and I can take a list. Okay, this fine. So I think we are understanding how to go ahead. And actually even more is there. There is option type I have not explained, so let's skip that. If something is not an atom, product of alpha with alpha is also not an atom. Okay. Why is that? Of course, because I can take first atom and second atom, say they are different from each other. There are many choices, but we can do better than that. So remember I told you there's a type called inhabited. Inhabited has only one field, which is the default element. So if something is not an atom, of course it's inhabited because you just take the first atom. But now you see, you start thinking mathematically. You think that with the product you saw that there seemed to be a redundancy. I mean, if you don't actually need the product. If you take a product where there are at least 2 elements, it has at least 4. All you need is that the first one has at least 1 element and the second one has at least 2, or the other way around. So we have instances like this. Okay, and concretely, let's look at unit is a type which has only 1 element. Okay, so if I look at nat cross unit, so unit has a type which has only 1 element, but this is going to be non-atom because natural numbers have 2 elements, at least we have proved that. So your type inference will give you a first atom of this. It will also give you a second atom of nat.nat because it looked at a product, it knows that both of these, I don't know which one it did actually. It has 2 ways of doing this. It can note that both of them are non-atoms, or it may note that the second one is inhabited and the first one is non-atom, or the other way around. There are 3 different paths. This can sometimes create problems if you have multiple paths, but here it doesn't create problems. Okay, so this is to show you how we construct the type classes. They capture structures. Okay, so in about so we have seen many concepts of Lean. What we once saw syntax. The afternoon we'll get to what is very more directly relevant for the hackathon, which is domain modelings in Lean and syntax in Lean. But let's now look at a real example, which is one of the standard ones I look. Look at quicksort. Yeah. Sorry, which one? Oh, okay. Thanks for this question. Yeah, so this is a spiffier way of writing this. Okay, so pipe operator means, oh, actually the pipe operator was not needed even. So the way is normally when things associate, if you write FAB, it's F of A applied to B. But if you want A and B to be applied together, you use that pipe operator. It says applied a function to everything that comes after, do that first. It says right associate rather than left associate. Okay. In Haskell, this is dollar for those who know dollar. Okay, the dollar makes things harder to read. In Lean, instead, there are two different pipe operators. So this one sort of more obviously tells you look to the right first. Yeah, thanks. Okay, so here's, oops, did I close it? No, I didn't, fortunately. Okay, here comes quicksort. Everybody knows quicksort, I assume. And this illustrates how every time I lecture, things get shorter. I did one little thing here, which made life easier. Okay, so first of all, the naive quicksort is the following. If I quicksort an empty list, I get an empty list. And I'm going to take the first element as the pivot. Okay, so I define two functions, smaller, the elements that less than or equal to a pivot, and those that are greater than pivot. Okay, so naively what I can do is that I can look at those that are smaller than a pivot and those that are larger than a pivot. Okay, and then I take the pivot in between the two. Yeah, so to remind people, quicksort means given a list, you take maybe an element ahead and everything else, break the rest of it into those that are before and after that, and recursively quicksort that. Now I had to put partial here because if I don't put partial here, it complains saying I don't know if this is going to run forever, if this is going to terminate or not. Okay, so but the better way is to say termination by L dot length. The reason this terminate is length gets shorter and shorter. Now you may ask, why does the length get, how does it know the length gets shorter and shorter? It has to prove that the smaller has length and larger has a length which is less than this. Okay, the last time I did the demo, I had to give it some help in this. But this time I've done something a bit sneaky, which is in this basic, I added a rule which told it that, so basically what happens is there's something called decreasing, I should not maybe have said decreasing tactic, I should have said decreasing something else. Okay. I told it to use grind to prove termination in short. Okay, so we have seen grind is powerful. It has its built-in thing. There was something slightly wrong, I'll have to fix that, but never mind, it worked. Okay, so it you can define quicksort and it terminates because it gets shorter. And now the great thing about this is that you can prove, okay, I'm just going to run through the code in 2 minutes and then we break for lunch, and then if there are questions and so on, we can discuss later. Okay, this is as I said, ambitious to rush through this very fast, but this code is away. So as I said, it's useful when you define something to make its defining properties as theorems. And when I annotate it like this, it says simp, use this automatically, grind, use this automatically. Okay, so we have member if and only if below. So then we can prove some theorems which says you are in an element in a list if and only if you are either below the pivot or above the pivot. Yeah, that is clear. And from that you can prove by induction that quicksort satisfies one of the two important properties of sorting, that it doesn't change the list, that you are an element in the sorted final list if and only if you are in the initial list. Okay, and we want to do better than that. In fact, this was an exercise you can do better than that and count. And now let me just, so I've gone 2 minutes over time, so let me quickly say, we saw other examples. We saw in the case of even, we captured a property as an inductive type. Similarly, we can capture the property of being sorted as an inductive type. Namely, an empty list is sorted, a singleton is sorted, and if I take a list, if I take x, y and l, so that x is less than or equal to y, and y followed by L is sorted, then x and y and L is sorted. Okay, so this is sort of capturing sorting by axioms. So this is typically what you do when you model anything in Lean. You use these axioms to do it, and then with some help you can prove that quicksort is sorted. Okay, so this is the story here. With that I will almost end. Of course any questions are welcome. So there were question I was asked once, so I'm preempting it, is so what we are working with eval, can you actually compile and run things? Okay, so here I'm compiling it, and this is using our same quicksort. Lake is the build tool of Lean, and well, so it sorted 100,000 elements in 91 milliseconds. So I did not do various optimizations which can easily push this up a bit, but what I wanted to kind of emphasize is that we've been writing programs and proving there is still work to be done to get Lean faster, but it runs, and it runs pretty fast. Okay, the goal is to run like Haskell, if not quite C++, but certainly faster than say Python. I mean, so it can run real world programs. Yeah. So yeah. So thanks. In the afternoon we'll resume with slightly more advanced features, and the code is there. Questions are welcome now or after lunch.
Hello everyone. We'll quickly take a break for lunch and be here by sometime 2:10. Yeah. Thank you.
Yeah, we can chat over lunch. Yeah. Yes. Other property. That's right. What Navina? Yes, that's right. Add is the bare operation. Then there is another type class called add_com, which will be the commutativity of addition, etc., etc. So similarly, there's an order type class which is nothing at all, or you can, but it is usually convenient to make it as a hierarchy where you keep extending it, because you might want to have fewer properties and more properties. Yeah, that is correct. So yes, I mean even this, the type class I defined it had one property only. Yeah, you might want to have many properties at once, but if it is sort of mathematically natural or programming wise natural, though, you do it as a hierarchy, add one property at a time. But if there are two properties where you never want one without the other, then you will just put them together.
they've got it covered. Yes. Mic testing, check, 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 check. Check 1, 2. 1, 2. 2, 2, 2. Check, check, check. Mic testing, 1, 2. 1, 2. 2, 2, 2. 2. Picture in picture.
ಬರ್ತೀನಿ ಬೇಗ ಬರ್ತೀನಿ ಒಂದು 5 ಗಂಟೆಗೆ ಬರ್ತೀನಿ ಆಯ್ತು ಆಯ್ತು ಸರಿ ಸರಿ
Check, check, check. Check 1 2, check, check, check. Mic testing. Check 1 2, check 1 2. Check 1 2 1 2. Check, check, check. Mic testing. Check 1 2. Check mic testing. Check 1 2 1 2. Check 1 2. Check, check, check.
Check mic testing. Check 1 2. Check 1 2. Check check check.
I'll start, but I will. This is. Can you help me by getting rid of
Has
that?
everyone come? The population looks very
No,
less.
but I'll take my time setting up the laptop.
210.
No, but it's okay. I'll just set up my laptop, meaning because that's a iffy process. This way,
Shall I take out this?
yeah, can you? Thanks. We'll start slowly. Oh, people will come in droves, but. Oh, I'll need to change my mouse's battery. I'll need my notebook. Oh, thank you.
You have any audio?
Oh.
You can plug in.
Thanks.
Yeah, it's working. It's working. The
But
current
I'm
is
getting.
coming.
Oh, mouse. Oh, okay, sorry. I thought it was giving me a warning about. people back or should I start? Neeraj, should I start? Or? Yeah. Okay, so sorry, the setup here is quite unique in difficulty level, but let's hope it works. So we had the quick sort. Now I have forgotten what I should do. I'll resume in a minute. Yeah, so continue the introduction to Lean with two different things I want to talk about in the next 40 minutes or so. One of them is we'll talk about state monad and preserving states, and the other is metaprogramming. So let me go with the state first. Yeah, so was this already ready? Yeah. Okay, let's start with an example. So we already saw one monad, which was lists. So monad just means something where you can, we'll see what it means a little better in a few minutes, but it means you can use this piffy do notation to extract things from inside it. Okay, and the most important one for Lean metaprogramming at least is what's called state monad, which remembers the state. So systems can depend on the state, and state monad is one which keeps track of the state. So this is not a big deal. It's actually a very thin wrapper. It just means that you have a state as input, and then you have an output and a new state. Okay. But so typical example where you use this is this infamously slow function. Right? You take Fibonacci numbers. Everyone knows what they are. F of 0 is 0, f of 1 is 1. And f of n is, actually f of 0 is 1, as far as I'm concerned. F of 1 is 1, and then we go from n plus 2 is the Fibonacci at n plus 1 plus Fibonacci of n. And almost anyone, when they learn about recursion, will hear this is a horrible way to compute Fibonacci numbers. That is because we have computed, say, Fibonacci, say, 33, it means we have to compute Fibonacci 32 and 31. But when computing 32, you have to again compute 31. And it does it again. So every time you compute two numbers, and then you compute 2 and so on, and it branches. And so with such small numbers as 33, you already run out of into trouble. Okay, a more interesting example would be things like Catalan numbers and so on. There are various recursive formulae. Okay, so Fibonacci, there's a simple way out of this. You just compute the pair, fib n and fib n plus 1. That is a nice recursion. You can even what is called tail call optimize it and everything else. But in general, what you want to do is you want to say once you compute a value, remember it. That is what we will do. And that's what the state monad will let us to do. So I'm going to define fib m. M means monad. And this is monad customized for Fibonacci numbers. What is this? This is state m. It's a state monad with hash map nat nat. Okay. So hash map is just a map which has an input and an output. Hash means it's an efficient implementation. Given a natural number, it calculates a natural number. This is all the Fibonacci numbers calculated already. So this starts off as empty, and then every time you calculate it, you do it. And so we'll define the Fibonacci member in such a way. First, I'll take the cache, which is the map things that have already been calculated. Okay, so far so good. And then what happens with that is that, so this is the cache, and if you hover on it, you'll see it's a hash map from net to net. And so when I want to calculate a value, I first check if I've already calculated it. That's what the get does with a question mark. So when you get something, you either get something or you get nothing. Okay, so this is what's called an option type, we saw briefly, which is also a monad. So you either get some value or you get nothing. And if you get some value, you return it because we already stored the value. Yeah, so this is the case. On the other hand, if you get nothing, then you use the recursive formula. In the case of 0, we know it's, Fibonacci starts with 1 as far as I'm concerned. So Fibonacci at value 0 is 1. So I'm just going to store the value 0, 1. And again with 1 I store it. If it's n plus 2, you notice I put an arrow here. What this means is it calculates the Fibonacci number, which is going to depend on the state, and then returns the value only. So this is the value of the Fibonacci number. But in the process of calculating it, it has modified the state, and the new state is used in the next step. And then you get a Fibonacci n. When you calculate the second one, the new state has been used in the second one. Now you add these two and then store the result and then return it. Okay? And then you see here, of course this ran earlier, but if I calculate 1001, it's instant even though it's just running out of the screen. Yeah, so unlike the other case, Fibonacci numbers is instant, because once it calculated a number, it extracted it from a calculation which also modified the state. All subsequent commands use the modified state. Okay, so you did not recalculate anything when you calculated things previously. Instead you have this, and it's basically instant. Well, what is this run command? Okay, so the value you get for Fibonacci m, I'll just point out. If you say check m, check fib m. So fib m is going to take a natural number as input, and it's not going to give you a natural number as output, but instead, like we had a list of natural numbers, we have a fib m of natural numbers, which means it's a natural number depending on the state, and the act of computing which also modified the state. Okay, but what if you just want the number? Then you have a command called run and another called run prime. So run prime is the command where you have to give it the initial state. In this case, it's an empty map. You give it an initial state, which is an empty map, and then, so I could even have said empty here instead of this. Yeah, use initial state is the empty map. Yeah, you give it an empty map, and then it keeps calculating it, starting with the empty map, and then discards the final state. If I use run instead, it would also return the final map, which I don't want, that has 1000 values stored in it, okay, which would just clutter up the display if I tried to display it. Okay, hash map has no default display. You can make it displayable, but it would simply clutter up the state. So that's the issue with the Fibonacci m of run prime. So that's the, yeah. Can't hear you, sorry.
Yeah, do we need a theorem for slow fib and fib m agreeing on their outputs?
This is actually a very good question. It brings up several answers. Okay, the first one of which is that you can only agree on the output if you said if you started with a trivial initial state. Okay, because I could lie. I could give it an initial state which has some wrong values of Fibonacci, and then it will give me wrong values there, and everything else also will be wrong. Yeah, so if I change the initial values. So such a theorem is not actually true even if you don't also specify initial state is these. Okay. Second point is proving things in monads is a little tricky. There are now two frameworks, std.do and then Whale as it's called, which let you do it. So proving a statement like that is a bit tricky, though we'll see in our next example that we can do it. Okay. In certain cases. But final point is, of course, yes, you should prove it. Because if you have a fast algorithm which is optimized and another which is obviously correct, then one of the things you want to do is to prove that the optimized algorithm is the one that is easier for a human to read and check correctness. So that would be a weaker version of what we had with sorting, or where we proved the sorting has the given properties. Yes, that's right. Yeah, someone had a question here? For finding the, you mean running something like Eratosthenes sieve?
For the nth prime number finding.
Using Eratosthenes sieve or something like that?
Yeah, I mean even just the monads, using that. And
yeah, you would use monads for lots of state things like this. With prime numbers, you'll have other issues as well. But yes, almost anything where you do things recursively and which involves computation, you should remember previous values.
What we used to call dynamic programming, right? This
Yeah. So you will use for many such situations a state monad. Okay, and my next example will be a complicated one, and this is getting a little more like the theme of the hackathon. Yeah, sorry, but there's a question before that. Yeah.
Modify and insert, they're all part of monad.
Yes, very good questions, thanks. So if you have a monad, just like you have do notation, more precisely, sorry, modify and insert are part of state monad. If I take a monad like a list or option, modify doesn't have any meaning there. But
monad by itself just gives us the do and the operator which is left.
Monad by itself gives us exactly what are called map and bind, map and flat map. And we'll see examples of that in detail, but not modify. So modify makes sense if you specifically have a state monad. On the other hand, insert, where is it? Insert has nothing to do with monad, it's a property of hash maps or dictionaries. So insert is simply a function that is inserting a value and modifying a map. So this function has to do with the particular data structure I'm using to store it, which is a map. But the modify is a state map, like run and run prime. These are state monad specific things. Yeah. FibM. Yeah. Yes.
So basically, how does the get know that it is the state monad of fib_m and not anything else?
Hover on get, but this has a non-trivial case. Yeah, so get of a state monad in this case is always the state of that state monad, because this is a simple state monad. I used what's called state m. But what you may be thinking of is in monadic programming, you often have one state on top of another state on top of another state, what is called state T. So which is the state you will get? Get will always get the outermost state, but often you don't want it. So there is something called get D and read D. These are methods that are associated, and then you tell it what type to get.
What if you want to input one state and modify it somehow to get another state?
Yeah.
But you pass it as a parameter in the function.
Meaning?
Like, for example, n could be a, let's say, fib_m of some nat, maybe.
You want n to be also fib_m?
For example, in some case.
Yes, you can.
So in that case, the get will give you what?
No, it will still use only the right-hand side. It will not get the state of the argument. It will get you the state of a monad. Okay, so let me sort of clarify. Let's check state m. Yeah. So fib_m, capital fib_m, is just an abbreviation for where is it? State m of hash map. Okay. So it will always give you this particular hash map. If you have multiple states, you can get specific ones. Yeah.
So if I have an ordered pair of state m's, like state m cross state m, then what?
No. So state m is a function which will take a type to a type. So if you have state m cross state m, it's no longer a monad, and you can't use do, and you will not get anything at all. What you can have is a state stacked on top of other states, and that is a common idiom. There you use state T. In that case, get will get the outermost one, but get D and method which is there, which can get you any one of them, and you do frequently use that. Because you actually have a meta, elab, this, that levels. You want to get at a particular level, you can, there's a refinement of that.
So when you use the, right to your right. When you use the do notation, you directly go inside the monad, which is the output type, right? Like if it's, here it's fib_m nat, so once you do do, you are inside fib_m, and that's why get state will get the, get will get the state.
Yeah, so get is specific to state monads. The arrow is for all monads. Yes, but that's right. Because the type, when you say do, you know that which monad you're in. That's correct. Yeah. Okay, sorry, your question from there? Run versus run prime. Run returns both the value and the final state. Run prime throws away the final state. So in this case, what we want is the Fibonacci value at 1001. If I wrote run here, it actually would complain because hashmap doesn't have a display wrapper as it's called, but if I converted it into list or something, I'll get all the 1000 values it calculated along the way. I don't want it, I want to discard them. Yeah. So run versus run prime. Run is runs it and gives you the final state and the value. Run prime discards the final state. Yeah. Any other questions? Okay, so let me now go to a big example, and which is in draft, which I will not do this. These sort of bring things together. So this is kind of, you can say, one peak. Finally, I'll have one more peak when I write at the end, where I look at this file monad, which is kind of a baby version of modeling an agentic system. A very, baby is an exaggeration, very, very tiny piece of it. Okay. But let's take an example of a stack machine, and a very simple one. So a stack machine is a stack of natural numbers. Okay, this is kind of upside down stack machine in a sense. So what we have is a stack, and I'm just going to use lists for stack. There's a list of natural numbers, and I have three possible instructions. I can push onto a stack, I can pop onto from a stack, and I can add. And what add does here is it takes the top two values, adds them and dumps them back on the stack. Okay. If you add a few more, then a stack machine can be used to compose all sorts of things. But be warned, of course, that this thing doesn't always make sense. You cannot pop an empty stack. And to add, you need at least two elements. Okay. So this is a case where you're sort of modeling a system in, this is kind of both sides of the hackathon theme, but you're kind of modeling a system and you want to prove validity, etc. Okay. So program here is just a list of instructions. Abbreviation is just a special kind of definition, which is telling, hey, Lean, please expand this quickly. So stack is just a list of natural numbers. Now, how do I evaluate a program on a stack? Okay, there are two bad ways of doing it, or not great ways of doing it. One is with exclamation, which tells you that, never mind, I don't have the tail thing. This can give errors. Okay. So there are two ways of giving it. One way is to give you an option stack, which means it either gives you a stack, some stack, or it gives you nothing. And as soon as you have an invalid option, it gives you nothing. Okay, so if you have an empty one where we're, so if the program is empty, then of course do nothing, just return the stack itself. Okay, if you have a push command first, then add P to the stack and then run the program. Okay, but on the other hand, if you have add or pop, things are more complicated. If you are adding, there should already be at least two things on the stack. Add them up, put that in the stack, and then run the rest of the program. And similarly. But failure of these, you return none. Okay. So this is a kind of thing you do in functional languages. Okay. Option, it's called maybe in Haskell, it's option in Scala, where you don't do the bad thing of throwing a null pointer or giving none, but instead explicitly say we have some type. Either we are returning something of that type or just that type, or we are returning nothing. So keeping track of things. But this is much less than we'd want in Lean, because this only means that you're not going to crash. It's harder to reason about. You don't want values. What we want to understand is how to prove things. Okay. So what we want to do is we want to define when a program is valid on a stack. And just before lunch, I took an example. I said you could kind of axiomatize this by saying how are all the ways of constructing a valid program on a stack. Okay. This doesn't depend on the specific stack. It depends only on the stack size. Okay. If you make it dependent on specific stack, proving will be harder. It gets clumsier. Okay. So if you have an initial stack size and a program, then we are going to, I'll open this. Okay. So if you have an initial stack size and a program, then it may be a valid program or it may not be a valid program. Okay. So what are the valid programs? First of all, if a nil is, nil, so this is just a fact that if I took an empty program did nothing, then whatever stack we have, it's valid because there's nothing to run. Okay. So whatever the stack size n is, then if you took an empty program, it's valid. Okay, and then what if the first instruction is a push and rest? Okay, what happens if the first instruction is a push? Then actually our life is easier. What we need is the rest of it, for it to be valid with initial stack n, it's enough that the rest of it is valid with initial stack n plus 1. So if you had a program which started with push and then had a bunch of instructions and your initial stack size was 7, after push it would become 8. So if you have a program which is valid, then after pushing k it becomes valid with with size n. If it was valid with n plus 1, it's easier to be valid with larger sizes. Pop, it goes the other way. If you want to pop, if you want a program with, if the first instruction is pop, then if n is 0, it is never valid. You can't pop an empty stack. If it's of the form n plus 1, then n, which initial stack size n, you should be valid with the program p. P is the tail program. And similarly with add is even more complex than this. If the size is 0 or 1, it's not valid. But if the size is n plus 2, then after you do the add, the new size is n plus 1. So you can deduce a valid program of size n plus 2 with addition if you have a valid program with n plus 1. Okay? So this is kind of a bit of a mouthful to digest, but part of this ambitious hackathon is digesting things fast. So feel free to ask questions. So this, you should think of this arrow as like implication. And what you have captured is, these are the things that tell us ways in which I can tell how a program is valid. Okay. Once I have this, I get some theorems out of this definition, and I tell simp and grind you can use them. Okay. And then, to my pleasant surprise, okay, you suppose you have a program which pushes A, pushes B and adds, then it's valid program starting with an empty stack. And grind just proves it. Let me just stress test this. Suppose I change it to initial whatever n is. Sorry, n. Yeah, it still does it. So if I took any natural number, whatever my initial stack size was, it could be 0 or anything positive, then if I took push A, push B, and then I add, because what I did is I put 2 things on the stack and popped. That was fine. What if I push A, push B, add, push C and add? What is this program actually? This program is something which is going to add A plus B plus C and put it on the stack. So this is also valid with an initial stack. This grind can prove, but not with its default configuration. I have to tell it try a little harder, and it can do it. Okay, so this is an example of a stack machine. Okay, so here are other theorems when proved just as experiments. Okay. Yeah. No, so that is the main thing I wanted to show. So you can, I think I used some of these. So in the same light, we can prove some general results. Okay, so if I take, if a program becomes valid after pushing, then it must have been, it is valid with k plus 1 for the tail that was given, and the similar ones for add. And now this lets us have a, I should have maybe made this a type class actually. No, it's okay. I made it a type hypothesis. Okay, so now we can have a nice safe evaluate function, something which is guaranteed not to crash. Because if you think stack crashing, you could end up with a buffer overflow or something like that, okay, or buffer underflow. So you evaluate given a program and given a initial stack, okay, and a proof that for that stack length, the program is valid. Only then you get a stack. And how do we do it? We induct. We induct on the program, and then we can use various results which tell us they are here. Okay, so here we are evaluate. Okay, and this was an invalid case, and it just refused to run it. If I push 2 and then add with an empty stack, then I have a stack with only 1 element, so I tried to push it. Okay, I could use the same syntax, but it just crashes. Yeah. So again, like we did in the other case, we could always have by grind as part of a macro to shorten our syntax if we are always going to be typing by grind. So this is the story here. Yeah. So Okay, let me get to the next set of examples, then we will go to the final one later. So let me sort of, we're supposed to be 2 to 2:45, let's say 15-minute delay. Okay, I'll go. Okay, so now these were maybe almost an exhaustive, one more feature we'll see in the next example. So we have seen most of the features of Lean. I'll then, yeah. Okay, I'll do pi4 and load 5. What were the other files? Oh, sorry. This is not relevant. Okay, so let me slightly switch gears. We'll do, yeah. So now, so far what we've seen is really programming and proving in Lean. We have seen most of the concepts. We have seen monads, we'll see a bit more of them. We have seen type classes, explicit, implicit parameters. We have seen theorems. We have seen how to construct properties. We have seen how to prove things. So we are really in a position to use it as a programming language. And we have seen an extended example of modeling a domain in Lean. Okay. So now we'll turn to what is called metaprogramming, which is extending the syntax. So what is metaprogramming? Metaprogramming is working not with a language, but with internal representations in the language. So you're working not with the terms, the objects, the classes, but how they are internally represented. Okay. We did that a little bit when we used what is called a macro. And so the conceptual point with Lean is a bit unusual. Metaprogramming has two levels. So here you see a Lean program. It's just a string. It is not directly converted into an internal representation. It is first converted into what is called syntax. In most languages are what's called abstract syntax tree. But Lean, being a formal proof system, has a deeper level called expressions. And these expressions are a fixed small class. It's itself an inductive type with about some 8-10 options. Okay, so expressions are the really core notions in Lean. You go to syntax and you go to expressions. And so when you talk about manipulating internal structure, you could manipulate syntax or you could manipulate expressions. And macros are things which map syntax to syntax. So let me quickly look at a couple of examples of macros, and then we'll look at something lighter. And this is, again, one of the early comments which came in Lean. One thing people like about Python, even those who are fans of other languages, is the for comprehension. This is no doubt extremely elegant. Yeah? So you have this kind of syntax. X star X for X in 1, 2, 3, 4, 5. Or X star Y for Y in this, for L in this, for X in L, and for Y in L. Okay? This is undoubtedly this thing. And well, then Lean will have a little bit of Python envy and say, why can't we have this in Lean? Okay, and then as Leo de Moura would say, make it in Lean. Okay, so we'll show you how to make it in Lean. Let's make it in Lean. Okay, so in Lean itself we have something not so different from it, which is the list comprehension. Do loop, do notation. So if I look at this example, what I'm saying is do let X come from that list, return X star X. This looks a lot like the previous example. Yeah, it doesn't look that different. Okay, but actually this do notation is really what is called a map function on list. List.map is something which, given a function from alpha to beta, and a list of alpha gives you a list of beta, simply by mapping each element. So what I do is I take each element and square it. This is a function, squares each element, and this is what I get is here. You can guess what this is. So when I talked about monads, mapping is one of the fundamental things you can do with the monad. So even more fundamental is you have singleton lists actually. And what about the more complicated list comprehension? That became this monadic notation. We have L in 1, 2, 3, 4. And we can multiply it this way. Okay. So if we use list.map naively, we get, so suppose if we just converted all these into map, then I don't get actually the correct list. What I want is list of products. Yeah? But instead what I get is that I'm sorry, where was I? So this one became a list.map. But if I use list.map in this nested way, then I would get, instead of this list, I'd get a list of lists. Because every time you map, you're getting deeper and deeper into the lists. Okay? So let me just unpack this for you. If you apply it to L, you're taking L is a list, you're mapping each term, oh, okay, anyway. So this is a list of lists. Yeah, so I'm unpacking it badly. What we need to do is use this term called flat map. So flat map is something which, given a list and a function which takes each element to a list, gives you not a list of lists, but flattens the whole thing out. Okay? There's an operator called bind which is similar to this. So flat map is given a list. So here what we do is, maybe I should have a simpler example. Sorry, I'm a little short of time. So we have a list, and we flat map means given a function from lists to not just one list, but a list of lists. Okay, so then we will, let me give a simpler example. So eval, suppose I take a list. Suppose I take a list of integers, 2, 3, 4. Okay, and then I map it with the function which will take a list x to the list which consists of x and x star x. What is the result I get here? So this is a function which takes each element to a list, and that list is x and x star x, or let me make things interesting, more interesting, double. So it gives you two numbers, one of them is the double and one of them is this. But if I map, what happens is 2 goes to a list, 3 goes to a separate list, 4 goes to a separate list, I get a list of lists. Okay? But now suppose I change this, instead of deleting I'll copy, and I flat map. Okay, suppose I want to flat map the list. Okay, then what I get here is, when I want to flat map this list, then I get a single list. All it has done is taken those lists of lists and flattened them. Okay. So this is the fundamental thing. So the question is, what is monad? It's something where you can have what's called pure a single element, but basically the main operations you can have are mapping and flat mapping. In a state, mapping and flat mapping would be that, okay, so we'll come to that later. Okay, so now, great, we know how to do these things, but we can actually make a pi for comprehension in Lean. Okay, so namely, we'll take a teak for term. So this is the simpler version of for comprehension. If I have a term, and then I have an identifier, a letter, x in so and so, then I write a function and map the function. So if I look x star x, pi for x in so and so, I get exactly what I got in the case of Python. So we have managed to introduce Python notation to Lean for comprehension by rewriting it in this way. I use pi for because for is actually a word in Lean, and it's a bit of a nuisance to avoid a clash between the technical terms. Yeah. Sorry, what were you saying?
This is working at the syntax level only?
Correct. This is working at the syntax level.
Yeah.
We'll come to the expression level in a few minutes. Yes, correct. So this is where I defined a syntax and I had it as a syntax level. Okay. So here is the next one, which is working not at the syntax level. So I've been talking about lists in Python, but Pythons also have arrays, okay, where you put a hash. This is a more optimized version of a list. Okay, list you do when you want to prove theorems about it. You use arrays when you want efficiency. So what if you wanted to use the same notation pi for, but with a list it gives a list and with an array it gives an array. Okay, then you have a problem because you want to use list.map in one case and you want to use array.map in the other case. So syntax to syntax mapping will not work. You have to be a little bit smarter. You have to actually build an expression for that. And here I'll just show you what we did here. Okay. think things are getting a little heavier, so I'll just slow down and yeah. So let's look at this. So previously what we wrote were elaborator macros, and let me sort of end this session with just this. This time what I'll do is write what's called an elaborator. So an elaborator is something which will take syntax and give you an expression. Okay, and we'll see how an expression in Lean looks by constructing it. First of all, I have the same pi4 syntax. I have a fun syntax, which is function $x to t, and elab term is something that will convert the syntax into an expression. So I got an expression. I got an expression for this function part. Okay, but the more interesting thing I did was that I looked for the type of, where is it? Yeah, I infer type of L expression. What is L? L is this one, is the list. Okay, so let me again look at this as an example. This could be x star x for x in, and L is either a list or it's an array. So what I'm doing here is I'm inferring the type. I first find the expression for it and infer its type and check whether it's some kind of list or some kind of an array. And if it's some kind of list or some kind of an array, then I make the function application, apply the function, which maps a list to this expression. And if it's an array, it maps an array to the expression. And if it's neither, it throws an error. Okay? And, so as you see here, in this case, what it did is it looked at 10, 20, 30, found that it was a list, and constructed a list for you. And the list that it constructed for you is in the following way. It made the function x to x plus 1 and just evaluated it. And then it found this was a list, so it took list.map and fed in that function. And in this case, it found this was an array, and as you see, it returned, if you put a hash before it becomes array notation, it returned a list array. Okay, so this is just a glimpse of the power of metaprogramming in Lean. Okay, so here you can really embed another language in Lean by doing this kind of thing. Okay, so maybe because of the delays, let me just stop here. Prathamesh will take over, and then we'll look at a little more metaprogramming and then one final example after a break. Yeah.
So we will have our next talk as a continuation from the morning's talk by Professor Prathamesh. This will be again on the introduction of LeanLang part 2.
डायरेक्ट करा था डायरेक्ट वाला
Thanks a lot. I know this is a session that's going to be one of the hardest to catch attention in. I mean, the time before the coffee, afternoon coffee is always like, yeah, I think the time when the sleep starts acting up the most. So I hope we just kind of, but like try to at least get some attention, just pack some energy just so that we kind of get through with getting through some other basics of Lean. Okay, so just to kind of say, so this is what I'm going to throw around are basically 2 examples in this session of verification. And possibly if I have time with one with basically where I kind of redo one with Monads. So the first example is actually it's a paper which I just kind of encountered on Monday itself, and I was kind of quite fascinated by, which was essentially that people were trying to kind of do these tooling for lightweight monads, lightweight formal methods. And they wanted to basically, the visualizations of formal methods you have in tools like Alloy, people wanted to kind of get nicer visualizations. And this is a group in Brown which has done this. And then so for that they created a programming language, and then they verified that the programming language was correct at some level, the soundness of it in Lean. So the paper is pretty much on the website that I gave, and it's been largely inspired by this effort. Okay, so in the morning we just looked at tree, and so what we'll kind of look at is trees along with some embedded visual representation. So I'm going to create some kind of a semantics of these inside inside Lean. Okay, so let's just go back. So I think just to kind of tell you what we're going to do. Oh, and before this, I think I've just been asked. Okay, so all of this is available on my GitHub repository, which is basically Prathamesh Jashturaga, and the GitHub repo is bits and branches. Okay, so that's the GitHub repository you can find this in. And so idea is we want to develop a visualization for data structures basically, and we already know some trees. We'll stick to like writing max heap, and we'll attempt to prove some properties along with some properties of max heap on the side. Okay, in order to do this, we need to first create a max heap data structure and few nice properties of the data structure. Create a framework for visualization in Lean as a data type, which also encodes the information coordinates of leaves and nodes. Okay, and maps the trees to visualizer, and then we prove some properties of the visualizer. Okay, right, yeah. So let's begin with this. So I'm going to begin something called as a heap tree. Does this look familiar? This heap tree, does anyone? Yeah. So how is it different from the tree in the morning that we did? Anyone? Yeah, but in this definition, is there anything? Sorry? Sorry? Yeah? I can't hear. No, nothing. It's actually the same tree. It's just the same tree. I just called it heap tree. This really, I mean, I'm not really imbued any heap properties of this as yet. Okay, right? So I think I've not done anything to that effect to suggest that it's a heap. I just called it a heap tree. So it's bits and branches. Yeah. Okay, bits because of this. Prathamesh Jashturaga, you'll find it. It's public repository. Okay. Yeah. Okay, so again, we open the namespace for it, and as Sudhata suggested, I'll just kind of make alpha have some nice properties such as decidable equality and have an order on it. Okay, so the first thing I want to kind of get to when we want to kind of define is that we want to basically make sure that if I have like the child value essentially, which is basically should be less than some, is bounded by some value, like value of all the nodes is bounded by some value. Okay, so which is what I'm kind of saying, that essentially if it's a leaf, it's true. If not, my child value here, which is the of the topmost node, is bounded by some parent value. This parent value right now at this point need not belong to the tree. Okay, so that's kind of independent. We will use that more carefully in a bit. So then how do we define max heap now? Okay, so now is where we are kind of defining max heap. We are defining it as a property on this tree. Okay, so it has the following component. It's inductive. So we are first saying a leaf is a type of is a max heap leaf, and satisfies the property of it. And given a node, okay, I have L, which is a heap tree, V, which is alpha, and R, which is a heap tree. If L is a max heap, R is a max heap, if it is root bounded by L, that means that for L and R, if I take the topmost element, if they exist, is basically bounded by V, right? So that's what it is. And then I would say it is, again same for R, then we would say it is basically X max heap node LVR. Okay, So just a question, how many of you haven't seen functional programming before? Okay, ever, okay. So 4 or 5 people. Okay, just a quick thing. So what we're going to see here when I'm saying A implies B implies C implies D implies is essentially saying it's pretty much kind of equivalent to A and B and C and D implies in some sense. I mean, this is basically a technique called currying. Okay, so in some sense, you can actually kind of verify this through it, and there's a lot of nice properties that you have actually with currying. So yeah. Now, of course, so let's try and kind of prove some properties of max heap. Okay, so what's the first property of max heap that you would want to prove? If something is a max heap, if I tell you what's the first property you would want to prove? Sorry? Top element is the highest element, right? I mean, that's essentially. So I want to collect all the elements somewhere, right? So that's the first idea. We want to collect all the elements somewhere. And so I'm going to define this function to basically to fin set alpha. Okay, which takes a heap tree and gives it a finite set over alpha. Okay, again, this is when you particularly finite set is a type of finite sets over a particular alpha. It's a polymorphic type. Okay, so a heap tree for a leaf gives me an empty set. Okay, so that there is no element here. And for a node LVR, I collect nodes on L, we collect nodes on R, and I just add V to it. Okay, right? So we're just adding E to it. It's not very different here. Okay, so just to kind of show you how we can evaluate this, I have this 5, 2, 4, 3 lean again, and yeah, it's collecting some nodes, right? We can see that it's collecting some nodes here. Okay, now I think I just defined this function, which is basically, let me just show this, which is, let me just fill this up properly. Okay, it goes to something called as an option type. Okay. So just an option type, just to kind of define, if I just had to define would basically, it consists of 2 kinds of objects. Okay, it consists of some none, and it consists option type of alpha. It consists of none is an element of my option type of alpha, and this is how I would really formally define this, or it would have some V of alpha of my option alpha. Right? So I think these are 2 kinds of objects. This is basically how an option type looks like essentially. Okay, so this is an option type, I mean, which was discussed before, I think, just to kind of tell you how it actually looks like when we describe it as an inductive type. Okay, so just to erase, we just work with the option types that are provided. So, and generally we use it often, like for instance, if you want to divide a number, basically a division by number is not always strictly defined. You may have none sometimes, and you may have actually some value sometimes, right? So for get node, we have for leaf, we are not getting like any node. There is no central node whose value we are trying to extract. For node LVR, we get some V. Okay. But the thing is, you see on the right side, we are not using L and R anywhere, right? So I just can just put in like an underscore to kind of say, okay, hey, I mean, I'm not really using this anywhere. And so I want to introduce some tactics here, just to kind of see this. So which is, sorry. Okay. Yeah. So I want to say that this is basically is max heap of this. Okay, sorry, let me just take this off. So I'm trying to prove that this is basically a max heap that we see, which is essentially it's a node which has some value V, and it has 2 leaves on the side. I'm trying to say it's a max heap. Okay, so how do we prove this? So when I put this constructor, it basically kind of gives me 4 cases. Is the leaf max heap, or the left side, the right side is max heap, and then if you kind of go here, you will also see that V is root bounded with leaf, and V is again root bounded with the right side, okay, because they're both the same. And now for all of them, essentially you have the same thing, which is basically you just want to like basically just simplify with the definition of max heap leaf and root bounded, you will basically get the answer. Okay, for each of the 4 cases, I just have to do that. Okay, so the way you would generally normally do cases in the most messy way is write something like this, like simp is max heap dot leaf or something like that, and Yeah, which basically tells me the specific thing that leaf is a max heap. Okay, yeah. So something to that effect. This does one goal, then it does another goal, then it does another goal. Or I can just say that all these goals essentially we just look. If you observe that all the goals will technically, most of the goals look very similar and they all need the same tactic. So we just kind of just use this, and right. Just another simple thing, just to kind of introduce you to just one or two more tactics, is that essentially if you see this, we have some h1 which is a is equal to b. It has nothing to do with roots or trees, and maybe I won't even use it, but I just thought it's nice to see here. Is that a is equal to b and b is equal to, sorry, we just substitute a, we would basically kind of literally a is equal to b, wherever b is, we get substituted with by a, and then you just get the same final answer. Now, of course, the same thing can be literally done by something called simp all. Simp all just simplifies by basically considering all the possible hypotheses. It includes all the hypotheses in the list of things that you're actually doing it. Okay. Now, the last thing I want to show you is how do we really deal with the cases when you have an existential quantifier as a hypothesis, right? So that's one particular proof tactic I just thought we could just see before we again embark on this. Okay. So here it is. There is an existence px and qx. And there exists an x such that p of x is true. Okay. So for that, let's say if I do R cases, remember the hypothesis H has an existential quantifier. Okay. So how do we really do that? So usually we assume, okay, consider x to be that object which satisfies this property. Right? In math, that's what you would really consider. Consider let x not be the object that satisfies this property. So I do R cases, which essentially tells, which breaks, which essentially, for instance, if I just did R cases with H, it gives me something, and if I say HP, it was just going to give me this. I can break this further with HQ, which basically breaks that further. So R case essentially splits these rules, and then I just tell it, as I said, to use this X, and then it automatically, the Lean's very powerful thing. Okay. So now max heap, how I would ideally define, is again like in the way it starts defined, is actually the type class, which is basically there's a tree, and you have a proof that it is actually a max heap. Right, so that's essentially how we would kind of literally ideally define this. But of course, I'm not kind of going to use this much because I think our goals are slightly tangential. So, but this is basically the more nuanced way we would want to actually do this. And since this is an introductory lecture, so yeah, okay. So there is a brief small notes. I think so. Anyone who basically wants to kind of just revisit what we have done. Again, the whole idea is it's a very quick intro. So anyone who wants to revisit all the stuff that we've done, you will always find it back. You can go back to the notes online and you'll be able to see this. Okay, so the first thing we want to prove is the following, that root is maximal element. Okay, that is for all elements belonging to collect nodes, get node of t get is greater than or equal to lm, right? So does this capture the specification for a max, I mean one property of a max heap that you would want to test? Would this qualify? Okay. So get essentially means it tells you, given a sum v, it tells me what the value of v is. We can get that from that. So what do you think about this? For all elements which we collect the nodes. Sorry, yeah. Panic, yeah. Unless, yeah. That's true actually, yeah. Proof of non, yeah. That's true actually, yeah. Sorry, however again, yeah. Yeah, panicking on none, yeah. Yeah. So okay, so I think I'll just ignore that. We just kind of ignore this. Yeah. So I think that's actually an interesting point. Yeah, this is actually just panic. This is not a safe version in that sense because on none it's kind of literally going to panic. Okay, so this is not a safe version of get. But I think I just was very lazy with this. So okay, so now how we do this is basically, as you can see, for all the elements of the tree which we collect the nodes of it, we want to show that if we actually extract the top value, it's going to be greater than A for any element. Okay. So we're going to do an induction on tree. So I'm going to first basically assume that my tree is a leaf. Okay. So we are basically just collecting the nodes, and I just kind of simplify with the collecting nodes and it kind of takes care. Okay, because essentially if you're collecting nodes, you get an empty set and then that just makes life simple. So now again, remember for induction hypothesis, you have to induct over both the left case and the right case, right? So for the node, I take the left tree, a value in the center, the right tree, the left hypothesis and the right hypothesis. Okay, so we see it so far here. Which is the so the very first one here is essentially the left hypothesis. That means if L is a max heap, L is not equal to identity, and for all these elements, if it is the topmost element is greater than 0. For R max heap, if R is not a leaf, then for all elements this is greater than equal to thing to the LM. This property satisfied, and H is basically, this is a max heap, the one we are considering, the one you are considering. Now for all the elements belonging here, the topmost element is essentially greater than or equal to this. Okay, and this is basically telling us that this is not equal to leaf, which is something that's kind of fairly straightforward, but it just states it. I mean, as a part of, by just substituting it in the hypothesis. So how do we kind of now go about doing this? Okay, so the first thing to notice is that the goal is of the form for all. Okay, the goal is of the form for all, and when I say that the goal is of the form for all, we want to basically convert it to basically given any instance of LM. Okay, given any instance of LM, I would want to kind of convert it to that. Okay, so I would basically, for instance, I would just write intro LM. It's going to kind of say, okay, LM is a natural number. Now show it for this particular LM. Okay, like a fixed but arbitrary. Okay, right, as we would really call it in math. Okay, now I can also kind of use the intro rules and essentially correspond to what you would call as introduction rules for logical systems for natural reduction. Okay, so basically that's where the name intro comes from. And at this point, again, if I put the LM, it also, sorry, can you see what has changed here? Can we observe what's changed? Anyone in the audience between the last LM and before this? Okay, okay. So this LM essentially basically takes this last fort and puts it into the title LM. LM becomes the name of HLM. This is hypothesis on an LM. I should have, named it better, but it kind of sends it as a hypothesis. Okay, so instead of for all elements which basically belong into set S, I say consider a fixed but arbitrary element L, and then I had an hypothesis that E belongs to the set S in some sense. Okay, that's what we are really kind of trying to say. Okay, so then now we have these properties and we want to kind of get somewhere. Okay, so I'm going to simplify my get node. Okay, when you simplify the get node, all the problems essentially disappear, and essentially what we are trying to ask to prove is just to prove that this LM is less than or equal to V. Okay, because that's essentially what we have to kind of prove. Okay, and then now what I want to have is now this LM is basically, LM basically belongs to, this element basically belongs to this left VR. Okay, so it can basically belong to the left, it can be equal to V, or it can be R. There are three possibilities, right? So I'm basically asking it to simplify this. It kind of converts it to this. Okay, so now again I can use R cases. Now R cases can be used in multiple contexts. So one of them is if I have a hypothesis of the form P or Q or R, I can basically kind of instantiate it to the three cases where for my hypothesis is P, then my hypothesis is Q, and another hypothesis is R. So this is what the R case is doing. So I'm going to call the three hypotheses as HV. So remember, if you can see this HLM disappears, and what we have is HV, HL, and HR. And the very first hypothesis is only LM is equal to V. Okay, right? And when I put a dot, essentially I'm basically working with one case. This is the first case. And here it's fairly simple. We just have to directly apply HV, you will basically going to get this answer. Okay, so if you just directly apply HV, you get this answer. So I'm just going to directly substitute it with that. Okay, so now let's consider the second case. In the second case, it belongs to the LM, it actually belongs to the left part of the tree. Okay, now how do we do this? So again, I want to know this L itself can be two possibilities. So one is that the leaf can be empty. The left part itself can be just a leaf. So at that part, what we can do is we have this HL, which is this LM belongs to this leaf collect nodes. So essentially, if this leaf is empty, then it's not going to really belong anywhere. So there's going to be a contradiction. So I'm just going to do this, and it kind of finishes off the goal here. And then otherwise, the leaf is essentially the L is another tree, which is LL, VL, and RL. Okay. So for this, sorry, now we have this hypothesis that basically this is basically, this particular thing is essentially a max heap. Okay, so I'm going to put these cases, and that kind of gives me, if you look at it, it's going to give me these four possible, it's going to give me these four hypotheses, which is A, LL, V, the first VL, RL is a max heap. V is root bounded, sorry, this is root bounded by V. R is a max heap, and yeah, R is also root bounded by V. Okay, so I'm going to basically put all these assumptions with this case node. Okay, and then what we do is, so now we have these four things. So I'm going to first rewrite this root bound to essentially at HP. So what that does is, it gives me the fact that VL is less than or equal to V. Okay. So now I also want to say that the VL is greater than or equal to LM, and then that basically takes care of the job. Okay. So to do this VL is greater than LM, if you notice closely that this is basically LM is an element here, and this is a max heap. And then we have this inductive hypothesis IHL, which tells me that if this is a max heap and this is not equal to 0 for all LMs, this can be done. So I'm going to simplify this HA at IHL, and IHL essentially becomes this. Fairly simple, yeah. And then we just substitute LM IHL here, and then we just directly just use grind, and it literally takes care of the entire thing. Okay, so now that what remains is essentially the right side of it. Okay, and the proof is very similar. So I would just like to leave it to you as an exercise. You just have to make some adequate changes. You would be able to kind of do this. Okay, so the proof is fairly simple, and it's not very different from the left side. And then of course there are also methods by which, where you have the proofs are very similar, you can actually kind of extract the commonalities and just apply them once instead of like rewriting multiple things again. Okay, now I think we will come to writing actually the visual tree structure. Okay, so now the structure, the 2D grid positions are basically indicated by two things, X and Y. Okay, and we derive this representation and decidable equality. That's basically just a two-coordinate system. And the drawn tree essentially is the tree that we are actually trying to draw. Okay, so it has, so what we need to draw something, we need the following things, which is one, which is a value that's actually being stored at that point. Then we have the position, we have the left, which is if there is a left drawn tree, and if basically where is the right drawn tree, but if there is a position to be up to the right drawn tree. Okay, so now what we will do is this layout function actually takes a tree and two integers, which are basically the starting points, and it kind of returns an option drawn t into integer, and basically it literally returns this, and where it basically with the second cross essentially tells you the position of where you are actually going to put the next tree that exactly exists. Okay, so for a leaf, if my for a leaf, and no matter what the second question is, that I'm actually not drawing any option tree. Okay, and I'm actually going to put it, the dot basically goes to whatever was the next X that was there. Okay, so consider this node LVR, and I have some depth. Okay, so there is some depth at which we are actually where the node is basically being criticized, and the last coordinate is essentially net X. Okay, where we're going to actually put the last element. Okay, so so the first thing is, let's take this layout depth -1. So that means if I take the L1, the left part will be at a layout which is at depth n-1, and it was actually at some position X. Okay, so then yeah, this is L and the depth -1, and if it was the next position from there, it was at the position X. Then we apply this, we get these true things, which is the draw left, which is the option for the draw tree, and then the next position in which it is actually going to kind of where we are going to be working. Okay, so let's call this the root X as the position where we are going to be the next position. Now for the right tree, we're going to actually add 1 to that. So it's going to be basically root X plus 1. And again, the depth has to be 1 degree lower than where we actually are. Okay, so that's where we are. Okay, so that kind of allows us the freedom. So now what do we really draw? So we basically have a value V, and that value is, the position of that value is at root X and at the depth. And the left is the left draw tree and the right is the right draw tree. And this is going to be the outcome of drawing a particular node, okay, if it is of the form. and this is going to be drawn, and after the next position it arrives at is the next x2, that is after we draw the right tree. Okay, so that's the next position that we would be entertaining. Okay, so now where does the layout, if you actually put 2, 0, 0, 1, we're going to get this layout function. Okay, so just to kind of give you, let's draw this leaf 2, leaf 1, 1, and you get the value of 2, we get the position 0, 0, the left is none, right is some value 1, position x is equal to 1, y is equal to -1, left is equal to none, right is equal to none. So it essentially gives us some value. Okay, so now the funny thing is, this function looks very messy. Okay, at the end of it, okay, I tried my best to explain it to you in a few minutes, but it looks really, really messy, right? So how would we kind of try to verify this? Okay, so I'm not sure how many of you actually managed to get through the very brief introduction I gave, but essentially you have to trust me on this, that this function is actually trying to map it. Okay, but the question is, why should you trust me on this? Right, you have to verify some properties of this, that essentially it is actually going to do what we want it to do. So what would be the properties you would want to verify of this function? What would be the properties you would want to verify of this layout function? It's a very messy function you can see here. Okay, because I don't think I would have convinced anyone in the last 5 minutes that this is actually the function that is going to do the job for you. Okay, so what would be the properties you would verify of a function that basically takes a tree and maps it to a max tree and maps it to a coordinate system? What would be the properties you would think? Okay,
the parent is on above the children nodes if you're mapping it to a coordinate system.
Right, perfectly right. So the parent should always be greater than the children system, right? Given any parent, it should be higher than the children. Okay, right? Anything else? What would be the other properties you would want to verify? It's embedded. Okay, so in the sense, edges don't cross. Exactly, edges don't cross. Right, edges don't cross. That's, I think, one of the most important things. And especially when you're trying to draw, like, kind of create an artificial visualizations, the hardest problem is to ensure that the edges don't cross. Right, that's a fairly complex question. Yeah, and essentially, I think, yeah.
All generations or layers are at the same.
Of all the generations, the layers are actually at the same level.
Yes.
Yes, that's another property. Yes, perfect. So what I'm going to do, I mean, given the time, is just I'm going to do one. Okay, I'm just going to say that the y decreases. Okay, and the edges and the fact that the x coordinates are kind of again increase as you kind of go from left to right is another thing. And perhaps in using these, you would be able to kind of show the edge crossing thing. Edge crossing is a little more like harder to kind of do this. And just to tell you, I mean, all of this code is not very hard. I mean, I literally came back home one day at 12 o'clock on Monday when I heard this talk and did it from like 12 to 2. Okay, so this can be literally done in 2.5 hours. This kind of work if just, okay, so. And I mean, okay, actually I did a little more yesterday morning, so I think, yeah, polishing, so yeah, but you can spend it just a few hours, you'll be able to do this, so yeah. So this was basically at layout here, and so what we have is, essentially we have this heap, and what we are saying is, if this YT decrease, yeah, sorry, I'm just kind of lost between the screen and this, sorry. Yeah. So if you have the heap tree layout, implies that, oh sorry, I'm just completely now lost with where we are. Oh sorry, if heap tree layout is equal to some dt and next x prime, then drawn tree, y tree decreases essentially with this drawing tree, the y decreases. Okay, so this y decreases on a drawing tree is essentially encoded by this. Okay, that you have a drawn tree, and if the second and the third coordinates are basically none and none, okay, you are basically going to be true. If the second one is L and the third one and the is P, you have to ensure that the position of the Y for L is essentially less than P dot Y, and Y decreases in L. If again the same thing happens, you again the right position essentially less than P dot Y and Y decreases. And otherwise we have this P and then some L and some R. Okay. So these are the properties that exist, and y decreases L and then R decreases is just recursively kind of framed. Okay. Now, just to get back to this particular proof, essentially what we are doing is we are trying to do induction here, And so let's just see what exactly happens if I just do induction like this with what exactly is happening here. So we're going to do an induction on the tree. Okay, so this is basically mapping the tree to the layout. And I'm saying if it is of the sum form, then essentially whatever the form is, it's a decreasing y coordinates. Okay, so which is what it is asserting. So how do we really do, so what exactly can be the problem when we actually just write the induction here in this form? Can anyone spot an issue with this induction as the way we've written it here? Between IHL and H, do you see a problem? Okay, I'm going to just point out where to look between IHL and H. Or sorry, yeah. So literally assuming the same depth, right? So which is not the case because the depth of it should be literally like depth minus 1. So the way is basically it treats it as a fixed variable and not as a variable that's actually quantified, which is what we want actually the depth to be. So that no matter what the depth is, no matter what the next x is, no matter what the drawing tree is, and no matter what the next x prime is, that it should essentially, the IHL should basically be independent of that. Okay, so that's what we actually this generalizing does. It basically takes when you have certain parameters that essentially have to be generalized, that have to be quantified. Okay, for essentially the sake of a proof, you write generalizing. Okay, so that's a fairly important trick, I think, to go with an induction. Because in induction, quite often your proofs don't naturally, your induction tactics will contain certain variables that need to be quantified, that need to be universally quantified for your induction hypothesis to hold true. So which is what this does. So we have a leaf, fairly simple proof again. So now again, now this is a command called unfold. What it does is it just unfolds a definition at a particular definition. And so what here we do is I think just a small trick which is basically generalized because I have this l.layout.nextWidth. So I'm just going to call this depth minus 1 L. I'm just going to call it RSL. And I'm just going to create, it just creates this new thing called HL, which is, this is equal to RSL. Okay, then again we do an R cases of this. And similarly we're going to generalize this here. So which basically kind of, yeah, which allows us to just some nice renaming. And then of course we kind of come across this topic where this thing, so where I have my R here, sorry, where is H here? Sorry, so I have this particular H which is again very messy thing, which is equivalent to, but it's messy, but it's basically has 2 coordinates, and each of them is basically kind of bound to a tuple in some sense. So what we do is we do an injection, which kind of simplifies the H into smaller things, and we again use injection to kind of smallify it into like smaller goals. So we kind of have like much nicer properties, and then we just rewrite the HDT to extract HDT very carefully. And now we unfold what exactly it means for the Y to decrease. And now we would basically take the KSL for draw X with none. And again, I do it, now there are possibilities for drawing right. Okay, if the draw left is none, the right can be drawn or not. Okay, so the draw right itself is none, we use a grind. If not, we again just kind of literally go through this and get through. Okay, so and similarly, for some, again, it's just a matter of just writing some very straight commands and then just plugging through a grind. Okay, and this is pretty much, I think, what you can really do here. Okay, so I think the interesting is basically the idea of generalization, which sometimes when you have really messy topics, you can just club them into a new goal, and then you actually have to quantify. I think these are 2 essential ideas with which you can actually prove this a particular theorem. Okay. And yeah, and I think I've been, of course, at it since then, also to kind of actually extract a nice JSON file from here. So I think that's not yet done through. Hopefully, I'll get done with it by tomorrow or something. So yeah, now I think the second part I want to do is basically, again, so Siddhartha discussed the compiler. So I just want to discuss this compiler for a very small toy language. Okay, so this toy language essentially contains programs of this kind. Okay, so I have X assigning to Y assigned to X plus 3. If X is greater than Y, then Z is equal to 1, else X is equal to 0. Okay, so this is, so what are the elements that we see here in this programming language? it's a bunch of sequence of commands. What are the elements that we see here? Sorry? Assignments, conditionals, yes. Literals, yes. And variables, yes. Sorry? Comparison. Okay. Do you think this allows mutation? Yes. Okay. Why? Yeah. Right. In the last one we are having. So we are allowing mutations in this language. Okay. So I want to capture mutations. So now I just want to rewrite the same thing. So I'm going to call each step like essentially it begins with a sequence. Sequence is what kind of like binds it off. Okay. So I have assign X. Now all variables are strings. And the type of what we are assigning it to is kind of made clear. So this is assigned to nat5. And assign Y to add the internal syntax is var X to nat x plus 3. If then else assign it of this form. Okay. So now the question is, how do we really represent a state? There are multiple ways of representing a state here. Okay. So the way I kind of choose to represent a state is actually not the most nicest, but I like it. So yeah, but it has its issues. Sorry, but it has its positives in terms of so the state is essentially a function from string to natural numbers. Okay, right? So we just define it as a state is actually rather the type of functions from string to natural numbers. Okay, states are essentially. So given any program, the state of a program at that point, it tells me what is basically the function and what values of strings it is taking to what values of natural numbers. Okay, there are also nicer ways. I think you can actually think of it as like a tupled list, for instance. That could be a nice way of thinking of a state that also has a much better memory bound, right? So yeah, like far better in terms of computability, but yeah. But let's just stick to this. So now I have this. So I want to first define an empty state. An empty state is all the variables are mapped to 0. Okay. All the variables are mapped to 0. And that basically essentially means my state will basically take you strings and my variables can only take natural numbers in this programming language. Okay. Now how do I really update a state? I update a state, I take a variable name, I have a new name, and it kind of gives me a state. So it gives me a function where if x is equal to var name, then it gives me the new value, otherwise it just returns the old value. Okay, where s is the state function, right? So state is a function, remember that. Okay, so now let's talk about the expressions. It's fairly simple. Nat is an expression, var is essentially a string. Add is, you have, it's recursively coming in. I take two expressions and we get another expression. Subtraction is again expressions. And yeah, you can do a derived expression here. So I can check these three and all of them basically give me an expression. Now, of course, once you have an expression, you also want to evaluate expressions, right? So how do we really evaluate expressions? So the first way I would going to evaluate an expression is, I take the expression and the state and return a nat. Okay, so I'm going to match the expression with a natural number. It should return the natural number itself. If I match it with a variable, it should basically a variable is a string. So and this remember state basically takes a string and returns a natural number. So it should return the natural number associated with the variable at that particular period of time, right? And add is essentially we take two numbers and we evaluate the expression with respect to the given states. And again, subtract, we do the same. Okay, so we start with the empty state and I'm going to write a single line program which is nat3, nat4, and you can see the command here which is it returns 7. Okay, now we define this, now we want to inductively define statements. Okay, so this statement is assign, it assigns to the variable name the value. Okay, this essentially sequence of statements and essentially remember note the recursive nature here. Okay, right? So S1 is a statement and S2 is a statement. So it can basically kind of plug back statements into each other. Okay, and then if then else, I have a condition which is an expression. Okay, and I think then branch, else branch, both of which are statements. Okay, again I have two different statements eventually kind of boiled down to. Okay, so what can be the, so can you notice something slightly off here what I did with respect to conditions? Anything slightly off? But anything's possible. No, I'm not sure what that means. Okay, yeah, but yeah, exactly. Okay, right. So essentially conditional, we need like something more than that. Conditional essentially requires some kind of a Boolean evaluation, right? Essentially some kind of a Boolean evaluation. I just defined it to be an expression. So what we're going to do is default in our restricted languages, we're going to assume that we take any expression and it's going to be basically greater than 0. When we evaluate it, we're going to check that it is going to be greater than 0. That's how we're going to evaluate these statements. Okay, so we're going to evaluate a statement like this. So we take an assignment. This is the value that of E after the assignment. Essentially, I'm going to evaluate the expression E in the state S. So if I'm going to assign var name E, so I'm going to evaluate this and then I'm going to update it, right? So I'm going to update the state with basically with yeah. So which is what we do, and so basically if I'm taking a var name and I kind of have an expression, it's going to evaluate that expression given the state and it's going to update it with that value. Okay. For a sequence, like I first evaluate S1 and then I evaluate S2 with the new change state. Okay. And if then else, I'm basically if evaluate expression condition is greater than 0, as I just stated, then we evaluate expression X, otherwise expression 2. Okay. So what would be some properties of this programming language that you would want to verify? Sorry? Variable assignment? Okay, so let me do a simple one. So I'm just going to take a simple line. I take h and add 1 to it. I want to basically make sure it is greater than the h itself. Okay, right? So I'm going to basically just check it with assign. Sorry, eval state. I'm going to check it with eval statement. And then I want to basically just update and eval expression. No goals. Okay, right? So we have a proof of the fact that as h increases. What about the other one? What about other proofs? Okay, so now here in the second one, again through a bunch of syntactics, you can just try it out yourself. What it basically asserts is the fact that you have a program, and again if I add any b to h, okay, it is greater than what is the value of h is inside the program. I basically mutate h and add a b to it at the end of it. It's greater than the value that you actually after you run the first program itself. Okay, so that's a property that's actually can be again fairly simply proved, and maybe I'll just kind of copy this and show it to you that this is fairly, I think it's pretty much the same set of tactics I'm going to use, and it does the job. Okay, right? So, and if I just had to actually like much easier would have been just to put them as grind and then just use the grind on it. Okay, or just simple rules. Okay, similarly, this is another one. If this is basically some kind of compiler optimizations. That if I have add e nat 0, then I can basically just get add e itself. Okay, this is a dead branch elimination. That is, if I have like some nat 0, if then else. Okay, if I basically get that's equal to 0 because we are testing only for greater than 0, then I just it's the same as just evaluating the second statement, right? So essentially, this can again be done with the simp eval statement. Yeah. Sorry. 1 second. Yeah, eval expression. This literally does a job. Okay, and so similarly we have something which is a sequential association, right? So that's another thing we want to have. So no matter if I execute sequence 1 and 2 and 2 and 3, essentially the sequential association should be associative in a program, in a sequential program like this, right? So that's essentially what it is asserting. And again, you can actually try and check it out yourself. So especially all these other programs would essentially are something that we can do. How much time do I have? Oh, sorry. Okay. Okay. Sorry. Yeah. Sorry. Yeah.
The sequence underscore assoc lemma below, like in the next screen.
Here.
Yeah, no, a little above. Yeah, that one. The sequence association. Aren't we trying to compare two states which are defined as functions? We are trying to establish equality between two functions.
In this particular case, so it's an evaluation of a statement which is not giving us a function here, right?
No, eval statement
takes
that S will give you a state which is a function.
So it's a state, it's a function. It's actually a function. You're right, and this requires a funnext. Okay, okay. Thanks. You're actually right on this. Yeah. Sorry. What we can do is funnext of k. That's the tactic I would have wanted to. Okay, right.
What does funnext do?
So what funnext does is it basically tells me if I have a function. Okay. That basically, it's if I'm trying to compare two functions. Essentially, it is the extensional equality of the functions. That means for any given variable k, they should actually return the same value.
Okay, and it can prove that?
Yeah, it can be proved. Yeah. So yeah. Yeah. Yeah, in this language you can prove, of course. Yeah, not like in not like languages like Agda, which are all like far more constructive. So you wouldn't want to be able to do that in this. Yeah, here you can actually prove this. So yeah. Okay, but I would just kind of just maybe I'll just catch up with you later. I just want to show one more thing before I kind of end. So maybe I'll just catch up with you a bit on this. Okay. So the last thing I just wanted to just quickly show you was this. Sorry. Was that essentially most of this stuff can be done much more elegantly using Monad. Again, sorry, I don't have the time to go through this, but you can do it far more elegantly using Monads. And there's actually a bunch of, again, it's all called monadic computation in my notes, and we have also unfolded some monads for you, like what it would mean in terms of the monad structure. So here, so it can be done far more. So for instance, this add, sorry, this is, and I've just put them off a comparative level, that is, it gets the state and returns the state essentially acting on X, or or you basically evaluate expressions. So you're not really you're no longer doing even for something like sequence, you're no longer doing those really messy sequencing operations. You are basically checking the states. It kind of does much more, it's far more neater with monads, this entire operation. Yeah. So yeah. Like a lot of the syntax become clearer because keeping track of sequences in long chains can become a bit messy. Right, it becomes you have a much nicer syntax for doing that. So it's far more like, right. So that's essentially what it is in terms of writing. Okay, cool. I think any questions, Ashish? Any questions apart from Shikumar? So I think sorry, okay, so maybe still let's just do eval statement. Srikumar, so I think this is just the goal for you. Okay, so it basically acts the state, which is functional extensionality, and then we directly run this. Okay. Okay. See you all. Any questions, anyone? Yeah.
Like if we use some of the constructs from before, like for example things like syntax and some of the elaborator to kind of like define our own syntaxes, so that like in the comment you had some syntax, right? Yeah. So we could have like some similar syntax looking code in
Lean. Yeah.
But like how do you handle kind of like conflicts with existing syntax? Like for example, like plus and stuff, they exist in both, and even in my language I would like to have numbers of some sort.
Okay, so see, when you're doing a semantic representation, it is basically a word that stands in for what the word is in language, right?
Right.
So it is basically compiling to the plus in Lean when we're evaluating it, right? Okay. So that's what is essentially happening. Okay, right? Yeah. Any other question? Yeah. Oh, sorry?
So if we take higher order properties, that is, let's say the incoming state satisfies some property for all properties, and then try to prove the sequencing operator, how good are the tactics over there? So if I want to say something like for all properties satisfied by proposition satisfied by the input state, if I do a sequencing operator, S1 followed by S2, and if I do them independently, then the final state satisfies the property. Yeah, host logic style kind of thing.
Yeah.
So Okay. The velvet kind of thing. Right. Okay. 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 That's what my question. Okay. Okay. Thank you.
Okay, thank you, Professor. So next talk is by Professor. Sorry. Oh, there's a coffee break right now. Oh, sorry. Never mind. Okay, so we go for a coffee at second floor, the floor above. I misread the schedule. Anyways, so yeah, we'll be back in 15 minutes. We should start by 4:15. 4:10. Let's try to come back by 4:10, and maximum 4:15 will start. Yeah, you can set it up.
What's your name? Similar looking things.
Sorry?
This one was mine, I suppose.
वो लोग ready नहीं थे जाने के लिए. They were setting up for this. Okay.
Can I put this? This is for the power, no?
Yes.
This is happy. Where is this?
The HDMI they will give, you can connect it here. The second one.
Yes, yes, yes. Just give me a second.
Yours is Mac? Mac, right?
Yeah. Will there be a problem?
No, no.
I'll be doing PDF things to kind of make it less problematic. I have. Oh, it's not happy.
Wait. Wait a sec. Just go in any of the slides. Can you go to display settings? There was a blink. So your resolution was there. Can you go to the display settings?
Where is display? This is
You need to put this configuration.
oh my god. This is where are you, man? Do you see display? Yeah, displays. Oh, this is the same displays. I'm not sure. Where is the resolution?
I think advanced. Advanced? No, I don't see it. Can you do it full screen? Any chance this tab? What is the issue with the resolution right now?
The frame rate should be 30 hertz or 60 hertz. Oh god. This thing seems to be totally increasing even. You wanted to see more?
Just first resolution here maybe, just in case it comes.
Yeah,
Screen resolution.
Where is that one?
Can you
Oops. Something else is up. Oh, this. It. Thank you.
So, good evening, everyone. So, we will start with our next talk for the day. This talk will be presented by Professor Ashish Mishra. He is assistant professor at IIT Hyderabad, and his research interests include program synthesis, automatic program verification, and functional programming and type synthesis. So he will be giving an interesting talk on the topic of introduction to refinement types. And okay, yeah.
Thank you, Anirudh. So, so I'd like to start by thanking the organizers and Siddharth for inviting. And so this talk is somewhat related, somewhat also goes in another. Am I audible? Yeah. So this is somewhat related to what we are talking. In fact, a lot related to what we are talking in this this kind of workshop. There is some points where I want to take your attention a bit away. So if you have been following what Siddhartha or Prathamesh has been talking from morning, is that Lean is a very expressive language, as well as with a very expressive type systems where you can write these rich properties. And then, as you might be following, a lot of effort is towards actually proving some of the properties about these things you're writing. And one of the kind of key points which is being we are all learning, is that a lot of this is automated through various tactic mechanism. So in this automation of verifying the properties about proofs or about terms, or if you're talking about any other data type, it's okay. There is a rich literature in the domain of program verification or software verification.
where for last 20, 30 years people have been building, and I think Siddhartha in the morning kind of gave some idea that, okay, software verification community is a lot interested in the automation portion of this thing. And there are various works in that domain, and particularly related thing to this lean kind of machinery is this notion of what are called as refinement types. So I'll be talking particularly about refinement type here. And most of my work builds on various kinds of refinement types. I build different newer kind of refinement types. So I was also tempted to give a more hands-on thing, but 45 minutes was not good enough for that. But the good point is that in the refinement type world, if you are with me and you keep on following, okay, I am able to specify a property using refinement type, then the actual proof is not interesting. You just push a button and run the type checker and it proves the thing or gives you a counter example, okay? So the interesting thing is how to use this language of refinement types to specify interesting property. And that's what I will try to do in this talk. Through examples, I'll try to kind of give you examples of interesting properties which you can write with what these things, refinement types are. Okay? So let's try to start with taking a step back, if you're coming from more formal verification programming languages perspective. So the typed programming is the core of it is this dream that my type checked programs don't go wrong. Okay, that's the philosophy in that program, in that world, that if I type check, then the programs don't go wrong. The notion of what don't go wrong means is very precisely defined by the kind of type systems you are working with. But the idea is that if you think of very simple languages like C or Java or somewhat with stronger types like Haskell or OCaml, you will find that your type system is fairly basic, and it is basically restricting what kind of values terms in the language can take. Okay, so that's what is happening in more or less the thing. But even that basically prevents a whole class of runtime errors. Okay, and that's what make it. So if you have program with JavaScript, which has a much weaker type system in the background versus, let's say, a language like C even, you'll find that, okay, your type checker is giving you much more kind of guarantees. If you are a fan of Rust kind of language, you see that type checker gives you much more advanced guarantees about memory safety and other kind of things. Okay, so the dream of type programming is always to kind of avoid these kind of errors. However, the standard type systems are often blind to what you can think of as logical errors, okay? And a kind of very classic example, and sorry that I'm using the same, so by definition classic means like you can use it n+1 number of times. So is this kind of error like division by zero error, okay? And so here's a function. So yeah, so more or less the syntax I will use in the slides is Haskell, but refinement types are not only limited to Haskell, they are kind of defined for OCaml. We have a whole machinery of that. They're also defined for imperative languages like C and other things, okay? So for example, if you are thinking of average kind of thing, so if you can see that once you are looking at empty list for example, then the type system sees 0 as a valid integer as an input, and this may lead to division by 0 kind of error in the thing. Okay, so this is one example of logical error you can think of. Okay, so I would like to kind of just give you, I haven't explained the whole syntax, but I would just like to tell how these kind of logical errors, the first attempt of refinement types was to kind of prohibit these kind of logical errors. So it's kind of right to put that context as well before I go into much more. So refinement types, which are built into various kind of things, liquid types, relational refinement, and there are so many other things. They are also implemented in languages like Haskell, OCaml, and others, allow you to define kind of similar kind of properties that Siddhartha or Prathamesh has been defining since morning in types. So for example, here I'm defining a type called as non-empty, and for now just take from me that what it is saying that it is a list such that the length is not equal to 0, okay? What exactly are those curly braces? What is that bar? I'll come to that. Okay, so right now it's a type which is refining the behavior of your original list of integer type. That's why refinement. To saying, okay, these are only those lists such that their length is non-equal to 0. Okay, so this is the kind of notion. Somebody was asking what is the notion of refinement in this. So the general idea is that if you look at all possible list of integers and think of a space of values they will take, a refinement of that, a refinement type of that, or a refinement of that type will carve out a subspace in those values. Okay, so that's how it is. It is a refinement of the original behaviors of the thing which you are actually covering, which is very common in computer science in general. So using this non-empty thing, and I think a similar kind of example had been talked about earlier as well, you can now revise the type of average, and all the refinement type I'll write in this blue colored thing with these kind of curly braces. So this average, this is the standard type for average, which is also called as the base type, and this is now the refined version of the type. And with this refined type, your type system can actually restrict the you to apply average to cases where your length of the list, input list, is 0. Now, one of the things to understand, one of the basic difference, I think Professor Siddhartha also in the morning gave you these kind of examples, but when you were trying to apply these functions, remember the hypothesis things which are over there. This is just like an hypothesis being added to now with this input. Here, the burden of proving on those hypotheses is not on you. The type system will be inferring them directly. Even with the tactics, they are more or less automatic, but here the type system will do the inference for you. When you try to apply to an empty list, it will right away raise a type error. Okay? So now I'm going to talk about a bit more, given that this is lean versus, I'm putting it in the context of where we have seen a lot of lean kind of programming. So I think to understand the refinements in the way of refinement types, it's important to understand there's two ways of proving properties about these terms or programs. So I'll use terms and programs then as same because they are for PL perspective they are the same thing. So most of what we saw in the what we have been seeing since morning is this extrinsic style of proving properties about functions, about data types, and so on, where you define these functions and data types as themselves as terms, and then prove a property or a theorem or a lemma about them as an extension. And so I'm not saying that theorem provers can't do intrinsic styles of proving, but more and more the difference is that they do this kind of proving where you define a term and then try to prove some properties about that. As compared to that, as I have been saying, the refinement type community is more about doing what is called as intrinsic style or Church style of proving these things, where a term exists with its type. Okay, so when you say that x as an integer, when you're first writing these kind of programs, x and the type integer was together a term in the language. Okay. So you can't write terms which have incorrect types. Particularly, that's what your type system restricts you to do. You cannot even write those terms which have incorrect types. Having said that, I must say that refinement types, there are refinement types which also do extrinsic style of proving, but more or less that's the kind of understanding in the world of people who do refinement types. Okay? So now coming to refinement. So what we do is basically we start with a base type A, like integer, and now I'm going to formally say what those curly braces are. And then we define a property R that refines A, R at A or something. And one of the things about this refinement is that if I just remove all the refinements in the program, I get the original term. Okay, so that's one of the property you keep on maintaining as you go along. So, is there a question? Okay, so this is how you, so given this, this notion of what a refinement is, so now you can define refinement types, or what are called as base refinement types, as follows. So this is a typical structure in which you write a refinement types, and what it is saying is that v or new, basically, which is used as a self-binding variable, this is talking about the variable for which, or the term for which you are defining the type, has some base type A such that new basically satisfies this property P of V, okay? Where P of V is a Boolean expression or a logical predicate. So now this doesn't look very different than any other dependent types as well. So one of the questions you might have, like, what are you talking about? I can write the same thing in those kind of worlds as well. So I'll come to that, the difference, what difference is there, but let's try to see some of the examples with this kind of structure. So here I have kind of just said P is the predicate rather than P of V, so I'm dropping V, just saying that, okay, P is by default applied to whatever variable you have over here. So now you can define the kind of things we have been defining in Lean, like natural numbers, like even integers, like integers which are less than 100 and so on and so forth, okay? So this is here, so this particular syntax of defining a refinement type is taken from Liquid Haskell, but many other languages like in OCaml and others also allow you to define a refinement type, which are basically a type synonym if you are into OCaml and Haskell world. Natural number, which is basically defined as this particular thing. Okay, so now coming back to this question, how is it? So given that this is particularly allowing my, so this looks eerily similar to dependent types. What is the kind of basic difference between a dependent type-based system like Lean versus this world? So the difference lies in terms of two things. On one axis is the expressiveness of these systems. On the other axis is the decidability of type checking in these systems. Okay. So dependent types are extremely powerful systems, and they have very high expressiveness. So you can also define high order. So this P basically could be any higher order logic or any rich logic as well. But as you go into those richer and richer logics, you lose the decidability component. And one of the things which you are continuously taking, that it is deriving this decidable equality, it might not be feasible every time. So refinement type by definition restrict these predicates or refinements, so as to say, to a fragment of logic, so as you get a decidable type checking as an output of that. Okay, so by design, these systems are built so that your predicates are coming from a small fragment of first order logic, so that for any functional language, more or less, any term you will write, its type checking will be decidable. And because of that, a lot of, you get this guarantee that whatever types you're writing, you are getting this automated type checking as an output, with the expense of losing expressiveness. However, a lot of interesting properties, and this we have seen over the last 20 years with various kind of works, could be modeled by staying within this domain of limited expressiveness of first order logic. Definitely not all things could be proven, and that's where it's an interesting time seeing Lean also getting that kind of automation along with that. Okay, so now going further, so now we understand the difference. Going further, I think some things is direct. Yeah, the P has to be a first order logic formula. You can do quantification, but the point is, like, every time. For various interesting properties, you can do quantification, but every time you have to do some neat trick in your type system to lower them down, okay? And that's where most of the type system research has been. How do you do that neat trick, okay? So our work or other works are always about that. So there's no formally, so when you design the refinement type system, you will design what this P would be, what these are called as qualifiers in this world, what these qualifiers could be. Syntactically, while designing a language, you're not restricted to make it, you can make it as expressive as you want, you can make it, but later on, I'll talk about that. When you actually want to do type checking, particularly subtype checking in this world, you need some well-structured properties of P, and that's where you will lose decidability. So to answer your question very formally, there is no restriction on you. You can make it as rich as you want. You can still call it refinement types, but you will lose decidable type checking. Yeah. So I think the one of the more empirical question is, like, what kind of formulas can exist over there so that you still have decidability, and that, I think, to answer that question, I think we stay in first order logic. Even in the quantification, you don't talk about quantification, or you can talk about quantification or the term variables, not or predicates. You don't go into second order. That's what the thing is. Okay, and as we'll see, but for various kind of hard order functions, you need some kind of properties or predicates. But that's where the tricks come into. Okay, so now some of the things is directly borrows from dependent types. So function types are particularly that thing. So here, just like any other dependent function type or product type, basically you can define a function type. For example, for clamp, which takes from integer to integer to integer, you can say that it takes the first parameter is low. The second parameter actually depends on first parameter. So this dependence is given by this kind of first order logic predicate. And then basically, if low and high satisfy this relation, then it just returns an integer. Okay, so this dependent function type so function types and refinement types are exactly like dependent function type. The only difference is that each of these parameters are themselves a restricted form. Okay, so this will allow this will again so now here again. So if you write any definition over here, and if you check that definition with this particular type, now whenever you make a call to clamp in any context, you are never allowed to make a call to clamp 10,5, for example. Okay, so you don't have to prove that anything about that. So it can infer these things. So another thing it does is very interesting. So a lot of the other things which we saw were towards when suppose we have this kind of functions like my absolute function, and it has two different branches, and I want to prove that I refine its type by saying that, okay, it takes an integer and always returns a natural number. And ideally, what I have to do is I have to kind of do some kind of induction on the branches and then prove it, even though the grind can basically grind away everything. Here, you don't need to do that because your underlying typing semantics will know that, okay, for this particular branch, you already have that x is less than 0. And if x is less than 0, then this particular expression will return a positive thing. So your type checker will generate these kind of constraint automatically and throw it to solver. And it can, without any kind of additional effort, you can right away prove something like that. Okay? Yeah, so I think I had a slide which I removed because I thought, so what is happening in the background is that think of this, that I'm saying that in this branch, I know something about what is the context and what is the value of this. In this branch, what is the context and what is the value is there. So all these things are translated into some kind of first order logic formula expressions. And then you also give a specification. Remember, your top level specifications are acting like a specification which you want to check against this program. Those are also first order logic expressions. And now you want to do what is called as subtyping check, whether the type you got for the term is a subtype of the original term. Okay? And that subtype check is basically in this world which relates all these syntactic logical expressions into actual logical checks which could be thrown to SMT formulas. Okay? And that question was very exactly at the right time. So basically in the standard, so how many of you understand subtyping? Okay, so a lot of, if you think in terms of programming languages, so subtyping is interesting because of what is called as substitution principle. And what it says is that if you define a subtyping relation between two types, T1 and T2, so in any context where you can put a term of supertype, you can always replace that with a term of subtype. That's the substitution principle, and that makes a lot of interesting things in programming languages, particularly very useful in object-oriented world. Okay, so but the notion of subtyping in most of the standard type system is often manual hierarchy. Either it is defined in the, you have a question? Either it is defined in the language or you define it using this subclassing kind of structure. Okay. In refinement size system, it is a logical kind of implication. So I think this, maybe this is not a very good thing. Maybe look at this. I think this is, because I was talking about R. So here is what is happening. So let's say you want to say that this particular type with a refinement P and a base type B is a subtype of this another particular type with base type B and refinement Q. this you can argue when whatever is your context. So remember, context keep all the variables which you have already have a type around. Under that context information, if you can actually prove that the refinement P implies Q, okay, for all variable parameters for which P and Q are defined, okay. So there is a universal quantification in this thing. So this particular rule, which is the subtyping rule in the refinement type, is the place where you actually take these kind of subtype checks and all these specifications into your logical constraint, so as to say, and these kind of implication checks are then thrown to solver. Sorry? So the validity is the standard SMT kind of validity under, so you assume, so your question is very valid, so basically, yeah, so that under the given set of theories in SMT world you are talking about, and the constraint your program has generated, so for conditional branches and other things, you want to prove that for every value variable of the correct type under those theory, P can implies this Q. Is that the question? Okay, yeah. So it is based on what theories you are working with. Okay, so if you go beyond the time, most of these. So to give you an example, most of these theories will be equality, uninterpreted functions, and linear integer arithmetic. More recently, also some algebraic data type theory, but that is not very well evolved in SMT solvers. Some theories of strings as well are there. So. Okay. So now what? So this is basically used now to kind of make logical judgments in the refinement type system. So for example, the type system knows that even is not always a nat. Okay. How does it know that even is not always a natural number? Because if that is the case, then it will have to prove that if I have a type for even, it must be a subtype of nat. And that, if you want to kind of prove, then you will have to prove something like for all v, if you do mod 2 is equal to 0, implies that mu is greater than equal to 0, which your Z3 will say false, and basically type system will say that this is not a subtype. So a lot of these logical deductions which you will do in a proving style in Lean world are basically translated into these things, which anyways I think Lean is also doing a lot of that internally. But okay. Another very interesting thing in this world, so because, as I said, like a lot of effort has been made to kind of make it as much less painful for people using it, even though it's still very painful, is that is this idea of refinement inference. Okay, so you don't want to write these formulas other than the top level specification. That's what your goal is. So you give me a big program and just write a specification at the top, and I should be able to infer as much as of refinement type as much as possible. So there are various kind of works which have gone into making these inference systems richer and richer. Type class inference at least is not there, so basically that could be added into this world. So refinement type world never went into type class inference kind of thing. But there's a lot of machinery for this. So for example, in this particular case, if you look, if you define a positive type called as positive for all integer greater than 0, then you can actually prove, given this definition of absolute sum and your earlier definition of my absolute, the specification for my absolute, plus the property of the head, which is giving you the head of a list, you can actually prove that the output of absolute sum is going to be positive. You don't have to annotate any of these things. The type checker does it automatically. Basically, the designer of the type checker does it a lot. So that's it. Okay. So far so good. So I can basically define these kind of inductive. We are still not in the inductive data types, but some data types with kind of additional properties associated with them. Now, one of the things we haven't yet seen is like almost all these languages have these richer data types like lists and trees and other things which are inductive in most of the cases. And so how do we express the properties of these systems? Okay, that's one of the things. And Siddharth was in his talk, I think. So Prathamesh first defined all these types in inductive world, different kind of things. So you can define different data types, and then I think Siddharth at certain point mentioned about axiomatizing some of the properties of these things. Okay, so but here remember we are relying that there are first order formulas which automatically capture these properties about these things. So for example, length of these list or height of a tree. Okay, where does these things come from is the question. Okay, so one of the idea could be that we just like we were using greater than, less than in our earlier examples. So these kind of, just give me a second. So where is that? Yeah, so these kind of formulas, when you're looking at this was directly coming from the underlying SMT theories, okay? So one of the extension could be that even for these kind of formulas, I can write away, even for these data types, I use the underlying SMT theories, but as I said, those theories are not that kind of efficiently implemented, or many of these things are also go to the cases where SMT solvers struggle. So to kind of handle that thing is, the idea in this world is also towards axiomatizing some of these things. And the axioms in this world are called as measures. Okay, so it's very simple. You basically define these kind of measures which are going to be predicates for your theory. But you don't even need to go into theory in most of the cases, because all you want to is translate them into some kind of uninterpreted functions in SMT solvers, and then you can discharge many of the interesting properties. Okay, so for some of these things you do need some interpretation. Okay, so for example, length of a list could be defined as a measure, and you can now define as empty list as length 0, and then length of anything non-empty is 1 plus the length of the tail of the list. Okay, and once you have defined this, now you can talk about interesting properties of these algebraic data types. Okay, so for example, you can define a list A, which is a list of so the standard polymorphism kind of term polymorphism is here as well. So rather than talking about list of integers, you can talk about list of of data type A. But you can also talk about empty list, which is just saying that length of mu is equal to 0, and non-empty list, which we already saw that you can either say this or length of mu is not equal to 0. Okay, so any of these things could be. And now using this, you can talk about properties about these kind of functions. Okay, and so for example, if you actually use a safe head function, which is basically just returning the head, but it shouldn't be applied on an empty list. So basically, you can give it a more refined type, and now your type system will be okay with this particular case, because it will be able to deduce that. Yeah, so your type checker will say that this particular thing is safe because there is no error. Error is not reachable. So this is for pedagogical purpose. It won't exactly say that, but yeah. Okay, good. And there are different kinds of measures you can define, and you can talk about interesting properties about these things, not very different than. So one of the caveat is that when you define these measures to your SMT solvers, if you are a designer of these type systems, you have to give these axioms. Okay, so because it needs to know what measure, how does the measure increase or decrease. So you are axiomatizing exactly as you are doing in other words. Okay. So now we can again talk about the safe average case. This I don't want to talk. So yeah, this I want to talk. So now till now we have been seeing these kind of things where we have these data types and we basically refine it with very simple formulas. But this can go much deeper. Okay, so we can have these refinements embedded directly into data type definitions now. Okay, and this is where intrinsic nature of these things become much more clearer. Okay, so basically, for example, you're defining these sparse vectors, and what you are assuming is that every index in the sparse vector is strictly less than this dimension. Okay, so your sparse vector is a vector where the values of type are of type A. And it has this data type has basically the dimension as well as the elements, and what you are suggesting that this is a list of an element and the index of that element into the list, and you are putting this constraint into the index that whatever this index is, it has to be always less than whatever your dimension is. Okay, so this is like deeply going into the deeper structure of the data type and trying to refine that structure itself. Now, with this kind of thing, when you actually want to create an kind of inhabitant of this particular type, if you are not following this constraint, your inhabitant, your type checker will complain, and we'll see this with a binary search tree, which is much more interesting. So. So the sparse vector is just saying that not all the indexes, very few indexes are filled, and you want to kind of, whatever values are there, you are keeping this index, and you are saying that I have a dimensionality, and I always not all these things are filled. Okay, so yeah, maybe this is a better example. So binary search tree we have been looking. I think we looked since morning. So the top is a standard binary search tree definition in a language like OCaml or Haskell. This is a Haskell version. And this is a binary search tree where elements are for type A, and this could either be a leaf or a node with 3 parameters. So one is basically the root. This is a structure basically, root, left, and right. Each of these is a binary search tree, and Prathamesh defined many of these structures of this kind where you had the structures plus variants as well. Okay, so now I want to kind of embed the refinement. I want to embed the binary search tree property into the type system, and here's how you can try to do that. So you define this BST-A where leaf is as it is, but node now you can use this refined type that root is of type A, and left is basically has a type called as BST-A-L, A of root, and right has BST-A right R of root. So where BST-A-L and BST-R are defined as follows. So BST-L is basically takes 2 parameters. One is the type parameter, and other is basically the. So this is also a value parameter in this what it is called, and what it says is that this is defined as follows: that BST of this is a binary search tree where all elements satisfy the property that these elements are less than the second argument passed to the BST AX. Okay. Similarly, you can define a BST. So BST-L and BST-R are basically binary search tree where every element is less than X and right greater than X. And now you use this BST-L and BST-R information right away into left and right node, and you can assign these kind of, you can define this type into the system. Now, ideally at this point, I should have kind of opened a refinement type checker and shown you. But I don't think I did it. So, but what I did is basically I coded something into this thing. So if you actually try to create a binary search tree which does satisfy this property, okay, then for example, if you look at this particular thing, the binary search property will be satisfied in all the nodes, okay. But so then if you try to create a OK BST which with the construction applied to the type to the data constructor which you saw earlier, corresponding to which there is a type constructor, then your type checker will be happy. But if you try to do something like node 69 leaf and leaf in between somewhere where which is a right child of yeah, I think this is the problem now. I think this was the problem. Yeah. So it is. I was forgetting this particular. So yeah. So it is in the left child, but it has one of the elements which is greater. So what property does it violates? It will violate this property that the left child has this BST-L type, because the type system won't be able to prove this constraint in this particular case. Okay, good. So now till now what I have done is I have said like you can define interesting properties, somewhat interesting properties, by showing you that you can embed binary search tree kind of property also into refinement. I have also shown, okay, you can talk about inductive data types. There are some of the non-trivial properties on them. One of the big, but all of this has been in the first order world. In fact, you have always been talking about a term where you never were talking about higher order functions or any property on the higher order world, okay? And till now, all good. I think we have seen a lot of examples in the lean thing as well of these kind of things. The things become trickier when you are into higher order functions, okay? And what are these functions? So I think the most interesting ones I will take. So most of these function languages have these higher order functions, these are functions which basically takes other functions as arguments. So they can also return other functions as return values. And a classic examples are map, filter, and fold, okay? So one of the questions is like, with whatever types the way we have defined the types and I have introduced them, how do I define a map function, okay? Before you actually see this thing, so I think, okay. So here's the definition of map. So how many of you know what map function is? Okay, so a lot of people know, so but I'll define map or a list or a collection, if you want to say. So map is a function which takes another function, okay, from A to B, and it takes a list of type A and returns you a list of type B. So what it does is basically goes to each element of the list, applies f, the function on that, takes the return value and put it into the new list. Okay, so this is like going step by step into each element and applying this function on that side. So I didn't write the standard type, somehow I missed it, but the exact type in a non-refined type of this will be map is a function which takes f of type A to B, and it takes a list of type A and it returns a list of type B. That's what its type will be. Okay. So this is, if you just look from here to here, that will be the refinement type, non-refined type of map. So now, if we want to give a refinement type for map in general, one of the things we can say is what property should map satisfy. Okay, we have been trying to see this thing. So given that refinement types are capturing some logical properties of these things, one of the property you might say is, okay, whatever map is, it should satisfy that it maintains the size of the list intact. Okay, so that is first level of refinement we can do without any non-trivial kind of addition to what we know. So for example, here we can just say, okay, the refinement type for map could be something like length of mu is equal to length of x's. And this in itself is going to be somewhat useful, that it can prevent you if you're making a kind of very silly errors, or maybe if you're generating code from LLMs, these kind of errors could come. But I don't think humans will make these kind of errors. But or maybe they. So this prevents us from accidentally generating an infinite list or duplicating elementary structures and so on and so forth. Okay. And similar thing you can think of filters. So filter is a function which is basically again takes a predicate, basically a Boolean valued function, A to bool, takes a list, and basically it returns a list of all those elements of the original list for which the Boolean predicate holds true. Okay, so it basically filters the element based on your predicate function. And here again you can think, okay, whatever is the list it returns, it must always be less than that. We can also go further down. Okay, so in this particular case, for example, we can also say, okay, whatever elements are in the final list will always be an element of the input list. So we can also talk about membership kind of properties which we saw in the morning. So far so good. Okay. So but how do we type map and filter so that it works for any refinement? Okay, so it takes a function, and remember our functions are also refined type, has refinement types. So these and so one of the examples could be, and if you map an increment function over a list of natural numbers, we should get a list of positives. Okay, so that's what I want, that if I'm applying this to a list of natural numbers, I increment all these functions, I get a list of positives. Okay, but there is no way, none of our systems were talking about a property, so property of the function itself. Okay, so there was in general what we want is, while trying to map, if a function f, which is an argument to map, transform an element with property p into one with q. So if f is basically transforming input having property p to q, then map should perform a list where all elements satisfy p into one where all satisfy q. Now this, remember, is talking about properties for all p and q now. We are in kind of muddy waters now, where refinement type people, we all get very kind of afraid. Okay. So good thing is that people have spent some time in these domains, and there are notions which basically capture some of these things. And one of the interesting notion which could be very interesting for people who want to kind of look into these higher order properties and still get a kind of some automation is this idea of what is called as abstract refinements. Okay, and the idea is very similar to, like, you have these type variables. You think of predicate variables, like p and q, and you basically use them in your type as and how you want. Okay, so you define these predicates, but before you actually throw it to type checkers, the neat thing is they will be instantiated with an exact predicate. Okay, so so you won't be proving this property for all p and q. You will instantiate it first and then throw it to solver. But I'm not going to talk too much about how you get that engineering thing done. So this is not exactly abstract refinement. This is not polymorphism in the most general form in terms of that. But it is if you are aware of OCaml kind of polymorphism, in the type variables is that kind of polymorphism in the abstract world. So let's try to understand this abstract refinement with another example, okay, before coming to map, which is a much more abstract thing. So let's say I am defining a max integer function, okay? A max integer is a function which takes 2 integers and returns an integer, okay? And then I wanted to see, okay, if this max integer function is applied on 2 even integers, then ideally I should be able to prove that the return thing is also even integer, because it's picking one of them and returning you. So by definition, if both of them are even, then I should get this property in the output that this is also even. But unfortunately, I don't get that automatically. So if I want to use this max int in a context where the output requires an even thing, I can't directly pass max x of y, okay? What I can do is I can define another function, max int even, and then I can give, okay, if the both of the inputs are even, then you basically get even. But this is much more restricted or much more refined function, okay? So this won't even allow the context where the arguments are not even, okay? So what actually is these kind of cases where you want some kind of polymorphism in terms of no matter what the refinement is, if both these arguments do satisfy that property, then the output should satisfy the property, okay? That's what you are saying right now. So this is what you can do with this, what is called as abstract refinement. So you say that, okay, my max int now is has this kind of implicit, if you want to call it, these are not implicit parameters. So basically you have these abstract refinement predicates, P and Q, in this case only P, and now you are saying that whatever is the predicate which the 2 integers satisfy, the output will also satisfy that. Okay, so now this P could now be the kind of things which we are saying is even, is odd, and others. And remember, is even and is odd will be defined by some measures. Okay, and remember those measures will be some integer to Boolean function because it's even and odd. So later on you can take P and instantiate if it is even and is odd, and so on and so forth. P is a measure, so no, it is not redundant because in some sense you can say that I'm saying that this is a predicate, so it is redundant. But remember, there is some kind of search happening internally when you are actually instantiating it, and P could be any measure in general. Okay, so you can say that I might say that P is length. The other thing is the size of tree. Okay, so I can define P one measure as the length of a list, other as the size of the tree. Now my types can actually say that P of first thing equal to yeah, length greater than something. But what I'm saying is that could be one thing, or it could be that I define P as the length of a list. Let's say my function is taking a tree and a list both. I will define one measure over the list, one measure over the tree, and then I can check that the length of the list and the height of the tree are somewhat related or something like that. Okay, so in general, it's not always necessary that but you're right. In the end, this P here, whatever your thing is used as a predicate, will be a Boolean thing, and this is what it is saying. So this int of angular bracket P is an abbreviation for just simple thing that V of int nu of int such that P of mu holds true, which by definition, as you are saying. Okay, so now you can give this kind of type. Now, in fact, you can also do something like you are defining how much time I have. Just 5 minutes. Okay. So I'll cut short some of the examples. Okay, so one of the examples, I think it allows you to do. So now we can come back to at least the map function. Okay, so now I can do interesting things with maps. So remember, I said like for any property P, if f takes any property P to Q, then map should transform the list, and now it is easy to define. And in fact, if you use any of these type systems, you're welcome to kind of use our type system, which is in some of the artifacts we have. Plus, Liquid Haskell is one of the more popular ones, which they have done, at least earlier they had done very good job. I don't know how much they are following. So now you can define these kind of interesting things. Okay, I think I won't do the fold case, which is the most kind of complicated case in this, because remember, fold, you are maintaining multiple things. So fold operation works in the following way, that you have a function which basically works over a list and some kind of accumulator, which you are accumulating, and it is basically going to each of the element in the list and accumulating some information about it. Okay, that's how you can folding what or catamorphose. Okay, so particularly what I will say that in order to prove give a precise type for fold, you need some kind of inductive invariant to be holding, and that inductive invariant is being listed over here. One of the thing is that if I can say that my base empty thing is satisfying P, and my function which I'm applying satisfies some property, which is an induction hypothesis, then basically I can say that, or maybe I should say that, since I'm here already. Okay, so fold is basically going from, is a function from A to B to B, so where A must be the element of the list, B is an accumulator, you take the current element, the accumulator, and returns a new value of the accumulator. You start with some initial value of the accumulator, and then you basically have a list, and you finally give the accumulated value altogether. Okay, so if you understand it in a different way, it's okay. But in order to give a type to fold, okay, how would you give this type? The thing you want to say that if I have a predicate which takes a list and the accumulator and calculates some invariant over there. Okay, so P is that invariant which basically at any point the remaining list and the current accumulator holds over the accumulator in the remaining list. And additionally, if I can show that, okay, on the original list, the initial accumulator, if this predicate holds, okay, so remember P has two arguments, P of empty says that P empty and B holds, that's what it means. As well as if you say that for my function, that is the operator which fold is kind of folding with, does satisfy the property. So forget this thing, this is just for proof, for help of the type checker, that if I am looking at the current element, I have a property which holds for the accumulator plus the remaining thing, that is this invariant holds initially. Then I can, if I can say that it invariant hold for this newly constructed list with x and x's. So so this is like an inductive hypothesis. The property holds here, and for the current element, if I increment it by 1, then basically the property holds. Then I can say that the property holds for the overall thing. So what you are building is an inductive invariant and trying to. So now initially I said that you don't have to give much things to the type checker. For many of the fold operations, you will have to provide these invariants either in terms of some axioms to the solver in the background, or most of the type checkers will ask you to put some annotations giving these properties. Okay? Okay, so I'm not going to do sorting. The only interesting thing I want to say is, like, once you have specified a property of sorting, you can change your functions internally to quick sort, merge sort, and any other sort. More or less, you will be able to, even with the recursive function, you will be able to, type checker will be able to prove whether it's correct or not. You once have to write the specifications, and that's very neat as compared to as you go along trying to look in the automation side of this thing. Not going to talk about this. So another thing which you can do is basically you can, and I think Prathamesh was talking about monads to kind of model these states. Refinement type world also, so because you want to kind of model many of the stateful properties, people have defined bind and return operators, which are higher order functions. Just like I have been giving these types to fold, you can give types to these bind and other operators, and then you basically can use them to compose these things together. Again, we have done this thing in, and I think where this becomes particularly interesting is this kind of a world of parser combinators. If you have written these programs, these are extremely high order programs by design, and and particularly we wanted to kind of see whether we can define a DSL where we can use refinement types to check properties of data dependent and other context sensitive parsers. Okay, so we were not interested in checking the full correctness of parsers, which is a very hard task, and I don't think you can do it. I don't think it's not a correct assessment. You can't do it, check all these properties and check into refinement types. But what you can do is, like, certain data dependent properties that you parse some portion of the input. The value of that is what the length of the remaining portion depend on, which is very much common in packet parsing. Or the kind of cases like you have in context sensitive cases in C-like parser. So there is when you are looking at an identifier, whether it's an identifier or it's a type declaration, Sometimes it's context dependent, and C internally, if you look at the C parser, which at that time I had to look a lot into deeper details, it does a very hacky thing about passing information from lexer to parser and parser to lexer back. So we can prove in our type checker that if you write with our parser combinators, you won't get those kind of errors. And the only neat thing is that we define these kind of these kind of specifications which can talk about horse style of specifications. Okay, so the specifications till now had been totally functional, although dependent but functional. Refinement types, we and others have also extended them to talk about horse style reasoning, where you can talk about. So for us, it was that it's a parsing expression with some kind of effect, so you can ignore that. Saying that in the input heap, if phi1 holds, and you run the program, whatever for this type is defined, you get a return type tau, and the output heap and the input heap are related by phi2. Okay, so this is like horse style reasoning. You start with the precondition phi1, you run the program, and we were only looking at terminating programs. So upon termination, you basically get this post condition. So ours is not the only one which basically does this thing, and through this we were able to check a lot of interesting properties into the parsing world. But I don't want to go in that direction. I also want to talk about one more kind of, and there are examples in this which shows that, okay, you can actually assign a type to this parser and you can check it. But what I actually want to talk about is this another direction of refinement types, okay, which we recently started to take. Just 2-3 minutes, I'll try to wrap. So till now, all our type systems, and even in all our proving in the lean world in the morning, has been about what are called as OR approximation, or a kind of proving safety properties of these programs. Okay, you say that I have a program, a term, or data, and basically there is a property which is defined either by a theorem in lean or by a type, and I want to check whether this program always is safe with respect to this property. That is, whatever value it reduces to, and safety in this world means like whatever value or canonical form it reduces to, it satisfies my specification. Okay, so that's the standard notion of safety verification. There is a dual notion of what is coverage verification, which becomes very interesting in the domain of testing. Okay, and particularly interesting in what is called as the property-based testing. Okay, so now property-based testing, I'll have to kind of quickly introduce, and it's a not very difficult thing to understand. So normally you do this unit testing kind of input and output things. In the property-based testing world, you give a property, just like you will give a specification you want to verify about a program. For example, here I'm saying that if I reverse the list twice, I should get the original list. Okay, so this will be my property of interest. Okay, so this is written in quick check, which is a Haskell kind of syntax. So these kind of properties like reverse of list should give you the original thing, could be given as a property. Now what the property-based testing systems do is that they have two components. One is called as a generator, and then the checker. Okay, so generator is basically given this property, it will try to generate randomly a sequence of inputs, and given some bounds, you will have to give some bounds, and then try to kind of test the program you have against the property. Okay, so it's like doing a more targeted approach of testing these programs against a property by randomly generating tests. Still, the test generation is random. Okay, now one of the interesting things in this world is that many a times you have to write these generators which require complex properties of the input. So for example, I might be working with programs, testing programs, which is called program under test. This program under test takes binary search trees as input. Okay, and now if I go to a generator which just generate binary trees, and I try to kind of filter out that as you are doing over here, all those things which are not binary search tree, the chances that I will hit any interesting bug in my program is very low. Okay, so one of the reasons is that the probability that I will be generating binary search tree is very low in this. Okay, so what these almost all these tools, so property-based testing is implemented in almost all the major languages, and what they do is they allow the users to write these generators themselves. So they give you the low-level generators for generating random integers, random booleans, and other things. They ask you to generate these things by composing them together. Their language also have non-determinant. So here is a very good example of a binary search tree, a generator, which basically takes two elements, low and high, and the goal is that as a user, I want to generate all possible binary search tree whose values are in between low and high, where node values are in between low and high. Okay, So this is what I want to do. Now, one of the problem in this world is, so correctness is just one problem, okay? So if you look at this particular binary search tree, one thing it solves is that it always generate well-formed binary search tree, because there is a check on the properties about low and high, and for each of these, you are generating these values. Yeah, so you are basically dividing it internally. But the dual problem is, how do I know that it is generating all possible values in this range is very hard to prove in this world, okay? So people just rely that it might be doing this thing, or do some kind of frequency that I want to increase frequency of this term or that term. What we have shown is that you can build a refinement type system, which we call as coverage types, which can actually, given these kind of programs, and these programs have non-determinism inside, prove that actually, given a property, you can prove that you are going to generate all possible trees satisfying that property, okay? And I'll try to kind of just give you the high-level gist of this. So normally in refinement type, I mean, like, if this is a type, then every value produced by this expression must satisfy. This is the coverage type notion. The writing is kind of similar. You refine it just with the square bracket. All it says is that this generator is capable of producing every possible value that phi satisfies. Okay, so this. So I'll try to kind of wrap in the saying that, okay, so this leads to interesting duality in subtyping and all other things. You are welcome to see the paper. I'm not going to go into this. So, but overall, what I will try to kind of conclude with this thing, where refinement types shine on some of the things. They shine on automation because of around 20 years of research in that world. A lot of things have been tried to be automated and then thrown to solver. They struggle with a lot of things. Every time you are going into higher order logic, they struggle with that. And there have been newer and newer domains, going from security to other domain, where still refinement types are continuously being implemented and developed. We are also doing some of those things. So overall, this marriage of refinement, and more recently, I can talk about that offline, there is this marriage. A lot of people, Ilya is one such person who is basically trying to embed these kind of refinement types into lean kind of machinery, which will be very kind of innovative thing. So thank you. So they are not interested in decidable fragment. I think what is happening is embed I means that normally refinement type is always built over a domain a language machinery. Okay, so rather than building it as an individual thing over a new language, what we'll do is you will shallowly embed these specifications and everything in lean. So what it gives you is that, okay, for you want to prove certain properties. I think there's some connection they're also making that you can directly make a call to solver. I don't know how that they are doing. For other things, you do these tactics. If you can't prove them, then you take these theorems and throw it to Claude kind of system and take the proof over there. So I think it's an interesting thing. What I mean is a shallow embedding of refinement type system, which is basically the language and the typing rules in lean.
One thing that you get is that if it almost succeeds automatically, little bit is remain, the user can come and try to map it.
Yeah.
While here, if it fails, it simply fails. Yeah. User has a second chance.
Sorry to eating your time.
Due to shortage of time, we'll just take like maybe one more question and then we'll move on to the next.
I can talk offline as well.
Yeah, after the talk works also.
You have a question?
Yeah, maybe we can discuss.
Yes, okay. So this is the last talk for today. This is a continuation of LeanLang that Professor Gadgil has been doing. So yes, I'll just remove this.
Wait for step the power cord. Gets confused and tries to run power from the USB port. We now hope for the best. That splitter, so I'll try mine. Okay, thank you. So to celebrate this working straight away for the last time, let's begin it. It's already, of course, way behind schedule. And morning, everyone was energetic. Now, of course, we are all tired. So I'm not going to do very much. What I'll do is we'll sort of morph into the discussion for Hackathon. So let's start by saying, yeah, thanks, Abhishek, Ashish, and Prathamesh for many very nice talks. We have seen many things today. So we'll see a couple of very basic things, and the idea is tomorrow when people start picking up their projects, we'll be around. And ad hoc, whatever you want to learn on Lean, you ask us. There are endless number of things I can do, and we'd want to do, but we'll resist the urge to do it because people have to get home and so on. Just ask people whatever you want to do. But there are some minimum things. But first I have to answer a question from the morning. I realized you had asked about grind, what about counterexamples? I gave half the answer, but I forgot the other half. That if grind fails, the error message often has a model which gives you a counterexample. Actually, it tells you this model satisfies all linear constraints. It's not technically a counterexample, but one can programmatically or manually extract a counterexample often, if it falls within the kind of SMT domain. So you're right about grind. I guess that was your instinct that SMT solvers also give models. And yeah, because grind is a best effort thing. It doesn't actually tell you it's false. However, it gives a trace which actually contains, in many cases, a message. Yeah, so thanks for that question. Okay, so we'll have to do a few practical things when we are talking about the hackathon. This was a rather ambitious goal in the hackathon. It's a little less ambitious than the original plan, which is people simply start hacking in Lean. So I had the tutorial because I said not enough people know Lean, so that would be a bit absurd. So this is kind of a compromise. And the idea is that for agentic verification, you can do one of two things. Either have a model system of agents and show that they do safe things. For example, they don't leak passwords. Or take a domain and assume what you are verifying is an output matches the domain. And we have seen various domains as examples. Yeah, I won't discuss more. We can if there are questions, but not right now. Tomorrow we assemble those who are hacking in another room, and we'll discuss these generalities, and in one-on-one you can discuss any background you want to know. Okay, but of course one of the things you have to do in the real world is read files. So in Lean, you can read files by using this thing called IO is input output, FS is file system. These are the system commands. When I open these things, it means that I can use shorter names. Okay, so there is a file called read file which just reads it as a block, and if I evaluate, I get a file. So I just read the read file. Okay, read me I evaluated. I got a JSON file. Sorry, read me file. That's all this is. And here's a JSON file. Another thing you have to do in practice when you're dealing with any domain, you can extend syntax and try to make a domain specific language, but the easiest thing to deal with in the real world is JSON. And you can get an LLM to make an output of a JSON thing with a schema for you. You have to process that in Lean, and Lean has built-in JSON support. In fact, its lake manifest is a JSON file, so it sits in this directory. How do I read it? I read it by using a thing called json.parse, lean.json.parse. And lean.json.parse either parses and gives you JSON or it gives an error. Okay, Prathamesh used option types. Except type is a little better than option. Instead of just saying none, it gives you an error. Okay, and so if I evaluate lake manifest JSON, it gives me this. In fact, if I had instead used, so in this case it looked at lake manifest and I did it here. Now one thing to deal with JSON, just because we are dealing with JSON, is there's a literal syntax. You write JSON%. This is one of the kind of syntax extensions I did for Py4, and then write JSON, it understands it. Okay, so here we are. Now I would have liked to explain this example in detail, but given shortage of time I won't. I will instead show you a spiffy feature of Lean, and you can ask me tomorrow or later how to implement this kind of spiffy feature. See, what is annoying here is because so the key property of a function is its value. If you give the same input, should have the same output. Okay, but that's not true when you read a file, because the file may change on disk. It depends on the environment. So you cannot actually have a string as a file. What you have instead is IO of string, where IO has some state, in this case state of the world. But that's a nuisance. What I say, I want to tell me just what the file is right now and freeze it as that. Okay, so let's see. So what we can do is we can write a so-called elaborator. I'll go back to the elaborator, but let me show you it in action. So in action, if I have an example file and I say load readme.md, okay, and then I evaluate, this is just like the previous one, it gave me this. But what has happened is you see this nice blue line here, and you see an apply, and if I click on this apply, it freezes and gives it to you. Okay, so this was just showing a nice feature of Lean. Here, this is an important example for the real world thing. This is extending syntax. So what we did was used a little elaborator here. So first thing I did is, let me say these because these are conceptually important. What I told you, Lean has syntax. Syntax can mean many things. It can mean commands, it can mean terms, it can mean just arguments, it can mean function applications, very specific things. But you can also create it can mean JSON, or you can create your own entire category of syntax. And I have created a category called file path. Okay, and then I say there are two kinds of syntaxes with file path. Either a string is a file path, or you use a file path / string. The reason of this is I want to make things system independent, right? File paths are different in Windows and in POSIX systems. So because you want to make it system independent like this, we'll create our own syntax category and use Lean system.filepath, which is system independent, and map this syntax, T syntax means typed syntax, to that. And then I create this little syntax which says load file and load the file using this. Okay. If you want explanations for this, catch me later, because right now I'm going to go to the final thing that I want to do. And the final thing I want to do is, as I said, there are two different, okay, and I think this is worth going into Zen mode for. Two different things we can mean by agentic verification. Build an agentic system and show that it does not do wrong things. So this is really an absolute toy version of this. Okay, we are building a agentic system which can read or write files. That's all. Okay, that's good enough to mess up your system thoroughly. So we want to be safe even with this kind of system. So it's worth verifying it, but we'll verify only very limited features of it. But conceptually, you can see how to generalize. I want to show what is the idea of the core idea. Okay. So first of all, there are two file commands which, given a file path, will give you. So what is a file command? A file command is a file operation which after it returns something. Okay. So if you read a file, it's a file command which returns a string. And if you write a file, you have to give it a file path and give it the content, and it returns nothing. Okay. Now in functional languages, you can't actually return nothing. What you return is something of type unit. Unit has only one element, so you are returning no information. So that's how you handle types in functional languages. So now this is what is called a free monad. I was just asked about that a little while ago. So what is a program? So we are going to write programs. We saw Prathamesh had an example, add one and so on, with just these two operations. We are going to have a program. You could add any number of operations here. Conceptually, it's the same thing. Okay. It is like our stack machine, but our stack machine only had a site. It did not actually return a value. So this is a little more sophisticated. So our program is either it simply returns a value of type alpha. So a program to give you an integer could be just an integer. This is a pure program, a do nothing program. Or cons, which is like lists cons, which will tell you that if I take a program that gives me beta, and something which given beta gives me a program that gives me alpha, I can compose this and get a function of type program which gives me alpha. So phylem is the monad of file programs. So your file programs of type alpha, and by making this an inductive type, it means that given any sequence, we'll write some actual programs later and prove something about them. We can get these things. Okay. So we saw with lists you can flat map, which is that given alpha to phylem, and phylem to alpha. We have, so given two types and given a function from alpha to beta and given an element of type program which returns alpha, I get a program which returns beta. That is just, if it's a pure function, it will just get f of a, and cons you get this element. Okay, so this is just a composition by flat map. And once we have this, we have a monad. Okay, so monad structure is the one that lets us use that spiffy do. Prathamesh ran out of time while trying to explain in his case with the programs. It makes composition clean and nice. It also has a bunch of other things, monad transformers, lifts, this, that. Whole lot of helpers have been built around this monad. You have a powerful library of helpers going beyond the do notation for composition. So we say phylem is a monad. So pure is like a single element in a list. The equivalent is just returning the value. And a flat mapping, we can flat map. So you can combine flat map and pure and map. Okay, and this monad we can read in, and this is just a renaming of the phylem.read and phylem.write. Okay, and like a state monad we can run. So, well, now forget the fact that it's a monad. This is a program. This is a program built out of doing two things, reading files and writing files, but also functions which are simply just ordinary lean functions, and also various composition. So we have a program built with that. Okay, so one of the programs we will write is we'll read from one file, read from another file, concatenate this, putting a blank line in between, and write to another file. Okay, so this is a program which can be built from these. We'll see with this. So running, it's just routine how you do it. You just think what it means. When you run, you have to return a value. I mean, because you need file operations, it's actually still an IO value using our older return. Okay, so now comes the interesting part. So this was our agentic system. Okay, so our agentic system is built by saying agents have this bunch of formal capabilities. Okay, so the formal capabilities are just a list with their types, enriching them. And then you have a run which binds it to the real world. The run or evaluate or whatever tells you how to model it in the real world. You could code generate Python instead as a running. You could do various things, but you connect it to the real world. But now we want to know whether things are safe or not. Okay, so this is a model of this. Already we have seen multiple cases where you can use what was I saying? Inductive types to sort of axiomatize what is a model of it. So this is an arbitrary toy model I have made. Any natural number is safe. Okay, we like numbers. They can't have anything evil in them. If I add two safe strings, I get a safe string. Okay, and I declare a few things like space and new line and semicolon are safe. And padding to the left and padding to the right is safe. Actually, the last two are completely unnecessary because I can use space and string append. I don't know why I put them. I hope. Did I get an error by that? No. Okay, that's padding left gets derived from this. Okay, so here is a theorem. It says that if I have two strings, then if I take the one string, then a enter, and then the other screen, new line, this is safe. Why is that? That is simply composition of these properties, right? You want to show that this is safe. See the goal, we have to show safe val s plus concatenation of these strings. Okay, I'm going to say that if I apply string append so and so, then it reduces to saying that we have to show this is safe and we have to show t is safe. T is safe by assumption. And again we assume new line is safe, and then we are done. Okay, so sorry, here I'm breaking it up into saying S is safe and new line is safe, etc. So I just composed this and got it. So I'm going to say safe path. Okay, this is, of course, you can use dot dot and mess it up. As I said, this is a toy model. You want to do better than this. A safe path is something which begins with either public or which begins with data. In reality, you have different safe paths for reading and writing. You can refine this model a bit accordingly. So a safe program is the following. If you take a safe value and take pure that, then it's safe. So if you are just going to give a number from some lean code, you have to already prove it's safe. Then that's fine. Reading is safe so long as you read from a safe path. Writing is safe provided you can write to a safe path and your contents are safe. You can't write a dangerous string to a safe path, right? So this is really modeling the real world. I think you can all start thinking of more serious agentic things. Okay. So for example, I would really want to separate read safe and write safe. What I wanted to do was say data can be written and read, but public can only be read. Okay, so you would want, that's one of the first refinements you want to do. So write safe is path should both be safe and the value that you write should also be safe. But whatever you read from a public path is automatically safe. And then if you compose safe things, then you're fine. Meaning, actually less than that. What I'm saying is that if I have a quantity x which is in phylum alpha which is safe, okay, so x is the result of a safe program, and I have a function with the property that it takes any safe value to a safe program. If I have a function which has this property, then the result after we compose is a safe program. Okay, that's completely logical. We ran a safe program and we did something else which, so when we ran a safe program, what we got in that program is a safe value, and then when we compose it, we are composing it by something which preserves safety preserving. Okay, so great. This has modeled everything. Now we can actually prove theorems. Okay, these are the theorems that, as I said, usually you want to extract from the definitions because you may change your definition later. These are just restating the definition. Okay, so now let's look at some programs. Here's a program which, given a file path P, it reads from the public /P and writes to data/P. It's copying from one directory to the other. Okay, and here's a theorem. This is safe. Okay, so now we are actually proving something. We have proved absolutely in Lean. I mean, of course, if you're saying this for the first time, you won't fully digest what is going on. But we have actually proved that this program is safe in our very precise sense. We use the fact that flat map is safe. So this is kind of encouraging because though we use monads and so on, it got rewritten to maps and flat maps and so on. So we use that flat map is safe. Okay, and that left you with certain goals, and then grind used the previous results to do it. So we read a file, wrote it somewhere else. And the final example maybe is that we merge public pubs. So we take two public files, P1, P2, and have an output file. And what we do is we read public/P1, public/P2, merge them with taking the first one and then blank space and then the second one. And then I write this to the data/out. Your instinct tells you that this is safe. The point about this is, of course, as I said, you can be very careful if you want to try to have much more complicated programs, but you want to sort of automatically prove that they are safe. Okay, and indeed you can prove literally that this is safe, that you read it with flat map safe, and then you read and then you write these operations and do it. Now when you want to automate this kind of agentic flow, what you have to do is build such bunches of basic theorems and annotate them with grind and so on, so that automation will programmatically prove it for you, not in a specific case. Or you can get an LLM to help you prove it, or various other such things with hints. But nevertheless, you can't be afford to manually prove this. So this is not there yet, in addition to being a toy example, but maybe so slightly conceptually heavy, but I thought I'll just so this is a toy example where we kind of made operations which could be messy, but we not only wrote a program, we wrote a program which and then proved that it's safe in an absolute sense, which you would want to do for agents. Okay, so I think with that I'll stop and any discussion if you want for these things. Tomorrow the day is quite open for discussions. So yeah. So thank you all. So in the case of agents, the programs should involve LLM calls as well. So this is the agentic network. This agentic no, so that's so.
Here
Okay, okay, both. Yeah, no, your answer is correct. Yeah. Yeah, so there are two ways in which agents come. Yes. Okay, there may be at least two ways in which agents come. One is, as you said, the agent can write the program given the capabilities of the agent, and then you have to prove it is correct before it is allowed to run. So like I had in the other thing, the evaluate would take proof of correctness, and you're only about to. But also, the operations can involve calling agents. And you also have to say that anything that comes from an agent, you don't want prompt injection, so you don't want that to be written to a file. And also the operations should involve, for example, secret keys, which are used for agents, but they should also involve sending WhatsApp messages, but not sending secret keys on WhatsApp messages. So there should be not one property like this, but a whole bunch of properties which will interact in interesting way. Yeah. Correct. Yes, yeah. Indirectly, sorry. So what we still do in Lean, it's not yet come, is there is io.process which runs a process, and we just use curl. I mean, that's how everybody who uses Lean and AI together. So you just use curl for network operations with that. Yeah, but there is an io.process which runs things. By the way, there is a meta-programming recipes which a bunch of us put together exactly for these kinds of things. I'll share a link to that in Zulip. And yeah, and of course, the point is we are around for questions now, of course, as well as tomorrow. Yeah. Any other? Yeah.
So there was one question
yeah.
from the morning session on YouTube.
Okay, sure.
I think it was directed to Professor Abhishek, but yeah, but anybody.
Okay.
So the question reads, I don't know if you can project it. So it's, do you think that TLA plus or Lean or While could help in developing CPU or AI chips when applied as HDL to Verilog or VHDL? Maybe, I don't know. You want to read it?
Yeah. So I just set this.
So I think people are already using this to model and then verify these kind of things. Okay, so this is already in use.
Are there any more questions? Okay. So if not, thanks for attending. We'll have tomorrow's hackathon session in Old Physics Building, which is near the library. Yeah, and we'll have breakfast and lunch and everything. So let's have fun tomorrow. Yes. Thanks.
Sorry, what time do we begin tomorrow?
9:15 is but the breakfast will be from 8:15. So yeah.
Okay. Yes, there are blackboards.
There are blackboards, yeah.
Those are
it's in the classroom.
UG lectures take place. So there. No, this place didn't have it, so that's it.
करता हूँ सर बात। हेलो हेलो हाँ हेलो हाँ बोलो। रजिस्ट्रेशन हाँ अच्छा अच्छा ओके हाँ हाँ यार क्यों बदलना है क्या बोला मैं पूछ के बोलता हूँ बोलिए अभी वो लोग आ गया है दूसरा सेटअप करना पूछो